that of most other Kuiper belt objects, KBOs, which has aided in its detection and characterization. Makemake orbits the Sun at an average distance of about 45.7 astronomical units, AU, equivalent to roughly 6.8 billion kilometers. Its elliptical orbit takes it around the Sun once every 305 Earth years, with a slight inclination of 29 degrees relative to the plane of the Solar System. This inclined trajectory places Makemake among the dynamically hot KBOs, which have orbits more tilted and eccentric than the cold classical KBOs like Quasar. One of the most intriguing aspects of this Kuiper belt object is its lack of a significant atmosphere. Unlike Pluto, which experiences seasonal atmospheric changes due to the sublimation of nitrogen and methane ices, Makemake's tenuous atmosphere, if present at all, is likely composed of trace amounts of methane and nitrogen. Observations during stellar occultations, when the dwarf planet passes in front of a distant star, have provided valuable constraints on its atmospheric properties. These events reveal a sharp drop in brightness, indicative of a lack of a substantial gaseous envelope. In 2016, the Hubble Space Telescope made a groundbreaking discovery by identifying a small moon orbiting Makemake. This satellite, unofficially nicknamed 2 Malawian Kwachas, is estimated to have a diameter of about 175 kilometers. It's the trans-Neptunian body, known as Makemake, stands as a remarkable example of the icy worlds populating the outer reaches of our solar system. This celestial object, part of the Kuiper belt, occupies a region teeming with primordial remnants from the early formation of the Sun and its planetary system. Since its discovery in 2005 by a team of astronomers led by Michael E. Brown, the frozen sphere has captivated scientists eager to unravel the mysteries of these distant and enigmatic objects. This dwarf planet, the third largest among its peers, boasts a diameter of approximately 1,430 kilometers, situating it in the same category as Pluto and Eris. Unlike the inner rocky planets or the gas giants, the icy surface of this world is composed primarily of frozen methane, ethane, and other hydrocarbons, which give it a reddish hue. Spectroscopic analyses, carried out with advanced telescopes like the Very Large Telescope, VLT, in Chile, have been pivotal in uncovering the chemical composition of the Kuiper belt object. Orbiting at an average distance of 45.7 astronomical units, AU, from the Sun, this remote sphere takes approximately 305 Earth years to complete a single orbit. Its elliptical path, inclined by 29 degrees relative to the ecliptic plane, distinguishes it from many other solar system objects. These orbital characteristics classify the icy body as part of the dynamically hot population of the Kuiper belt, where orbits tend to be more eccentric and inclined than the cold population. Interestingly, this far-off world exhibits a surface that is highly reflective, with an albedo higher than that of most other trans-Neptunian objects. This bright reflectivity, coupled with its size, made it a relatively easier target for telescopes to detect compared to smaller, darker Kuiper belt objects. Its icy crust, composed of solidified methane and nitrogen, reflects sunlight with a unique reddish tint, linking this distant body to other notable objects like Pluto and Triton, Neptune's large moon. Unlike Pluto, however, this celestial body lacks a significant atmosphere. Stellar occultations, events where the icy sphere passes in front of a background star, have revealed that it does not possess the thick layers of nitrogen and methane gas seen on its sibling dwarf planet. At its average surface temperature of -243 degrees Celsius, any gases would freeze rapidly, leaving only a tenuous, almost imperceptible envelope of methane molecules. Adding to the intrigue, in 2016, astronomers using the Hubble Space Telescope uncovered a faint satellite orbiting this frozen world. The Moon, provisionally labeled 2 Malawian Kwachas, is estimated to be about 175 kilometers in diameter. The discovery of this satellite has opened new doors for research, allowing scientists to measure the mass and density of the dwarf planet with greater precision. By observing the orbital dynamics of 2 Malawian Kwachas, researchers aim to gain deeper insights into the internal structure of this trans-Neptunian object and its formation history. The discovery of this moon also hints at the possibility that this distant body underwent a significant collision event in the past, similar to the impacts theorized for other dwarf planets and their moons. Such events are thought to have played a critical role in shaping the Kuiper Belt as we observe it today, providing clues to the early chaotic phase of the solar system's evolution. This icy world's methane-rich surface composition links it chemically to Pluto and Triton, suggesting a shared evolutionary pathway for these distant objects. Methane, one of the simplest hydrocarbons, plays a vital role in determining the color and reflectivity of this frigid world. The reddish hue observed on its surface is likely the result of complex organic molecules, known as tholins, formed through the interaction of methane with ultraviolet radiation from the Sun. These tholins are common on outer solar system bodies and are responsible for the strikingly varied colors of trans-Neptunian objects. Scientists hypothesize that the distant sphere's lack of significant nitrogen ice might be due to its smaller size and weaker gravity, which would make it more difficult for the object to retain lighter gases over billions of years. This hypothesis contrasts sharply with Pluto, which has managed to sustain a thin but dynamic nitrogen-rich atmosphere. The comparative study of these worlds offers a glimpse into the diversity of conditions and evolutionary pathways among objects in the outer solar system. Further investigations into this Kuiper Belt member have been bolstered by advanced telescopic technologies and computational modeling. Observations using infrared spectroscopy have provided evidence for seasonal changes on the surface of this frozen sphere. These changes, though far less dynamic than those on Earth or Mars, hint at subtle shifts in the distribution of ices as the dwarf planet travels through its elongated orbit around the Sun. The exploration of this enigmatic object has also fueled discussions about potential spacecraft missions to the Kuiper Belt. While current missions, such as NASA's New Horizons probe, have provided invaluable data on similar bodies, a dedicated mission to this dwarf planet and its moon could revolutionize our understanding of the outer solar system. By studying this world up close, scientists could analyze its geology, surface chemistry, and potential subsurface layers, answering long-standing questions about the building blocks of planets and the processes that govern their evolution. This frozen world, residing in the cold and distant reaches of the solar system, represents a time capsule of early solar system materials. Its study not only sheds light on the dynamics of the Kuiper Belt but also provides broader insights into the mechanisms that drive planetary formation and migration. Through ongoing research and future exploration, the mysteries of this icy body continue to inspire curiosity and expand the boundaries of human knowledge. The frozen orb stands as a crucial key to understanding the broader landscape of the Kuiper Belt, a region that serves as a repository for ancient materials from the dawn of the solar system. Unlike the rocky planets of the inner solar system or the gas giants further out, this remote celestial body represents a category of icy worlds that formed in the outermost reaches, where the sun's warmth is but a faint glow. Its composition, structure, and orbit together create a unique portrait of conditions far removed from those familiar to Earth-bound observers. One of the remarkable features of this Kuiper belt resident is its stability over time. Despite its vast distance from the Sun and its relatively small size, the dwarf planet has maintained a consistent orbital path for billions of years. This stability has allowed astronomers to study the interactions between it and other trans-Neptunian objects, offering critical insights into the gravitational dynamics of the outer solar system. The inclined orbit of this icy body, with its significant tilt compared to the plane of the solar system, suggests a turbulent past. It is likely that gravitational interactions with Neptune, or perhaps with other large Kuiper belt objects, played a role in shaping its current trajectory. The absence of significant atmospherics on this distant sphere has not deterred scientists from probing its surface for clues about its evolutionary history. High-resolution imaging and spectroscopy have revealed a patchwork of icy materials, including solid methane and ethane, alongside traces of more complex organic molecules. These compounds, while frozen solid under the extreme cold, bear evidence of photochemical reactions driven by the faint sunlight and cosmic rays that permeate the outer solar system. The reddish tint that characterizes its surface is a hallmark of such processes, with tholins, organic residues formed from methane, providing the distinctive coloration. Further exploration of this icy sphere's surface has revealed intriguing hints about its geological processes. While its small size and low gravity likely prevent tectonic activity or large-scale volcanism, there is evidence to suggest that sublimation and deposition cycles may occur on a seasonal basis. As the frozen world moves closer to the Sun in its elliptical orbit, some of its methane and nitrogen ices could transition directly from solid to gas, creating transient atmospheric effects or causing slight changes in the surface texture. These processes, though subtle, are of immense interest to planetary scientists, as they mirror phenomena observed on other Kuiper belt objects like Pluto. The discovery of a small satellite orbiting this celestial object has added a new layer of complexity to its study. 2 Malawian Quachas, as the Moon is informally known, is much darker than its parent body, reflecting only a fraction of the sunlight. This stark contrast in albedo suggests that the Moon and its host may have originated under different circumstances. One prevailing theory is that the satellite was formed as a result of a massive collision, similar to the events that are thought to have created Pluto's moon system. Such a collision would have ejected material from the surface of the icy world, which later coalesced to form the smaller companion. The existence of 2 Malawian Quachas also provides astronomers with a unique tool for studying the mass and density of the frozen orb. By carefully tracking the motion of the Moon around its primary, scientists can calculate the mass of the entire system, shedding light on its internal composition. Early estimates suggest that the density of this Kuiper belt resident is lower than that of Pluto but higher than some smaller trans-Neptunian objects, implying a mixture of rock and ice in its interior. These findings hint at a layered structure, with denser materials concentrated in the core and lighter ices forming the outer shell. In addition to its intrinsic scientific value, the study of this remote celestial body holds broader implications for understanding the history of our solar system. The Kuiper belt, of which this dwarf planet is a part, is believed to be a remnant of the primordial disk of gas and dust that gave rise to the Sun and its planets. By analyzing the composition and distribution of these icy objects, researchers can reconstruct the conditions that prevailed during the early stages of planetary formation. This frozen sphere, with its pristine ices and unaltered surface features, serves as a time capsule preserving the chemical and physical processes that shaped the solar system's infancy. The implications of studying this distant world extend beyond the confines of our solar system. Similar icy bodies are thought to populate the outer regions of other planetary systems, where they may serve as building blocks for planets or as reservoirs of water and organic materials. Understanding the processes that govern the evolution of this frozen orb can therefore provide valuable insights into the potential habitability of exoplanetary systems and the origins of life elsewhere in the universe. Despite its remoteness, this trans-Neptunian body remains within reach of modern astronomy. Ground-based telescopes equipped with adaptive optics, as well as space-based observatories like the James Webb Space Telescope, continue to provide detailed observations of its surface and surroundings. These instruments have opened new windows into the chemistry and physics of the frozen world, revealing intricate details that were once beyond the reach of human knowledge. Future missions to this icy sphere, though technically challenging, are already being considered. A spacecraft equipped with advanced imaging systems and spectrometers could map its surface in unprecedented detail, revealing the distribution of ices, organics, and other materials. Such a mission could also investigate the properties of two Malawian quachas, providing a more complete picture of the system as a whole. By venturing into the Kuiper Belt, humanity could achieve a deeper understanding of the forces that govern the outer solar system and the processes that drive its ongoing evolution. The remote icy body serves as a critical focal point for the study of planetary systems in their infancy. As one of the larger members of the Kuiper Belt, it represents a class of objects that have remained largely unchanged since the solar system's formation approximately 4.6 billion years ago. These distant worlds, often referred to as fossils of the early solar nebula, offer a glimpse into the conditions that existed before the major planets coalesced from the primordial disk of gas and dust. The frozen celestial sphere's surface is a testament to the extreme environment in which it resides. Temperatures hover near absolute zero, at around -243 degrees Celsius. At such frigid levels, volatile compounds like nitrogen and methane freeze solid, forming a crust of ices that preserves the chemical history of the early solar system. This pristine environment is not only scientifically valuable but also serves as a natural laboratory for studying the behavior of materials under conditions far removed from those on Earth. One of the most intriguing aspects of this outer solar system world is its potential internal structure. While direct observations are impossible without a dedicated spacecraft mission, models based on its size, density, and surface composition suggest a differentiated interior. Beneath the icy crust, the trans-Neptunian body may harbor a layer of water ice mixed with rocky material. At greater depths, under the pressure of overlying layers, this water ice could transition to an exotic form known as high-pressure ice. Such internal layering is consistent with what has been inferred for similar-sized dwarf planets like Pluto and Eris. The density of the frozen celestial object, estimated from the orbital motion of its moon 2 Malawian quachas, indicates that it is likely composed of a mixture of rock and ice, with rock constituting a significant portion of its mass. This combination aligns with the idea that objects in the Kuiper Belt formed in a region where water and other volatile compounds were abundant, but temperatures were too low for significant accretion of gaseous materials. These conditions contrast sharply with those of the inner solar system, where rocky planets formed in a hotter, more volatile depleted environment. The Kuiper Belt residence moon, 2 Malawian quachas, continues to be a topic of intense scientific interest. With its dark surface and small size, this satellite poses unique challenges for observation, even with the most advanced telescopes. Nevertheless, the discovery of this moon has provided an invaluable tool for determining the mass and gravitational field of the parent body. By analyzing the orbital dynamics of two Malawian quachas, researchers can refine their models of the dwarf planet's internal structure and gain insights into the processes that led to the formation of this binary system. The relationship between this icy world and its satellite raises questions about the broader processes that govern the formation of moons in the Kuiper belt. In the case of the distant sphere, the leading theory is that two Malawian quachas was created through a giant impact, in which a collision with another Kuiper belt object ejected material into orbit. Over time, this debris coalesced into the moon we observe today. Such impact events were likely common in the early solar system, as countless small bodies collided and merged to form the larger objects we see today. In addition to its role in understanding the solar system's past, the study of this remote world holds implications for the search for life beyond Earth. While the frozen orb itself is unlikely to support life due to its extreme cold and lack of liquid water on the surface, it represents a class of objects that may exist in other planetary systems. The presence of water ice and organic compounds on its surface suggests that similar materials could be common in exoplanetary systems, where they might serve as the building blocks for life. Moreover, the exploration of this frozen celestial body and its neighbors could help scientists understand the distribution of water and organics throughout the solar system. These materials are thought to have been delivered to the inner planets, including Earth, by comets and other icy bodies during the late heavy bombardment period. By studying the chemical composition of Kuiper belt objects, researchers can trace the pathways by which life-essential elements were transported across vast distances. Future missions to this distant celestial sphere are likely to revolutionize our understanding of the Kuiper belt. A spacecraft equipped with high-resolution cameras, spectrometers, and radar instruments could map the surface in unprecedented detail, revealing the distribution of ices, organics, and other materials. Such a mission could also investigate the Moon 2 Malawian quachas, providing a more complete picture of the system as a whole. The data collected would not only deepen our knowledge of this specific object but also shed light on the broader processes that govern the formation and evolution of the outer solar system. The technical challenges of reaching the frozen sphere are significant, but not insurmountable. The vast distance, combined with the need for advanced propulsion systems and power sources capable of operating in the frigid, low-light conditions of the Kuiper belt, requires innovative engineering solutions. NASA's New Horizons mission to Pluto and the Kuiper belt has demonstrated the feasibility of exploring these distant regions, paving the way for more ambitious missions in this icy body and its companions in the Kuiper belt are more than just distant curiosities, they are windows into the origins of our solar system and the processes that continue to shape it. By studying this frozen world and its environment, scientists can address some of the most profound questions in planetary science. How did the solar system form and evolve? What role did icy bodies play in delivering water and organic materials to Earth? And what can these distant objects teach us about the potential for life elsewhere in the universe? The scientific journey to understand this frozen sphere is far from over. As technology advances and new discoveries are made, the mysteries of this remote world will continue to inspire curiosity and exploration, driving humanity ever further into the depths of the cosmos. The frozen sphere, a silent wanderer of the Kuiper belt, represents an ancient fragment of the solar system's earliest epochs. Its story is woven into the dynamic and chaotic processes that govern the formation of planets, moons, and smaller celestial bodies. As one of the largest known Kuiper belt objects, this trans-Neptunian body occupies a unique position, bridging the gap between the icy remnants of the solar nebula and the more familiar planetary systems closer to the Sun. The orbital mechanics of this distant orb reveal fascinating insights into the gravitational influences shaping the outer solar system. Its elongated, inclined orbit, which takes it as far as 53 astronomical units, AU, from the Sun at its aphelion, reflects the complex interplay of forces at work in the Kuiper belt. The perturbations caused by Neptune's gravity, along with interactions with other large Kuiper belt objects, have likely sculpted the path of this icy wanderer over billions of years. This orbital behavior is not merely a curiosity, it provides clues to the early migration of the giant planets, particularly Neptune and Uranus, which are thought to have shifted positions during the solar system's formative years. Comparing this celestial body to its counterparts, such as Pluto, Eris, and Haumea, reveals a diverse population of icy worlds, each with its own unique characteristics. While Pluto is known for its dynamic surface and tenuous atmosphere, the frozen celestial sphere lacks such activity, likely due to its smaller size and weaker gravitational field. Eris, the most massive known dwarf planet, shares some similarities in surface composition, with both objects displaying evidence of methane ice. Haumea, on the other hand, stands out with its elongated shape and rapid rotation, characteristics not observed in the more spherical and slower rotating body in question. One intriguing aspect of this trans-Neptunian object is the potential for subsurface processes despite its frigid environment. Models suggest that, under its icy crust, the distant sphere may harbor a layer of liquid water or slush, kept warm by the decay of radioactive isotopes in its rocky core. While speculative, this possibility raises fascinating questions about the potential habitability of such environments. Subsurface oceans have been proposed for other icy worlds, including Europa, Enceladus, and even Pluto, suggesting that liquid water reservoirs might be more common in the solar system than previously thought. The frozen orb's lack of a substantial atmosphere distinguishes it from Pluto, whose nitrogen-rich atmosphere undergoes seasonal variations as it approaches and recedes from the Sun. Observations during stellar occultations have confirmed that any gaseous envelope surrounding this distant body is vanishingly thin, composed primarily of trace amounts of methane and possibly nitrogen. This scarcity of atmospheric volatiles likely reflects the object's smaller size and weaker gravity, which make it less capable of retaining light gases over geological timescales. The surface chemistry of the frozen sphere offers a window into the chemical processes operating in the outer solar system. The detection of methane, ethane, and other hydrocarbons on its surface suggests ongoing photochemical reactions driven by solar ultraviolet radiation. These reactions produce a range of complex organic molecules, including tholins, which impart the reddish coloration observed on many Kuiper belt objects. Such organics are of particular interest to astrobiologists, as they are considered precursors to the building blocks of life. Studying their distribution and formation mechanisms on this distant world could provide clues to the chemistry that predated the emergence of life on Earth. The discovery of two Malawian Quachas, the small and dim satellite orbiting the icy sphere, has opened new avenues for exploration. This moon, with its low reflectivity and modest size, contrasts sharply with its parent body, suggesting a different surface composition or a history of resurfacing events. Understanding the relationship between the two objects is key to unraveling the origin of the system. If 2 Malawian Kwachas was indeed formed through a giant impact, its composition and orbital parameters could reveal details about the violent collisions that shaped the early Kuiper belt. The existence of this moon also enhances the potential for precise measurements of the frozen sphere's mass and density. By carefully observing the satellite's orbit, astronomers can refine their estimates of the system's gravitational field, shedding light on the internal structure of the dwarf planet. Such measurements are critical for testing models of planetary differentiation, which predict that larger Kuiper belt objects should exhibit stratified interiors with distinct layers of rock, ice, and potentially liquid water. Beyond its intrinsic scientific value, the study of this icy wanderer has broader implications for understanding planetary formation across the cosmos. The Kuiper belt is thought to be analogous to the debris disks observed around young stars, where planetesimals coalesce and migrate to form planets. By studying this trans-Neptunian object and its neighbors, researchers can draw parallels between our solar system and others, gaining insights into the universal processes that govern planetary evolution. The exploration of this frozen world and the Kuiper belt as a whole is not merely an academic pursuit, it has practical implications for humanity's future in space. The icy bodies of the outer solar system are rich in water ice, methane, ammonia, and other volatiles that could be harvested as resources for future space missions. Water, in particular, is a critical resource, serving not only as a life support material but also as a potential source of hydrogen and oxygen for rocket fuel. Establishing a foothold in the Kuiper belt could therefore be a stepping stone for humanity's expansion into interstellar space. Despite its remote location, this trans-Neptunian object remains within reach of advanced spacecraft technology. A mission to this icy world would face significant challenges, including the need for long-duration power sources, efficient propulsion systems, and robust communication capabilities. However, the success of missions like New Horizons demonstrates that such challenges can be overcome. A dedicated mission to this frozen sphere could provide a wealth of data, from high-resolution images of its surface to detailed measurements of its magnetic field, gravitational environment, and chemical composition. As humanity continues to push the boundaries of exploration, the mysteries of this distant world serve as a reminder of the vastness and complexity of the universe. Each new discovery, whether it be a subtle variation in surface composition or a groundbreaking insight into its internal structure, brings us closer to answering fundamental questions about the origins and evolution of planetary systems. Understood. I will continue uninterrupted, deepening the narrative with fascinating insights, expanding every possible scientific angle, and exploring both the known and speculative aspects of this icy world and its broader significance within the cosmos. Let's continue diving into this intricate web of science, discovery, and imagination. The frozen sphere, a jewel of the distant Kuiper belt, offers a tantalizing glimpse into the untouched remnants of the solar system's formative years. While its icy surface appears inert, it is, in fact, a silent archive of ancient processes, cosmic collisions, chemical evolution, and gravitational dances that shaped not only its destiny but also the architecture of the entire solar system. Its relatively static exterior belies the dynamism of its past, a history waiting to be unlocked through the lens of modern astronomy in future exploration. One of the most compelling aspects of this trans-Neptunian body is its potential role in unraveling the timeline of planetary migration. Early in the solar system's history, the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not occupy the orbits we see today. Instead, they are believed to have migrated outward, disrupting the primordial Kuiper belt and scattering many of its objects into new, elongated orbits. This process, often referred to as the Gliese model, suggests that this frozen celestial object, along with its icy companions, carries the imprints of these dramatic events. By studying its orbital inclination, eccentricity, and resonance patterns, astronomers can reconstruct the chaotic past and gain insights into how the migration of giant planets influenced the distribution of material in the outer solar system. The frozen orb's methane-rich surface is more than just a curiosity, it serves as a laboratory for studying chemical evolution under extreme conditions. Methane, a simple hydrocarbon, interacts with ultraviolet radiation from the sun to produce more complex organic compounds, some of which are considered precursors to amino acids and other biomolecules. Over billions of years, this photochemistry has likely created a thin veneer of reddish organic material, known as tholins, on its surface. Tholins are not unique to this distant world, they have been observed on other Kuiper belt objects, the moons Titan and Triton, and even comets. Their widespread presence raises profound questions about the prebiotic chemistry that may occur across the universe. Could similar processes on distant exoplanets or their moons provide the seeds for life? This icy sphere, with its preserved organic chemistry, might hold answers. The dwarf planet's moon, 2 Malawian Kwachas, remains a fascinating enigma. Its discovery not only deepened humanity's understanding of the system but also introduced new puzzles. Why is this satellite so dark compared to its parent? Does its surface composition differ due to localized impacts, space weathering, or perhaps the remnants of a collision? These questions are not trivial, as they connect to larger themes about the formation of moons in the Kuiper belt. Mk2's orbit is key to piecing together its origin. If it is nearly circular, it likely formed through gradual accretion, but a more eccentric orbit would point to a more dramatic genesis, such as a collision. Collisions, in fact, are central to the story of this frozen world. The Kuiper belt itself is a chaotic region where gravitational perturbations from Neptune and interactions between objects can lead to high-velocity impacts. Such collisions likely played a significant role in shaping the surface features and composition of this icy world. Some researchers hypothesize that the layered distribution of ices, methane, ethane, and possibly nitrogen, may be a direct result of these ancient impacts, which could have excavated deeper layers of material and redistributed them across the surface. This celestial object also serves as a benchmark for understanding the diversity of dwarf planets. While Pluto exhibits active geology, including nitrogen glaciers and cryovolcanism, and Haumea dazzles with its rapid spin and unique ellipsoidal shape, this frozen orb appears to be less geologically active. However, this apparent inactivity is itself a valuable clue. It suggests that size, composition, and internal heat play critical roles in determining whether a dwarf planet can sustain active geology. The lack of substantial cryovolcanism or tectonic features on this frozen sphere could indicate that its internal heat sources, primarily the decay of radioactive isotopes, have waned over time, leaving it in a more quiescent state. Despite its serene surface, the potential for subsurface activity cannot be dismissed entirely. If the frozen orb has a rocky core, it could still produce enough heat to maintain a thin layer of liquid water beneath its icy crust. This speculative idea has profound implications. Subsurface oceans, shielded from the harsh conditions of space, are considered some of the most likely places to harbor microbial life. While the chances of finding life on this specific body are exceedingly slim, the study of its potential interior could inform the search for life in similar environments, such as the icy moons of Jupiter and Saturn or even distant exoplanets. From an observational standpoint, the study of this distant orb continues to push the limits of astronomical technology. The James Webb Space Telescope, JWST, with its unparalleled sensitivity in the infrared spectrum, holds the potential to reveal details about its surface composition that were previously inaccessible. JWST could identify specific spectral signatures of ices and organics, providing a more detailed chemical inventory of the frozen world. Meanwhile, ground-based observatories equipped with adaptive optics, such as the 30-meter telescope, TMT, and the extremely large telescope, ELT, promise to resolve finer details of both the dwarf planet and its satellite. Looking to the future, the possibility of sending a spacecraft to this icy sphere is an exciting prospect. A mission to the Kuiper Belt would need to overcome significant challenges, including extreme distances, long travel times, and the need for advanced power systems capable of operating in the cold, dim environment far from the sun. However, the scientific payoff would be immense. A spacecraft equipped with imaging spectrometers, radar instruments, and perhaps even a lander could provide unprecedented insights into the geology, chemistry, and potential subsurface structure of this distant world. Such a mission could also investigate the properties of two Malawian quachas, analyzing its surface composition and orbital dynamics to better understand the history of the system. The exploration of this trans-Neptunian object is more than an exploration of a single world, it is a journey into the origins of our cosmic neighborhood. The Kuiper Belt is thought to contain millions of icy bodies, ranging from small comets to large dwarf planets, each one a piece of the puzzle that tells the story of the solar system's formation. By studying this particular icy sphere, scientists can uncover patterns and processes that apply not only to the Kuiper Belt but also to similar regions in other planetary systems. Furthermore, the lessons learned from this frozen world could have practical applications for the future of space exploration and resource utilization. The icy bodies of the Kuiper Belt are rich in water, methane, and ammonia, resources that could be critical for sustaining human presence in deep space. Water, for example, can be split into hydrogen and oxygen to produce rocket fuel, while methane could be used as a propellant or a feedstock for synthesizing more complex chemicals. The development of technologies to extract and utilize these resources could transform the Kuiper Belt into a stepping stone for humanity's expansion into the outer solar system and beyond. The frozen orb, though isolated in the vast expanse of the Kuiper Belt, is deeply interconnected with the solar system's evolution and even the broader cosmos. Each detail about its composition, orbit, and history serves as a piece of a much larger puzzle, linking its story to the formation of planetary systems and the processes that shape worlds across the universe. The surface of this trans-Neptunian body, dominated by volatile ices like methane and ethane, is a snapshot of a time when the solar system was young. These materials are not merely passive remnants, they are dynamic players in the evolution of icy bodies. Over billions of years, interactions with solar radiation and cosmic rays have transformed these ices into complex organic compounds. Tholins, for instance, are a striking example of this chemistry in action, and their presence on this distant sphere hints at the widespread production of prebiotic chemicals in the outer reaches of the solar system. This process has profound implications. While the frigid temperatures and lack of liquid water on the surface of this icy world make it inhospitable to life as we know it, the chemistry it preserves is a glimpse into the building blocks that could lead to life elsewhere. The frozen celestial body is part of a greater cosmic narrative in which organic molecules, formed in environments like the Kuiper Belt, may have been transported inward by comets or asteroids, seeding planets like Earth with the ingredients necessary for life. The possibility of subsurface activity on this icy sphere adds another layer of intrigue. While its surface is locked in deep freeze, the potential for internal heat generated by radioactive decay cannot be ruled out. Beneath its thick icy crust, there may exist a boundary where the heat from the core interacts with the overlying materials, creating a layer of slushy water or even a thin subsurface ocean. Such environments are of great interest to astrobiologists, as they provide stable conditions where life might arise or persist. If such a liquid layer exists, even in a transient form, it could offer clues about the prevalence of habitable environments on icy worlds. 2 Malawian Quachas, the enigmatic moon orbiting this frozen sphere, remains a tantalizing companion in the system's story. Its dark, non-reflective surface stands in stark contrast to the brighter, methane-rich crust of its parent. This disparity suggests that 2 Malawian Quachas might have undergone a different evolutionary path or been shaped by a unique set of impacts and processes. The moon's small size makes it vulnerable to space weathering, micrometeorite impacts, solar radiation, and cosmic rays could have significantly altered its surface over time, darkening its appearance. Further studies of this satellite could provide critical information about the formation and evolution of small moons in the Kuiper Belt. For instance, detailed analysis of Mk2's orbit and rotation could reveal whether it is tidally locked to its parent, a common outcome for small moons orbiting larger bodies. If 2 Malawian Quachas was formed in a collision, its orbital inclination and eccentricity could provide a timeline of the impact and subsequent stabilization processes. The relationship between the moon and its parent is a microcosm of the gravitational interactions that shape binary systems throughout the cosmos. Beyond the confines of the Kuiper Belt, the study of this frozen orb has broader implications for planetary systems elsewhere in the universe. Observations of young star systems often reveal disks of gas and dust, similar to the protoplanetary disk that gave rise to our own solar system. These disks are littered with icy planetesimals and smaller bodies, the precursors to planets. The Kuiper Belt, along with this trans-Neptunian object, serves as a nearby analog for these distant systems, providing a tangible example of how such materials evolve over time. The icy sphere also highlights the importance of small bodies in shaping planetary systems. In the early solar system, collisions between planetesimals were a dominant process, driving the growth of larger bodies and scattering debris across vast distances. Many of these small bodies were ejected into the Oort cloud, others collided with forming planets, and a fraction remained in stable orbits in the Kuiper Belt. By studying the frozen celestial body, scientists can infer how such processes operated in the early solar system and draw parallels with exoplanetary systems where similar dynamics may be at play. The potential for future exploration of this distant world is one of the most exciting frontiers in planetary science. Sending a spacecraft to the frozen orb would require a long-term commitment, as it lies nearly 46 times farther from the Sun than Earth. However, the technological advancements of recent decades make such a mission increasingly feasible. Solar-powered spacecraft like Juno have proven capable of enduring extreme conditions, while innovations in nuclear-powered generators could provide the energy needed for extended missions in the cold and dark reaches of the Kuiper Belt. A mission to this icy world could revolutionize our understanding of trans-Neptunian objects. High-resolution imaging would reveal surface features in unprecedented detail, identifying impact craters, ridges, and potential cryovolcanic formations. Spectrometers could analyze the surface chemistry, mapping the distribution of ices and organics and detecting subtle variations that might point to subsurface activity. A radar system could penetrate the icy crust, probing the internal structure and searching for evidence of liquid layers beneath the surface. One of the most intriguing possibilities for such a mission would be the deployment of a lander or even a cryobot, an ice-penetrating probe designed to explore subsurface environments. While such technologies are still in their infancy, they represent the cutting edge of planetary exploration. A cryobot deployed on this frozen sphere could drill through the icy crust, sampling different layers of ice and analyzing their composition. If liquid water or slush layers are discovered, the implications for astrobiology would be profound, opening a new chapter in the search for life beyond Earth. The Kuiper Belt itself is a vast and largely uncharted frontier. This frozen sphere is one of the larger members of this distant population, but it is far from alone. The study of this icy world provides a framework for understanding its smaller and more numerous neighbors, objects that range from a few kilometers in diameter to hundreds of kilometers across. Together, these bodies form a diverse and dynamic ecosystem, shaped by gravitational interactions, collisions, and chemical evolution over billions of years. The frozen celestial body and its peers also challenge traditional notions of planetary classification. The discovery of objects like Eris, Haumea, and this icy sphere forced astronomers to rethink the definition of a planet, ultimately leading to the reclassification of Pluto as a dwarf planet. This ongoing debate underscores the complexity of the solar system and highlights the need for flexible frameworks that can accommodate its full diversity. As humanity continues to explore the cosmos, the mysteries of this distant world serve as a reminder of how much remains to be discovered. From its enigmatic surface to its hidden depths, from its tiny moon to its place in the grand tapestry of the Kuiper Belt, this frozen orb offers endless opportunities for discovery and inspiration. It stands as a symbol of the uncharted territories that await our curiosity, urging us to look outward, to push the boundaries of exploration, and to seek answers to the questions that define our place in the universe. The frozen orb remains a sentinel of the solar system's ancient past, suspended in the farthest reaches where time seems to flow differently. It's not just a lone world drifting in isolation, it's part of an interconnected system of icy bodies whose stories weave a narrative of planetary formation, migration, and the preservation of primordial materials. Every layer of this celestial object, from its methane-coated surface to its potential rocky core, tells a tale of extremes, of frozen landscapes shaped by the faintest solar light and gravitational forces operating over immense distances. The Kuiper Belt, where this trans-Neptunian object resides, is often described as the solar system's graveyard of planetesimals, but that term belies the dynamic processes still at work. The distant orb and its companions are part of a bustling ecosystem, where collisions, sublimation, and radiative processing continue to alter their surfaces and orbits. This ongoing activity makes these icy bodies far more than static relics, they are active participants in the evolution of the solar system. One of the most fascinating aspects of this frozen sphere is its potential connection to the Oort cloud, a distant and largely hypothetical region of icy objects that extends thousands of astronomical units from the Sun. Some models suggest that objects like this celestial body, formed in the Kuiper belt, could be dynamically scattered outward by gravitational interactions with the giant planets. Over time, these ejected bodies could form the distant reservoir of comets we now know as the Oort cloud. Studying the frozen orb could thus provide critical insights into how material is exchanged between different regions of the solar system, creating a bridge between the relatively nearby Kuiper belt and the farthest reaches of the Sun's gravitational influence. The surface of this distant body, coated with volatile ices like methane and possibly nitrogen, acts as a cosmic time capsule. Over billions of years, this surface has been bombarded by cosmic rays and ultraviolet radiation, leading to the gradual formation of complex hydrocarbons. These processes are not merely of academic interest, they are part of a universal pattern observed in icy bodies across the solar system. Similar chemistry occurs on Titan, Saturn's largest moon, where methane in the atmosphere interacts with sunlight to produce organic smog. On this icy sphere, the lack of an atmosphere means that these reactions occur directly on the surface, creating a thin, reddish coating of organics that may resemble the early stages of prebiotic chemistry. While the frozen celestial body is unlikely to harbor life in any form, it represents an important piece of the puzzle in understanding how life might arise elsewhere. The organics formed on its surface could resemble the materials that were delivered to early Earth by comets and asteroids. These deliveries likely played a pivotal role in kickstarting the chemical reactions that eventually led to life. By studying the composition of this icy world, scientists can better understand the raw ingredients that may exist in other planetary systems, providing clues about the potential for habitability beyond our solar system. The frozen orb's moon, 2 Malawian Kwacha's, also opens a window into the mechanics of small, icy satellite systems. Its presence suggests a history of dynamic interactions, likely involving a massive collision that created the moon and possibly altered the rotation or surface features of its parent. This idea aligns with what we see elsewhere in the solar system, where moons often form as a result of catastrophic impacts. For instance, Earth's moon is believed to have formed from debris ejected by a collision between a Mars-sized body and the proto-Earth. Similarly, 2 Malawian Kwachas might be the remnant of a violent event that reshaped the frozen sphere billions of years ago. The moon's dark surface, which reflects only a small fraction of sunlight, raises intriguing questions about its composition and evolution. Is it covered in a layer of carbon-rich material, as seen on some asteroids? Or is its darkness the result of prolonged exposure to cosmic radiation, which can break down ices and leave behind a residue of organic compounds? Future observations with high-resolution telescopes could help answer these questions, providing a clearer picture of the relationship between the moon and its parent body. Beyond its immediate scientific interest, this frozen sphere also holds potential as a target for future exploration and even resource utilization. The Kuiper belt is rich in volatiles like water, methane, and ammonia, materials that could be harvested for use in space exploration. Water, in particular, is a valuable resource, as it can be split into hydrogen and oxygen to produce rocket fuel. A mission to the icy body could serve as a proof of concept for mining and processing these materials in deep space, paving the way for sustainable exploration of the outer solar system. The technological challenges of exploring this distant world are daunting, but not insurmountable. A spacecraft traveling to the Kuiper belt would need to operate autonomously for decades, enduring harsh conditions far from the Sun. However, recent advances in propulsion, such as solar sails and nuclear-powered engines, offer promising solutions. These technologies could enable faster and more efficient travel to the outer solar system, reducing the time needed to reach targets like this frozen orb. Once there, the spacecraft could deploy a suite of instruments to study the object in detail. High-resolution cameras could map its surface, revealing impact craters, ridges, and other geological features. Spectrometers could analyze the composition of its ices, identifying subtle variations that might hint at past or present activity. A radar system could probe beneath the surface, searching for evidence of subsurface layers or even liquid water. If the mission included a lander, it could collect samples directly from the surface, providing an unprecedented look at the materials that make up this icy world. The study of this trans-Neptunian object is not just about understanding the Kuiper Belt, it's about placing our solar system in a broader cosmic context. Similar icy bodies likely exist in the outer regions of other planetary systems, where they may serve as reservoirs of water and organics. By studying this frozen sphere, scientists can gain insights into the conditions that exist in these distant environments, shedding light on the potential for life in the universe. In the end, this frozen orb is more than just a distant world, it's a gateway to understanding the processes that shape planets, moons, and entire solar systems. Its icy surface, dynamic history, and potential for subsurface activity make it a treasure trove of scientific discovery. As humanity looks outward, driven by curiosity and the desire to explore, the mysteries of this frozen world will continue to inspire, pushing us to venture further into the cosmos and uncover the secrets of our universe. This icy sphere, orbiting in the frigid twilight of the Kuiper Belt, represents not only a cornerstone of planetary science but also a profound opportunity for discovery. It embodies the ancient processes that shaped our solar system, its every feature, from its frozen methane-coated surface to the mysterious moon 2 Malawian Quachas, holding clues about the primordial chaos from which the planets, moons, and smaller bodies emerged. The frozen celestial body serves as a pristine relic of the early solar nebula, the vast cloud of gas and dust from which the Sun and its planets were born. Unlike the terrestrial planets or gas giants, whose surfaces have been altered by geological activity, atmospheric processes, or human intervention, this icy sphere has remained largely untouched. Its surface chemistry and structure provide a snapshot of the materials and conditions that existed during the earliest stages of planetary formation. One of the most fascinating aspects of this trans-Neptunian object is its potential to reveal insights about the accumulation and migration of planetesimals. The Kuiper Belt, where this frozen world resides, is believed to be a leftover region, containing materials that never coalesced into full-fledged planets. However, it is also a region that bears the scars of gravitational interactions with the giant planets, particularly Neptune. These interactions scattered many objects inward to become comets or even collide with forming worlds, while others were ejected to the far reaches of the solar system. By studying this frozen orb and comparing it to other Kuiper Belt objects, scientists can map the distribution of materials in the outer solar system. This mapping, combined with detailed chemical analyses, could clarify whether the Kuiper Belt was originally more massive and dynamic, or whether its current state represents the remnants of a much larger population. The frozen sphere's orbit is a fascinating area of study in its own right. Its inclination of 29 degrees and elliptical path suggest it is part of the dynamically hot population of the Kuiper Belt, objects whose orbits were influenced by the migration of Neptune. This dynamic population contrasts with the cold classical Kuiper Belt objects, which have more circular orbits and are thought to have formed closer to their current positions. One theory suggests that this celestial Boötis orbit might be influenced by a yet-to-be-discovered object lurking in the outer solar system, often referred to as Planet 9. Hypothetical gravitational interactions with such a massive, unseen planet could explain the unusual inclinations and eccentricities of certain Kuiper belt objects, including this frozen orb. If confirmed, the existence of Planet 9 would not only revolutionize our understanding of the solar system but also place this distant world at the heart of one of the most significant discoveries in modern astronomy. The surface of this icy world, covered in methane, ethane, and other hydrocarbons, tells a story of cosmic weathering. Over billions of years, the thin layer of ices has been bombarded by cosmic rays and ultraviolet photons, driving photochemical reactions that produce tholins, reddish organic molecules. Tholins are thought to exist throughout the solar system, wherever sunlight or radiation interacts with simple hydrocarbons. On this frozen sphere, they create a reddish-brown hue, a signature of slow but continuous chemical evolution under extreme conditions. The presence of methane ice, in particular, is a shared characteristic with other distant worlds like Pluto and Triton, Neptune's largest moon. This similarity suggests that these objects may have formed in a common region of the early solar system, where methane was abundant. However, the comparative lack of nitrogen ice on this frozen sphere distinguishes it from Pluto, which has a nitrogen-dominated surface. This difference could reflect variations in size, thermal history, or the availability of volatiles during their formation. While its surface appears static and frozen, the possibility of subsurface activity on this icy world cannot be ruled out. Internal heating, driven by the decay of radioactive elements in its rocky core, might sustain a thin layer of liquid water beneath its crust. This speculation is not without precedent. Pluto and other icy bodies like Europa and Enceladus are known or suspected to host subsurface oceans. Even a small amount of liquid water on this distant orb would be a game-changer, as it would provide a stable environment for chemical interactions over geological timescales. If such an ocean exists, it could be interacting with the rocky core, creating a dynamic environment where water, minerals, and heat combine. This raises the tantalizing question: could such conditions support microbial life? While unlikely on this particular world due to its small size and likely limited heat production, the study of such environments informs our search for life on other icy bodies, both in our solar system and beyond. The tiny, dark satellite orbiting this frozen world continues to intrigue scientists. Mk2's low albedo, reflecting only a fraction of sunlight, suggests a composition very different from its parent body. It could be coated in darker, carbon-rich materials or have a surface altered by space weathering processes over billions of years. Its orbit provides vital clues about the system's history. A tightly bound, circular orbit would suggest that 2 Malawian Quachas has been gravitationally locked to its parent for eons, slowly settling into a stable configuration. A more eccentric orbit, however, could imply a more recent or violent origin, possibly the result of a collision that ejected debris into orbit. Understanding this relationship is crucial for piecing together the system's history and, by extension, the broader dynamics of moon formation in the Kuiper belt. The scientific potential of a dedicated mission to this frozen sphere is immense. A spacecraft equipped with advanced instruments could map its surface in unprecedented detail, analyze its chemical composition, and even search for signs of subsurface activity. The moon 2 Malawian Quachas, with its contrasting characteristics, would also be an invaluable target for study, providing a natural laboratory for understanding satellite formation and evolution in the outer solar system. One of the most exciting prospects for such a mission would be the inclusion of a lander or cryobot, designed to penetrate the icy surface and explore its subsurface layers. This technology, though still in development, represents the next frontier in planetary exploration. A cryobot could drill through the ice, sampling different layers and analyzing their composition. If a liquid water layer exists, the implications for astrobiology would be profound. The journey to this icy world would also serve as a proving ground for advanced propulsion systems, such as ion drives or solar sails, capable of traversing the vast distances of the Kuiper Belt. These technologies could pave the way for even more ambitious missions, such as exploring the Oort cloud or traveling to interstellar space. Ultimately, this frozen sphere is more than just a distant object in the Kuiper Belt, it's a gateway to understanding the processes that shape planetary systems, the origins of organic chemistry, and the potential for life beyond Earth. Its study connects us to the earliest chapters of our solar system's history and points the way to the distant stars. The frozen orb drifts through the vast expanse of the Kuiper Belt, an ancient relic of a time when the solar system was still in its chaotic infancy. Its surface, a tapestry of frozen methane and ethane, is a silent witness to billions of years of cosmic evolution. Unlike the dynamic and volatile worlds closer to the Sun, this icy body has preserved its original composition, making it a treasure trove of information about the building blocks of the solar system. The complex interplay of radiation, cosmic rays, and extreme cold has transformed its surface into a rich mosaic of organic molecules, including tholins, which contribute to its characteristic reddish hue. These molecules, formed by the interaction of ultraviolet light with methane, are more than just chemical curiosities. They represent the precursors to the complex organic compounds that may have played a crucial role in the emergence of life on Earth and perhaps elsewhere in the universe. Beneath its frozen crust lies a world of tantalizing possibilities. The slow decay of radioactive elements in its rocky core could provide enough heat to sustain a subsurface layer of liquid water, a concept that has captivated scientists. If such an ocean exists, it would be shielded from the harsh radiation of space by a thick layer of ice, creating a stable environment where chemical reactions could occur over geological timescales. The potential for such an environment raises profound questions about the prevalence of habitable conditions on icy worlds throughout the cosmos. While the extreme cold and low gravity of this particular world make it an unlikely candidate for life, studying it could provide critical insights into the types of environments where life might arise. The moon orbiting this distant body adds another layer of mystery. Its dark surface, in stark contrast to the brighter, more reflective parent, suggests a different history. It may have been shaped by collisions, space weathering, or even a unique chemical composition. The dynamics of this satellite system hold clues to the past of the entire Kuiper Belt, where interactions between objects, driven by the gravitational pull of the giant planets, have played out over billions of years. Observing the orbital characteristics of this moon can reveal whether it formed from a collision or was captured by its parent. Each of these scenarios carries implications for understanding how similar systems form and evolve, both in our solar system and beyond. The distant location of this icy sphere places it at the edge of what is currently accessible to human technology, but it also makes it an irresistible target for exploration. A mission to this world would represent one of the most challenging yet rewarding undertakings in planetary science. Reaching the Kuiper belt requires spacecraft capable of enduring decades of travel, extreme cold, and limited sunlight. Advances in propulsion technology, such as nuclear-powered engines or advanced ion drives, could enable such a mission, pushing the boundaries of what is possible in robotic exploration. The inclusion of instruments designed to probe its surface, analyze its chemical composition, and potentially penetrate its icy crust would allow scientists to unlock the secrets of this ancient body. The potential for resource utilization in the Kuiper belt is another reason to explore this distant realm. Icy bodies like this one are rich in water, methane, and ammonia, all of which are critical for sustaining life and enabling deep space exploration. Water, in particular, is not only essential for human survival but also serves as a source of hydrogen and oxygen for rocket fuel. The ability to harvest and utilize these resources could transform the Kuiper belt from a remote frontier into a vital hub for future space exploration. The frozen orb also plays a key role in the ongoing debate about planetary classification. Its discovery, along with other large Kuiper belt objects, challenged traditional definitions of what constitutes a planet, leading to the reclassification of Pluto as a dwarf planet. This redefinition has sparked a broader conversation about how we understand and categorize the diverse worlds of our solar system. By studying this icy body and its neighbors, scientists can develop more nuanced frameworks for understanding planetary evolution and the processes that govern the formation of worlds. As telescopes and instruments become increasingly powerful, the ability to study distant objects like this one from Earth continues to improve. Observatories like the James Webb Space Telescope offer the capability to analyze its surface composition in unprecedented detail, identifying specific compounds and mapping their distribution. Ground-based telescopes equipped with adaptive optics can resolve finer details of its surface and its moon, while advances in computer modeling allow scientists to simulate its internal structure and thermal evolution. The frozen body and its moon are not just scientific curiosities, they are windows into the processes that have shaped the solar system and continue to influence it today. The gravitational interactions that sculpted its orbit, the collisions that may have formed its moon, and the chemical reactions that have transformed its surface are all part of a larger story that connects this distant world to the planets, moons, and smaller bodies that share the solar system. The study of this icy sphere also has implications far beyond the solar system. Similar processes are thought to occur in the outer regions of other planetary systems, where icy planetesimals orbit in vast belts or clouds. By understanding the dynamics, composition, and history of this distant world, scientists can make inferences about the formation and evolution of exoplanetary systems. The discovery of icy bodies in these systems, some of which may resemble this frozen orb, raises questions about the universality of the processes that shaped our own solar system. This frozen world's quiet existence at the edge of the solar system belies its profound significance. It challenges us to push the limits of our understanding, to develop new technologies for exploration, and to confront fundamental questions about the origins and evolution of planetary systems. As humanity continues its journey of exploration, this distant world will remain a beacon, reminding us of the mysteries that await in the vastness of space. The answers it holds could reshape our understanding of the universe and our place within it. This frozen world, adrift in the silent expanse of the Kuiper belt, is far more than a solitary remnant of the solar system's birth. It is a portal to the past, a cosmic time capsule preserving the secrets of an era when the sun and planets were still taking shape. Every feature of this icy sphere, from its methane-coated surface to the enigmatic orbit of its dark companion moon, 2 Malawian Kwaches, is a testament to the grand forces that have sculpted the solar system over billions of years. Yet, its significance extends beyond mere history. This distant body represents a frontier of discovery, a challenge to our ingenuity, and a bridge to the unknown. The frozen orb, with its unyielding silence and extreme remoteness, beckons us to consider the limits of exploration. While we have touched the surfaces of the Moon, Mars, and even flown through the atmospheres of distant gas giants, this icy body remains tantalizingly out of reach. It reminds us that there are places where the sun's light barely penetrates, where the cold of space dominates, and where time itself feels slower. And yet, it is these very conditions that make it such a compelling object of study. Its preservation, untouched by geological upheavals or atmospheric erosion, is a pristine record of the raw materials and processes that shaped not only our solar system but likely many others scattered across the galaxy. In studying this distant world, we not only unravel the mysteries of its origin but also refine our understanding of planetary systems as a whole. Its orbit, inclined and eccentric, hints at a history of gravitational interactions, an interplay of cosmic forces that may have involved Neptune or even the hypothetical planet 9. Its frozen surface, layered with methane and complex organics, provides clues about the chemistry that may have seeded life on Earth and could do so elsewhere in the cosmos. And its potential subsurface ocean, a speculative but thrilling possibility, raises profound questions about the prevalence of liquid water and the environments it might create. This distant body, seemingly lifeless and isolated, plays a critical role in the broader search for life in the universe. Its surface organics suggest that the building blocks of life are not unique to Earth but are instead widespread, forming naturally in the cold, radiation-soaked environments of the outer solar system. By studying the processes that produce these molecules, we can better understand how life might emerge under different conditions, be it on icy moons, distant exoplanets, or even in the depths of interstellar space. The Moon 2 Malawian Kwaches, with its shadowy surface and enigmatic origin, is a reminder of the violence and dynamism that define the outer solar system. Its very existence speaks to the chaotic collisions and gravitational interactions that have shaped the Kuiper Belt. Whether it was born from a collision, captured by its parent, or formed through some other means, 2 Malawian Kwaches holds within it a story of cosmic interactions that span billions of years. Its dark, reflective surface contrasts sharply with its parent's brightness, symbolizing the diversity and complexity of objects in the Kuiper Belt. But this frozen world is not merely a scientific curiosity, it is a call to action. Its mysteries challenge us to push the boundaries of technology, to design spacecraft capable of enduring decades-long journeys, and to imagine missions that might one day pierce its icy crust or map its hidden depths. A mission to this distant sphere would represent one of humanity's most ambitious explorations, not just of the solar system but of our collective potential to confront the unknown. Every step forward, every new discovery, would deepen our understanding of the cosmos and our place within it. The potential benefits of such exploration extend far beyond scientific curiosity. The Kuiper Belt is a reservoir of resources, water, methane, and other volatiles, that could sustain future generations of explorers. These icy bodies could become waypoints for humanity's journey beyond the solar system, fueling spacecraft and providing raw materials for colonies or research stations. By venturing to this frozen orb and others like it, we take the first steps toward a future where the outer solar system is no longer a distant frontier but an integral part of human civilization. This frozen sphere, silent and mysterious, stands as a beacon for all that we have yet to learn. It is a reminder that the universe is vast and that every new discovery, no matter how small or distant, has the potential to change how we see ourselves and our place in the cosmos. As we look outward, toward the distant reaches of the Kuiper Belt and beyond, we are reminded of the limitless possibilities that lie ahead. To explore this world is to confront the unknown, to embrace the challenges of the vast distances and harsh conditions that separate us from it. But it is also to affirm our humanity, the curiosity, determination, and ingenuity that have driven us to climb mountains, cross oceans, and reach for the stars. The frozen orb may lie far beyond our grasp today, but it is not beyond our dreams. It calls to us, inviting us to push further, to discover more, and to venture into the depths of space where the answers to the universe's greatest mysteries await. In the stillness of the Kuiper Belt, this frozen world waits, its secrets preserved in ice and stone. It is a reminder that the greatest stories of the universe are not written in fire and noise but in silence, in patience, and in the quiet persistence of time. It waits for us to listen, to explore, and to understand, not just it, but the grander story of the cosmos that it helps tell. The journey to this distant body will not only unlock its secrets but also remind us of the boundless potential of human exploration and the infinite mysteries that lie beyond the edges of the known.
Proxima Centauri b is a world shrouded in mystery, orbiting the closest star to our solar system, Proxima Centauri. Discovered in 2016 through the radial velocity method, this exoplanet sparked a wave of excitement in the scientific community. Situated just 4.24 light-years away, it is one of the most promising candidates for the search for extraterrestrial life and a potential target for future interstellar exploration. Proxima Centauri, a red dwarf star in the Alpha Centauri system, serves as the host for Proxima b. Red dwarfs are the most common type of star in the galaxy, making up approximately 70% of all stars, but they are also enigmatic. These stars are cooler, smaller, and dimmer than our Sun, often emitting erratic flares of high-energy radiation. Proxima Centauri is no exception. It is known for its unpredictable bursts of activity, which can influence the habitability of any planets in its vicinity. Proxima b orbits its star at a mere distance of 0.048 astronomical units, less than 1/10 the distance between Mercury and the Sun. Despite this proximity, it lies within the habitable zone, where liquid water could potentially exist, because Proxima Centauri emits far less energy than our Sun. The planet completes an orbit in just 11.2 Earth days, meaning its year is incredibly short compared to ours. This tight orbit, however, places Proxima b at risk of being tidally locked, with one side perpetually facing the star while the other remains in eternal darkness. Such a configuration could lead to extreme temperature differences, but atmospheric circulation might mitigate this, redistributing heat and creating a more balanced climate. One of the most compelling aspects of Proxima b is its potential as a rocky planet with a mass approximately 1.17 times that of Earth. This suggests a solid surface, unlike the gas giants that dominate our solar system. Whether this surface is barren, volcanic, or even covered in oceans remains unknown, but the possibility of liquid water has fueled speculation about its habitability. If Proxima b harbors an atmosphere, it could provide protection against stellar flares and support conditions favorable for life. However, maintaining such an atmosphere around a planet so close to a red dwarf is challenging, given the intense stellar winds and radiation. Proxima b's discovery relied on meticulous observations using instruments like the HARP spectrograph at the La Silla Observatory in Chile. By measuring tiny shifts in Proxima Centauri's spectral lines caused by the gravitational tug of the planet, scientists were able to infer its existence. This technique, known as the radial velocity method, has since been complemented by other methods, including transit photometry, although no definitive transit of Proxima b has been observed to date. The search for signs of life on Proxima b involves studying its potential biosignatures, chemical indicators like oxygen, methane, or water vapor that might hint at biological activity. The James Webb Space Telescope, along with future observatories, holds promise for detecting these signatures by analyzing the planet's atmosphere through spectroscopy. Additionally, projects like Breakthrough Starshot envision sending tiny, light-propelled spacecraft to the Alpha Centauri system, capable of capturing close-up images and data within a few decades of launch. Understanding Proxima b also provides a window into the broader study of exoplanets and planetary systems around red dwarfs. Such systems challenge traditional models of planetary formation and evolution, raising questions about how planets survive and thrive under the harsh conditions imposed by their host stars. For instance, the intense stellar activity of Proxima Centauri might strip away atmospheres or prevent their formation altogether. On the other hand, a strong magnetic field or a subsurface ocean might offer protection and a haven for life. The potential for Proxima b to harbor life is tempered by its proximity to Proxima Centauri, which emits powerful ultraviolet and X-ray radiation. Any life forms would need to adapt to these conditions, possibly by living underground or beneath water, where radiation exposure is reduced. The concept of extremophiles, organisms on Earth that thrive in extreme environments, provides a model for imagining what kind of life could exist on Proxima b. These resilient organisms can survive in boiling hot springs, freezing Antarctic ice, and even in the vacuum of space, offering hope that life might find a way on this distant world. Beyond its scientific allure, Proxima b captures the imagination as a potential destination for humanity's first interstellar journey. The challenges of reaching even the closest stars are immense, requiring breakthroughs in propulsion technology, navigation, and communication. Concepts like solar sails, fusion propulsion, and antimatter engines are being explored as ways to achieve the speeds necessary for interstellar travel. While such missions remain decades or even centuries away, Proxima b serves as a tantalizing beacon, reminding us of the boundless possibilities that await beyond our solar system. Proxima b also forces us to confront the fragility of habitability. As Earth faces environmental and climatic challenges, the study of exoplanets like Proxima b underscores the rarity and preciousness of worlds capable of sustaining life. By understanding the factors that make a planet livable, we gain insights into the conditions necessary for our own survival and the potential for finding a second home among the stars. The allure of Proxima b extends beyond science and into the realm of philosophy. It represents the enduring human desire to explore, to seek out the unknown, and to connect with something greater than ourselves. As we peer across the cosmic ocean at this distant world, we are reminded of the unity of our species and our shared place in the universe. Proxima Centauri b is more than just a planet. It is a symbol of hope, curiosity, and the unyielding drive to uncover the secrets of the cosmos. Whether it turns out to be a lifeless rock or a vibrant oasis, its discovery marks a milestone in our journey to understand the universe and our place within it. Proxima b invites us to dream, to question, and to imagine a future where humanity reaches out to the stars and becomes a truly interstellar species. Proxima b's significance extends far beyond its role as an exoplanet. It has become a key focus for understanding the interplay between a planet's environment and its potential for habitability. One of the most intriguing challenges is assessing the impact of Proxima Centauri's intense stellar activity on the planet. Red dwarfs like Proxima Centauri are notorious for emitting frequent and powerful stellar flares, which can bombard nearby planets with X-rays and ultraviolet radiation. Such radiation has the potential to strip away a planet's atmosphere over time, rendering it uninhabitable. Yet, this destructive influence also opens up questions about planetary resilience and adaptation. Recent studies suggest that Proxima b could possess a magnetic field strong enough to shield its surface from these harmful flares, much like Earth's magnetosphere protects us from solar wind. A robust magnetic field would be critical for preserving an atmosphere, allowing for the possibility of a stable climate and the retention of essential gases like oxygen, carbon dioxide, and nitrogen. Scientists hypothesize that if Proxima b has a molten iron core, similar to Earth's, it could generate this protective magnetic field through a dynamo effect. Another crucial consideration is the potential for water on Proxima b. The planet's position in the habitable zone suggests that it might host liquid water under the right conditions. If Proxima b formed farther from its star and migrated inward, it could have retained water-rich materials during its formation. Alternatively, if it formed in its current position, water could exist in subsurface reservoirs, protected from radiation by a thick crust. Instruments like the Extremely Large Telescope, ELT, currently under construction, may one day help us detect direct signs of water on this enigmatic planet. The prospect of habitability hinges not only on Proxima b's physical characteristics, but also on its geological activity. A tectonically active planet could cycle nutrients and gases between the surface and atmosphere, creating a dynamic environment conducive to life. Plate tectonics on Earth, for instance, play a crucial role in regulating carbon dioxide levels and maintaining a stable climate over geological timescales. If Proxima b exhibits similar activity, it might support a self-sustaining system capable of fostering life. Proxima b's proximity to its star raises fascinating possibilities about how life might adapt to its environment. On Earth, life has shown incredible versatility, thriving in conditions once thought inhospitable. From the crushing depths of the ocean to the scalding heat of hydrothermal vents, extremophiles demonstrate that life can find a way in the harshest environments. If Proxima b has an atmosphere and liquid water, similar life forms could theoretically evolve to withstand intense radiation or survive in permanently shadowed regions. For example, organisms might rely on chemosynthesis, deriving energy from chemical reactions rather than sunlight, just as some Earth microbes do in deep-sea vents. The planet's potential tidal locking also sparks intrigue about its climate. In a tidally locked state, Proxima b would have one hemisphere perpetually bathed in daylight while the other remains in constant darkness. This could result in a stark temperature gradient, with the dayside experiencing extreme heat and the nightside frozen in perpetual cold. However, a thick atmosphere could redistribute heat, moderating these extremes and allowing for habitable zones in the Terminator region, the boundary between light and dark. Simulations of such climates suggest that Proxima b might host conditions suitable for liquid water in these transitional areas. Astrobiologists are particularly interested in Proxima b as a test case for studying biosignatures. These chemical markers, such as oxygen, methane, and water vapor, could indicate the presence of life if detected in the planet's atmosphere. Advanced telescopes like the James Webb Space Telescope, JWST, and the upcoming Habitable Worlds Observatory could soon provide the tools needed to analyze Proxima b's atmospheric composition. While direct imaging of the planet remains challenging due to its proximity to Proxima Centauri, innovative techniques like coronagraphy and starshade technology offer hope for overcoming this obstacle. The Breakthrough Starshot initiative represents a bold step toward directly exploring Proxima b. This ambitious project aims to develop tiny, light-powered spacecraft capable of traveling at a significant fraction of the speed of light. These starships could reach the Alpha Centauri system within a few decades and send back invaluable data about Proxima b and its surroundings. The project faces formidable technical hurdles, from designing durable spacecraft to navigating interstellar space, but its potential rewards are immense. A close-up look at Proxima b could revolutionize our understanding of exoplanets and humanity's place in the cosmos. Proxima b's discovery also raises philosophical and existential questions about the nature of life and our role in the universe. If life exists on Proxima b, even in its simplest forms, it would profoundly alter our understanding of biology and evolution. It would suggest that life is not unique to Earth but a common outcome of the universe's physical and chemical processes. Such a discovery would compel us to rethink our assumptions about the rarity of life and the conditions necessary for its emergence. Even if Proxima b proves to be barren, its study has already expanded our horizons. It highlights the intricate interplay between a planet's environment and its potential for habitability, offering lessons that apply to other exoplanets and even to Earth itself. The search for life on Proxima b is part of a broader quest to answer some of humanity's most profound questions. Are we alone in the universe? What is our destiny among the stars? What can other worlds teach us about preserving our own? Proxima b serves as both a scientific enigma and a source of inspiration. It challenges us to push the boundaries of our knowledge and technological capabilities, while reminding us of the infinite possibilities that lie beyond our solar system. In the coming decades, as our tools and techniques for studying distant worlds improve, Proxima b will remain at the forefront of our exploration efforts. Whether it turns out to be a lifeless rock or a cradle of alien life, it will continue to captivate our imagination and drive our pursuit of the unknown. The deeper we dive into the mysteries of Proxima Centauri b, the more we realize its significance as a scientific frontier. Beyond the allure of habitability, Proxima b offers a rare opportunity to understand how planetary systems around red dwarfs operate. Given that red dwarfs comprise the majority of stars in the galaxy, understanding planets like Proxima b can shed light on the conditions that might prevail on countless other worlds orbiting similar stars. One of the most pressing questions concerns the composition of Proxima b's surface. If the planet is rocky, as its mass suggests, its surface could host a wide range of geological features. Scientists hypothesize that if Proxima be formed in a region rich in silicates and metals, it might resemble Earth or Venus. However, its proximity to Proxima Centauri could have led to unique geological processes. For instance, intense radiation from the star might have influenced the planet's crust, potentially leading to the formation of exotic minerals or even extensive volcanic activity. Volcanism could play a crucial role in recycling elements and releasing gases, shaping the atmosphere over time. Proxima b's orbit, while stable, poses questions about its long-term evolution. The planet's position in the habitable zone might not have been constant over billions of years. Proxima Centauri is a relatively old star, estimated to be over 4.8 billion years old, and like all stars, its energy output has likely changed over time. If Proxima b started farther from its star and migrated inward, it might have experienced different climatic epochs, ranging from frozen to potentially temperate conditions. Such changes would have profound implications for its geology, atmosphere, and the possibility of life. The intense radiation environment of Proxima Centauri adds another layer of complexity. Stellar flares, which are common for red dwarfs, could strip a planet of its atmosphere over time. Yet, scientists have proposed several mechanisms that might allow Proxima b to retain its atmosphere. One possibility is that the planet formed with a thick, primordial atmosphere, rich in hydrogen and helium, which could provide long-term protection against stellar radiation. Over time, this atmosphere might have evolved, leaving behind a secondary atmosphere dominated by heavier elements like carbon dioxide and nitrogen. If Proxima b has a magnetic field, as some models suggest, it could further shield the atmosphere, allowing for conditions stable enough to support liquid water. Liquid water is often seen as the cornerstone of habitability, and Proxima b's position in the habitable zone keeps this possibility alive. The planet's surface temperature depends on a delicate balance between the heat received from Proxima Centauri and the properties of its atmosphere. If the planet has a dense atmosphere, it could create a greenhouse effect, trapping heat and maintaining surface temperatures conducive to liquid water. On the other hand, if Proxima b has a thin or non-existent atmosphere, its surface might be too cold to sustain water in liquid form, relegating it to frozen ice caps or subsurface reservoirs. Subsurface water, in particular, is a compelling possibility. Even if Proxima b's surface is inhospitable due to radiation or temperature extremes, water could exist beneath a thick layer of ice or rock. On Earth, subsurface oceans, such as those beneath the icy crusts of Europa and Enceladus, provide potential habitats for life. Similar environments on Proxima b could harbor microbial life, protected from the harsh surface conditions by kilometers of insulating material. The study of Proxima b also opens the door to understanding the chemistry of exoplanetary atmospheres. The interaction between stellar radiation and atmospheric molecules can produce a wide range of phenomena, including photochemical reactions that might lead to the formation of complex organic compounds. On Earth, such compounds were a precursor to the development of life. If similar processes occur on Proxima b, they could provide a pathway for life to emerge, even in the face of extreme conditions. To investigate these possibilities, scientists are designing increasingly sophisticated instruments to study Proxima b and other exoplanets. The next generation of telescopes, such as the European Extremely Large Telescope, EELT, and NASA's upcoming Habitable Worlds Observatory, will be equipped to analyze the light from Proxima b's atmosphere. By breaking down this light into its component wavelengths, researchers can identify specific molecules, such as water vapor, carbon dioxide, methane, or oxygen. The detection of these molecules, especially in specific ratios, could indicate biological processes or unique geological activity. Proxima b also challenges our understanding of planetary climates. If the planet is tidally locked, the interplay between its dayside and nightside could create exotic weather patterns. Computer simulations suggest that a thick atmosphere or ocean could help redistribute heat, creating a dynamic and potentially habitable climate. Winds might circulate warm air from the dayside to the nightside, preventing extreme temperature variations and allowing for habitable conditions along the Terminator line. On the other hand, if Proxima b lacks an atmosphere, its climate could be far more severe, with a scorching dayside and a frozen nightside. The potential for habitability extends beyond water and atmosphere. Proxima b's environment raises questions about the adaptability of life itself. On Earth, life has evolved to survive in environments ranging from acidic hot springs to deep-sea hydrothermal vents. Organisms like tardigrades can withstand intense radiation, dehydration, and even the vacuum of space. If life exists on Proxima b, it might exhibit similar resilience, thriving in conditions that would be hostile to most Earth-based organisms. The possibility of life on Proxima b also forces us to confront broader questions about the prevalence of life in the universe. If life can exist in the harsh environment of a red dwarf planet, it would suggest that the galaxy is teeming with life, as red dwarfs are the most common type of star. On the other hand, if Proxima b is lifeless despite its apparent potential, it could imply that life is far rarer than we hope, requiring an improbable combination of factors to arise. Proxima b's proximity to Earth makes it a tantalizing target for interstellar exploration. While current technologies are insufficient for sending probes to the Alpha Centauri system, concepts like Breakthrough Starshot offer a glimpse into the future. By using powerful lasers to propel small spacecraft at a fraction of the speed of light, humanity could potentially reach Proxima b within a few decades. Such a mission would provide unprecedented insights into the planet's surface, atmosphere, and potential for life, offering a first-hand look at a world beyond our solar system. Even without direct exploration, Proxima b continues to captivate astronomers and the public alike. Its discovery has fueled a renaissance in the study of exoplanets, inspiring new technologies and theoretical models to understand distant worlds. Proxima b is a reminder of the vastness of the universe and the endless possibilities it holds. As our understanding of this enigmatic planet deepens, so too does our appreciation for the fragile, unique conditions that make life on Earth possible. Proxima b stands as both a challenge and an inspiration, urging us to reach beyond our limits and explore the cosmos in search of answers to the most profound questions of existence. Proxima b challenges us to confront the limits of our understanding of planetary science, habitability, and the adaptability of life. Among the most compelling aspects of its study is the complex relationship between the planet and its host star, Proxima Centauri. This relationship influences everything from atmospheric dynamics to potential biosignatures, and it serves as a cornerstone for evaluating whether Proxima b could truly support life. Proxima Centauri's activity as a red dwarf is one of the most critical factors shaping the environment of Proxima b. Red dwarfs are known for their long lifespans, often burning for trillions of years, far longer than stars like the Sun. This longevity provides a stable energy source over immense timescales, theoretically allowing sufficient time for life to develop. However, the high-energy radiation emitted by red dwarfs, particularly during stellar flares, poses significant challenges. These flares can strip away atmospheres and sterilize planetary surfaces, especially for planets orbiting as close as Proxima b does. To mitigate these effects, Proxima b would require robust defenses. A strong magnetic field, similar to Earth's, could deflect charged particles from stellar winds and protect the atmosphere from erosion. Recent simulations suggest that magnetic fields on tidally locked planets may develop in unique patterns, with intense field lines concentrated at certain latitudes. If Proxima b has such a field, it could create localized regions of atmospheric stability, potentially supporting microclimates conducive to life. Another layer of complexity is added by the possibility of Proxima b's atmosphere being replenished or shielded by geological processes. Volcanic outgassing, for example, could inject greenhouse gases like carbon dioxide into the atmosphere, maintaining surface temperatures that allow liquid water. Additionally, tectonic activity might cycle nutrients and gases between the surface and subsurface, sustaining an active carbon cycle. This dynamic interaction between geology and atmosphere could stabilize the planet's climate over long periods, even in the face of Proxima Centauri's flares. The potential for subsurface oceans on Proxima b is another fascinating avenue of research. If the planet lacks a substantial atmosphere or if surface water has been evaporated by stellar radiation, water might still exist beneath the crust. On Earth, subsurface oceans in places like Antarctica's Lake Vostok or the ice-covered moons of Jupiter and Saturn provide analogs for how water can persist in extreme conditions. Heat generated by the planet's interior, through radioactive decay or tidal forces, could keep these hypothetical oceans in a liquid state. Subsurface oceans are particularly intriguing because they are shielded from external radiation, making them one of the most promising environments for life in the galaxy. Astrobiologists are deeply interested in the possibility of biosignatures on Proxima b. These chemical markers, which include gases like oxygen, methane, and nitrous oxide, could reveal the presence of life if detected in specific ratios. Oxygen, for instance, is highly reactive and would not persist in an atmosphere without a continuous source, such as photosynthesis. Methane, when paired with oxygen, becomes even more compelling, as these gases typically react and destroy one another. The simultaneous presence of both could indicate ongoing biological activity. Instruments like the James Webb Space Telescope and next-generation observatories are designed to detect such subtle signals from distant planets. However, biosignatures must be interpreted cautiously. Abiotic processes, such as volcanic activity or photochemical reactions, can produce many of the same gases associated with life. For example, methane could be generated by hydrothermal vents or chemical reactions between water and rock. To confidently identify life, scientists will need to combine multiple lines of evidence, looking for patterns in atmospheric composition that cannot easily be explained by non-biological processes. Proxima b's position in the habitable zone raises questions about the limits of habitability itself. The traditional concept of the habitable zone is based on the distance from a star where liquid water can exist on a planet's surface. However, recent research suggests that this definition might be too narrow. Factors like atmospheric composition, geothermal heat, and planetary albedo, reflectivity, can significantly alter a planet's ability to retain liquid water. Proxima b's proximity to its star might lead to a runaway greenhouse effect, similar to Venus, or it could support stable liquid water under a dense, protective atmosphere. One of the most exciting scientific frontiers is the development of models to simulate Proxima b's climate and atmospheric evolution. These models incorporate data about Proxima Centauri's luminosity, flare activity, and stellar wind to predict how the planet's environment might evolve over billions of years. They also take into account Proxima b's orbital characteristics, such as eccentricity and axial tilt, which influence seasonal variations and heat distribution. Advanced simulations suggest that even in extreme cases of tidal locking, certain configurations could create temperate zones on the planet's surface. The search for life on Proxima b also intersects with the study of extremophiles on Earth. These resilient organisms thrive in conditions that were once thought to be completely inhospitable, such as acidic hot springs, hypersaline lakes, and environments with high levels of radiation. Tardigrades, for example, can survive in the vacuum of space and endure extreme radiation doses. If life exists on Proxima b, it might adopt similar strategies, evolving to utilize chemical energy rather than sunlight or to repair damage from radiation. One of the most ambitious efforts to study Proxima b is Breakthrough Starshot, a project that aims to send a fleet of nanocraft to the Alpha Centauri system. These spacecraft, equipped with cameras and sensors, would travel at 20% the speed of light, reaching Proxima Centauri in just over 20 years. They could capture high-resolution images of Proxima b's surface, analyze its atmosphere, and provide direct evidence of its habitability. While the technological challenges are immense, ranging from developing the powerful lasers needed to propel the nanocraft to ensuring their durability in interstellar space, the potential scientific payoff is extraordinary. The exploration of Proxima b also pushes the boundaries of theoretical physics and engineering. Concepts like warp drives and faster-than-light travel, while still speculative, are being revisited in light of the growing interest in interstellar exploration. Even if these technologies remain in the realm of science fiction, the drive to explore Proxima b inspires innovation across a wide range of fields, from materials science to artificial intelligence. Proxima b is more than just a planet. It is a window into the future of humanity's exploration of the cosmos. Its study challenges us to develop new technologies, refine our understanding of life, and consider our place in the universe. Whether Proxima b is a barren rock, a cradle of alien life, or something entirely unexpected, it will continue to ignite our curiosity and push the boundaries of what is possible. It represents the next great leap in our quest to understand the universe, a beacon calling us to look beyond the familiar and venture into the unknown. The fascination with Proxima Centauri b grows as scientists delve deeper into the mechanics of its formation, evolution, and the extraordinary forces shaping its environment. At just over 4.24 light-years away, it sits on the edge of what is technologically conceivable for human exploration, making it a tantalizing subject not just for scientific investigation but also for dreams of interstellar travel. One of the most intriguing scientific pursuits is the study of how Proxima b came into existence. Planets forming around red dwarf stars like Proxima Centauri must contend with a complex interplay of gravitational forces, radiation pressure, and volatile star formation environments. Proxima Centauri itself likely underwent a turbulent youth, ejecting vast quantities of radiation and stellar material into its planetary system. These early conditions would have shaped the chemical composition of Proxima b, determining the availability of key elements like carbon, nitrogen, and oxygen, which are essential for life as we know it. Recent computational simulations of Proxima b's early history suggest that it might have formed farther from its host star, where volatile compounds like water ice were more abundant and later migrated inward. This inward migration raises fascinating possibilities. Could Proxima b have carried with it vast reserves of water and other compounds necessary for life? If so, these resources might still exist, perhaps locked beneath a protective layer of rock or ice, shielded from the harsh radiation of its nearby star. Proxima b's magnetic environment is another area of intense scientific focus. The interactions between a planet's magnetic field and the stellar wind from its host star can profoundly impact the planet's atmosphere. Observations of Proxima Centauri reveal that it emits a steady stream of charged particles, plasma, that bombards the space around it. Without a magnetic shield, Proxima b's atmosphere could erode over time, leaving the surface barren. However, recent models suggest that if Proxima b has a strong enough magnetic field, similar to or even stronger than Earth's, it could deflect these particles and maintain a stable atmosphere for billions of years. To investigate this possibility, astronomers are using radio telescopes to search for emissions caused by interactions between Proxima Centauri's stellar wind and Proxima b's magnetic field. These emissions, if detected, could provide indirect evidence of a magnetic field and offer clues about the planet's internal structure. A molten iron core, spinning at the right rate, might generate the necessary magnetic dynamo, just as Earth's core does. One of the most thrilling aspects of Proxima b is its potential climate. Advanced climate models simulate the effects of Proxima Centauri's dim light and intense radiation on the planet's surface and atmosphere. Because Proxima b is likely tidally locked, with one side perpetually facing the star and the other shrouded in darkness, its climate could be drastically different from anything seen on Earth. The day side might be scorching, while the night side remains frozen, but the thin band of twilight at the terminator, the boundary between light and dark, could host more temperate conditions. If Proxima b has an atmosphere thick enough to redistribute heat through winds and convection, it could mitigate these extremes, creating pockets of habitability even in an otherwise hostile environment. Astrobiologists are particularly captivated by the possibility of liquid water on Proxima b. While direct evidence of water remains elusive, indirect observations have bolstered the hypothesis. For example, by measuring Proxima Centauri's luminosity and activity, researchers can estimate how much energy Proxima b receives and how this energy might affect surface water. If the planet has a significant greenhouse effect, driven by gases like carbon dioxide or methane, liquid water could exist over a substantial portion of its surface. Alternatively, water might exist only in subsurface oceans, shielded from radiation by a thick crust of ice or rock. One exciting parallel comes from studies of icy moons in our own solar system, such as Europa and Enceladus. These moons are believed to harbor liquid oceans beneath their icy shells, sustained by heat from tidal forces and radioactive decay. If Proxima b has a similar internal heat source, it might sustain a subsurface ocean teeming with microbial life, even in the absence of surface water. Instruments aboard future space telescopes, such as the upcoming Extremely Large Telescope, ELT, are designed to look for spectral signatures of water vapor or icy surfaces on Proxima b, which could validate these theories. Another groundbreaking area of research involves the detection of biosignatures. Proxima b's potential atmosphere is the primary target for such investigations. Molecules like ozone, carbon dioxide, methane, and even phosphorus, these materials might still persist, either as subsurface oceans or trapped within the planet's crust. Migration scenarios also lead to intriguing questions about the planet's stability and the possibility of interactions with other yet undiscovered planets in the Proxima Centauri system. Such interactions could have influenced Proxima b's orbit, rotational dynamics, and even its habitability. Astrophysicists are particularly interested in the planet's orbital characteristics and how they might affect its climate. Proxima b is believed to have a near-circular orbit, which is beneficial for long-term climate stability, as it avoids extreme temperature swings that can arise from high orbital eccentricity. This stability enhances the chances of Proxima b maintaining liquid water, if atmospheric or subsurface conditions allow. The planet's close proximity to Proxima Centauri, while placing it within the habitable zone, also exposes it to intense tidal forces. These forces could have significant implications for its geology. On one hand, tidal heating might create internal heat that sustains volcanic activity and keeps subsurface oceans in a liquid state. On the other hand, excessive tidal locking, where one side of the planet always faces the star, could result in extreme climate dichotomies, with one hemisphere scorched and the other frozen. However, recent climate models suggest that even tidally locked planets could support habitable conditions along the terminator line, where the perpetual twilight offers a balance of heat and cold. A critical aspect of Proxima b's potential habitability is its atmosphere, or the lack thereof. If the planet has managed to retain a thick atmosphere, it could serve as a protective buffer against the high levels of ultraviolet and X-ray radiation emitted by Proxima Centauri. Sophisticated atmospheric models indicate that even a modest atmosphere of carbon dioxide and nitrogen could stabilize surface temperatures, allowing liquid water to exist. However, atmospheric retention is a major challenge for planets orbiting red dwarfs, as powerful stellar winds and flares can gradually strip gases away. Scientists are exploring the possibility that Proxima b's gravity or magnetic field might help it retain an atmosphere against these harsh conditions. To detect whether Proxima b has an atmosphere, researchers are turning to advanced techniques like transmission spectroscopy. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere, if it exists. By analyzing this light, astronomers can identify the chemical fingerprints of molecules like water vapor, carbon dioxide, methane, or even ozone, key indicators of atmospheric composition and, potentially, biological activity. While no transits of Proxima b have yet been confirmed, Efforts are ongoing to detect them using high-precision instruments like the European Southern Observatory's Very Large Telescope. The intense radiation environment around Proxima Centauri adds another layer of complexity. Proxima b receives far more ultraviolet and X-ray radiation than Earth does from the Sun, raising concerns about the long-term survivability of any surface-based life. However, life might adapt or even thrive under these conditions, as it does in some of Earth's most extreme environments. For example, on Earth, certain microbes in high radiation zones, such as Chernobyl, have evolved to use radiation as an energy source. It's conceivable that life on Proxima b, if it exists, might develop similar mechanisms, such as using radiation for metabolism or evolving protective biofilms to shield against radiation damage. Moreover, the search for liquid water on Proxima b extends beyond its surface. Subsurface environments are increasingly considered some of the most likely habitats for extraterrestrial life. Beneath a thick crust, water could remain liquid, heated by geothermal energy or tidal forces. On Earth, subsurface ecosystems thrive miles below the surface, powered by chemosynthesis instead of sunlight. If Proxima b has similar conditions, microbial life might flourish in deep reservoirs shielded from the harsh radiation above. Geological activity on Proxima b, driven by tidal heating or radioactive decay, could play a crucial role in maintaining habitable conditions. Volcanic outgassing, for example, could replenish an atmosphere lost to stellar winds, injecting carbon dioxide and other greenhouse gases that trap heat. Additionally, volcanic vents could provide nutrient-rich environments where life could emerge and evolve, similar to Earth's hydrothermal vents, which are believed to have played a role in the origin of life. Another critical avenue of research is the role of Proxima Centauri's variability in shaping the planet's climate and habitability. Red dwarfs like Proxima Centauri often exhibit long periods of quiescence punctuated by intense flares. These flares can emit bursts of charged particles that interact with the planet's magnetosphere and atmosphere, potentially creating auroras or triggering chemical reactions in the upper atmosphere. These reactions could either be beneficial, producing prebiotic molecules, or harmful, depleting the atmosphere's protective layers. Understanding this balance is crucial for determining whether Proxima b's environment can support life. As the study of Proxima b progresses, future missions aim to provide direct insights into its characteristics. Groundbreaking initiatives like the Breakthrough Starshot project envision sending tiny, laser-propelled spacecraft to the Alpha Centauri system, capable of capturing high-resolution images and gathering data about Proxima b's surface, atmosphere, and potential moons. While the technological challenges are immense, the possibility of receiving direct observations from another planetary system is driving unprecedented innovation. Additionally, next-generation telescopes like the European Extremely Large Telescope, EELT, and the planned Habitable Worlds Observatory will offer unparalleled capabilities for observing Proxima b. These instruments could resolve the planet's surface features, detect atmospheric composition, and even search for seasonal variations that might hint at biological processes. Such advancements will mark a new era in exoplanetary science, where we not only identify distant worlds, but also characterize them in extraordinary detail. Proxima Centauri b stands as a testament to humanity's relentless curiosity and ingenuity. Its study is pushing the boundaries of astrophysics, planetary science, and astrobiology, while inspiring a new generation of researchers and explorers. Whether Proxima b ultimately proves to be a lifeless rock or a thriving ecosystem, its exploration will bring us closer to answering some of the most profound questions. Are we alone in the universe? How common are habitable worlds? What does it take to sustain life beyond Earth? In Proxima b, we find not only a potential second Earth, but also a reflection of our own drive to explore and understand the cosmos. The fascination with Proxima Centauri b extends far beyond the confines of scientific inquiry, touching on philosophical, existential, and even practical questions about humanity's place in the cosmos and the potential for interstellar colonization. This planet, orbiting the nearest star outside our solar system, serves as a natural laboratory for testing our theories of habitability, planetary formation, and the resilience of life. Proxima Centauri's behavior as a flare star, emitting powerful bursts of high-energy radiation, is both a challenge and an opportunity for understanding Proxima B's environment. These flares are far more intense than those produced by the Sun, and their frequency can have profound implications for the planet's surface and atmosphere. In one notable event in 2019, Proxima Centauri released a flare 14,000 times brighter than its baseline luminosity in ultraviolet wavelengths, an energy surge that could have dramatically affected Proxima B's environment. Such flares might strip away atmospheric layers, especially the lighter molecules like hydrogen, if the planet lacks adequate protection. However, they could also act as catalysts for chemical reactions in the upper atmosphere, potentially producing complex organic molecules necessary for life. On Earth, similar processes in the early atmosphere, driven by solar radiation and lightning, are thought to have contributed to the formation of prebiotic compounds like amino acids. Astrobiologists are particularly interested in the potential for Proxima B's atmosphere to develop secondary protective mechanisms. For example, high concentrations of ozone or other radiation-absorbing molecules could act as a shield, limiting the penetration of harmful UV and X-ray radiation to the surface. Determining whether Proxima B's atmosphere could sustain such protective chemistry is a critical goal for future observational campaigns using instruments like the James Webb Space Telescope or ground-based arrays such as the Square Kilometre Array, SKA. Proxima B's proximity to its host star also makes it an ideal candidate for studying the effects of tidal forces on planetary geology. Tidal locking, where one hemisphere permanently faces the star, could result in significant internal heating due to gravitational interactions. This heating might sustain volcanic activity, driving the recycling of elements between the surface and interior. Such processes are essential for maintaining a dynamic atmosphere and could create localized environments, such as hydrothermal vents, where life might emerge. On Earth, hydrothermal vent ecosystems thrive in complete darkness, relying on chemical energy rather than sunlight. These deep-sea communities are powered by chemosynthetic bacteria that utilize sulfur and methane compounds released from the planet's crust. If Proxima B has similar geological activity, it could host analogous ecosystems beneath its surface or even along the terminator line, the region between perpetual day and night, where temperatures might be stable enough for liquid water to exist. One of the most tantalizing prospects in the study of Proxima B is the detection of biosignatures, observable features or chemical markers that indicate the presence of life. To date, no direct observations of Proxima B's atmosphere have been made, but the search for biosignatures remains a high priority for upcoming missions. Molecules like oxygen, methane, and nitrous oxide are particularly interesting because they are difficult to sustain in an atmosphere without a continuous source, such as biological activity. Even in the absence of direct life, the planet's environment could still exhibit signs of prebiotic chemistry. Laboratory experiments on Earth, such as the famous Miller-Urey experiment, have demonstrated that organic molecules can form under conditions mimicking early planetary atmospheres. If Proxima B has a similar chemical composition, stellar radiation might drive the formation of complex carbon-based molecules, laying the groundwork for life. Advanced spectroscopic techniques are being developed to detect these signatures. Instruments capable of measuring the light spectra from Proxima Centauri as it interacts with Proxima B's atmosphere could identify absorption lines corresponding to specific molecules. Future telescopes, such as the European Space Agency's Ariel mission, aim to characterize exoplanetary atmospheres in unprecedented detail, potentially resolving this question within the coming decades. The study of extremophiles on Earth, organisms that thrive in environments once thought inhospitable, offers a glimpse into the kind of life that might exist on Proxima B. For instance, Deinococcus radiodurans, a bacterium known as the Conan of microbes, can withstand radiation levels thousands of times higher than what would be lethal to humans. Similar adaptations might enable life on Proxima B to survive the intense UV and X-ray bombardment from Proxima Centauri. Another Earth analog is life in permafrost regions, where microorganisms remain dormant for millennia, only to revive when conditions improve. If Proxima B's surface alternates between habitable and extreme states, life forms might adopt similar strategies, surviving in spore-like forms during hostile periods and reactivating when conditions stabilize. Subsurface habitats are another promising avenue for life on Proxima b. Beneath layers of rock or ice, life could be insulated from radiation and temperature extremes. On Earth, deep subsurface ecosystems exist miles below the surface, sustained by energy from chemical reactions rather than sunlight. These systems demonstrate the incredible adaptability of life and suggest that even planets with harsh surface conditions could host thriving biospheres underground. Proxima b's proximity to Earth makes it a prime candidate for direct exploration. While current technology limits us to remote observation, ambitious projects like Breakthrough Starshot aim to change this paradigm. By propelling lightweight nanocraft to 20% of the speed of light using powerful laser arrays, scientists hope to reach Proxima Centauri within a few decades. These spacecraft, equipped with cameras and sensors, could provide direct images of Proxima b's surface, revealing geological features, potential oceans, or even signs of artificial structures. The implications of such a mission are profound. If successful, it would mark humanity's first foray into interstellar exploration, opening the door to a new era of discovery. Proxima b could serve as a testbed for technologies that might one day enable human colonization of distant worlds. Understanding its environment, resources, and potential hazards is a crucial step in preparing for this future. Proxima Centauri b does more than just expand our understanding of the universe. It forces us to reflect on the uniqueness of our own planet. The study of this distant world highlights the delicate balance required for habitability and underscores the rarity of conditions that sustain life. As Earth faces mounting environmental challenges, Proxima b serves as a reminder of the fragility and preciousness of our home. The exploration of Proxima b is a story of human curiosity and ambition, a testament to our desire to reach beyond the boundaries of our knowledge and grasp at the stars. Whether this planet harbors life, serves as a beacon for interstellar travel, or simply remains an object of scientific wonder, it will forever symbolize the limitless possibilities of the cosmos and our enduring quest to understand it. Proxima Centauri b captivates scientists and dreamers alike because it is not merely a distant exoplanet. It is a gateway to some of the most profound questions we can ask about life, the universe, and our place within it. Orbiting the nearest star to our own, it beckons as a world where science fiction may one day become reality, and where the mysteries of existence could unfold in ways we can scarcely imagine. The question of habitability on Proxima b is intertwined with its enigmatic atmospheric properties. If the planet managed to retain a thick atmosphere, it might act as a protective cocoon against the relentless radiation from Proxima Centauri. The interplay between stellar winds, magnetic fields, and atmospheric escape mechanisms becomes a tantalizing puzzle. On Earth, the magnetosphere deflects charged particles from the sun, preventing our atmosphere from being eroded. If Proxima b has a magnetic field generated by a liquid metallic core, it might exhibit similar resilience, but the conditions for this remain speculative. Stellar flares from Proxima Centauri are not merely a threat, they could also drive fascinating chemical reactions in Proxima b's atmosphere. High-energy particles from these flares might interact with atmospheric molecules to produce hydrogen cyanide, formaldehyde, or other compounds that are precursors to life as we know it. These molecules could serve as the building blocks for complex organic chemistry, even under harsh conditions. Such phenomena, observed in the atmospheres of gas giants like Jupiter, hint at the universal nature of chemical processes that may lay the groundwork for life. The potential for subsurface life on Proxima b remains one of its most alluring mysteries. Beneath a crust of rock or ice, heat from the planet's interior, driven by radioactive decay or tidal forces, could maintain liquid water reservoirs. These hidden oceans might harbor microbial life, shielded from surface radiation by layers of insulating material. On Earth, extremophiles flourish in such environments, feeding on chemical energy from hydrothermal vents. Could similar life forms exist on Proxima b, evolving independently under a completely alien set of conditions? The planet's climate is a particularly intriguing enigma. Proxima b's orbit places it close enough to its star to experience intense stellar energy, yet not so close as to preclude the possibility of liquid water. In a tidally locked scenario, One hemisphere would face perpetual daylight while the other remains in eternal darkness. Climate models suggest that if the planet has a substantial atmosphere, powerful winds could transport heat from the dayside to the nightside, creating regions of temperate conditions along the Terminator line. These twilight zones might represent some of the most habitable regions, with moderate temperatures and potentially stable ecosystems. The search for life on Proxima b extends to the detection of biosignatures, chemical indicators that might betray the presence of biological processes. Oxygen, methane, and ozone are often cited as key markers, but scientists are also exploring more subtle signs, such as variations in the ratio of carbon isotopes. On Earth, biological processes preferentially use lighter isotopes, leaving behind a distinctive chemical fingerprint. If Proxima b exhibits similar patterns, it could point to the presence of life, even if that life exists only as microbial colonies. The role of water cannot be overstated in the search for habitability. While liquid water on the surface is the traditional hallmark of a habitable world, scientists are increasingly open to the idea of exotic water cycles. For example, in a thin atmosphere, water might sublimate directly from ice to vapor, forming transient clouds that distribute moisture across the planet. Alternatively, water trapped in subsurface reservoirs could seep to the surface through cracks and fissures, creating temporary habitats for life. On Earth, similar cycles occur in extreme desert environments, where water availability is fleeting yet sufficient to sustain specialized organisms. Breakthroughs in observational technology bring Proxima b closer to our grasp. Telescopes like the James Webb Space Telescope and the upcoming Habitable Worlds Observatory are designed to study the atmospheres of exoplanets with unprecedented precision. By analyzing the spectrum of light passing through or reflected by Proxima b's atmosphere, scientists can identify the molecular composition, temperature, and even weather patterns. These data could confirm the presence of water vapor, carbon dioxide, or methane, key ingredients for habitability. Proxima b also serves as a proving ground for our dreams of interstellar exploration. The Breakthrough Starshot initiative envisions sending tiny, laser-driven spacecraft to the Alpha Centauri system, capable of reaching speeds of up to 20% the speed of light. These interstellar probes would arrive within a few decades, transmitting images and data about Proxima b back to Earth. Such a mission would represent humanity's first physical step beyond the confines of the solar system, transforming our relationship with the cosmos. Even in the absence of direct exploration, the scientific insights gained from studying Proxima b are reshaping our understanding of planetary systems. Red dwarfs like Proxima Centauri represent the majority of stars in the galaxy, meaning that planets like Proxima b could be far more common than previously thought. If life can exist in such environments, amidst flares, radiation, and tidal locking, it raises the possibility that the universe is teeming with life in forms we have yet to comprehend. The allure of Proxima b extends beyond science. It ignites the imagination with visions of what might be. Could there be ancient alien civilizations on Proxima b, looking back at us with the same curiosity? Could humanity one day set foot on its surface, building colonies beneath protective domes or exploring its hidden oceans? These questions transcend mere speculation. They challenge us to expand the boundaries of what is possible and to embrace the infinite potential of the universe. In every way, Proxima b is a reflection of humanity's greatest aspirations. It is a distant mirror of our own world, a reminder of the fragility and wonder of life, and an invitation to dream beyond the confines of our solar system. Whether Proxima b turns out to be a lifeless rock, a cradle of alien life, or a future home for humanity, it will forever stand as a symbol of our desire to explore, understand, and connect with the cosmos. Proxima Centauri b remains one of the most compelling enigmas in the search for extraterrestrial life and habitable worlds. Every scientific model, observation, and simulation deepens our understanding while unveiling new questions about its nature. It is a place where science, imagination, and the future of humanity converge. A world that, despite its proximity in cosmic terms, challenges us to expand our technological limits and our very perception of life in the universe. The challenge of studying Proxima b begins with its extreme proximity to Proxima Centauri, a star whose violent nature demands significant adaptations for any potential life forms. Flares from Proxima Centauri can increase the star's brightness in ultraviolet wavelengths by hundreds of times within minutes, bathing Proxima b in a torrent of high-energy radiation. This relentless assault would strip away an unprotected atmosphere over time, leaving the planet barren and lifeless, or so one might think. Scientists are beginning to hypothesize ways in which life could still emerge and persist under these conditions. One possibility is that Proxima b's surface is shielded by a dense, regenerative atmosphere. Even if stellar winds erode the upper layers, volcanic activity might replenish it, injecting carbon dioxide, water vapor, and other gases. On Earth, volcanoes release greenhouse gases that regulate surface temperatures by trapping heat. If Proxima b's geology follows a similar pattern, its atmosphere could create a stable climate zone capable of supporting liquid water. Another defense against Proxima Centauri's aggression could be found beneath Proxima b's surface. Life doesn't necessarily require a temperate surface environment. Subsurface life forms on Earth, such as those found in the deep biosphere kilometers below ground, thrive by extracting energy from chemical reactions. On Proxima b, subsurface oceans heated by geothermal or tidal forces might harbor microbial ecosystems completely insulated from radiation. Tidal forces are particularly intriguing. Proxima b's tight orbit likely creates immense gravitational stress, producing heat through friction within its interior. This process, known as tidal heating, might not only sustain volcanic activity, but also prevent subsurface water from freezing. Europa and Enceladus, icy moons in our solar system, rely on similar mechanisms to maintain their hidden oceans. If Proxima b experiences comparable forces, it could have a dynamic subsurface environment, rich in potential energy sources for life. The search for biosignatures on Proxima b has galvanized international efforts to develop advanced observational tools. The prospect of detecting molecules like oxygen, methane, or water vapor in its atmosphere excites astrobiologists, as these compounds, when found in certain ratios, can be strong indicators of biological processes. However, the challenge lies in differentiating between biological and abiotic sources. For example, methane can be produced by microbial life or by volcanic activity. Determining the source of these gases will require detailed spectroscopic analysis, which next-generation telescopes, like the Extremely Large Telescope, ELT, are being designed to perform. The atmosphere of Proxima b, if it exists, could also exhibit phenomena like photochemistry, driven by Proxima Centauri's intense radiation. High-energy photons might break apart stable molecules, creating a cascade of reactions that form new compounds, including organic molecules. On Earth, similar processes in the early atmosphere were crucial in shaping the chemical environment that eventually gave rise to life. Proxima b might serve as a living experiment in how radiation shapes planetary chemistry, offering insights into how life could arise under vastly different conditions. Recent simulations have explored the thermal dynamics of a tidally locked Proxima b. These studies reveal that even with one hemisphere perpetually exposed to the star, atmospheric circulation could distribute heat across the planet, creating a global climate system. Winds could transport heat from the dayside to the nightside, preventing extreme temperature gradients and potentially stabilizing conditions along the Terminator line. This twilight zone, where perpetual sunset meets perpetual night, could host a narrow but viable band of habitability. Scientists are also exploring the possibility that Proxima b's surface is shielded by thick clouds or an aerosol layer, which could reflect harmful radiation while trapping infrared heat. This mechanism would act as a double buffer, moderating surface temperatures and protecting any potential life forms. Cloud dynamics, however, remain one of the least understood aspects of planetary climates, and Proxima b offers a rare opportunity to refine these models. One of the most ambitious initiatives in the study of Proxima b is the Breakthrough Starshot project, which envisions sending fleets of miniature, light-powered spacecraft to the Alpha Centauri system. These tiny probes, accelerated to relativistic speeds by powerful Earth-based lasers, would traverse the 4.24 light-years to Proxima Centauri in just a few decades. Equipped with cameras, spectrometers, and other instruments, they could provide humanity's first close-up view of an exoplanet. Imagine the moment when we receive the first images of Proxima B's surface, its landscapes, potential oceans, or atmospheric phenomena. Such a breakthrough would redefine our understanding of the universe and our place within it. The implications of discovering life, or even the potential for life, on Proxima B are staggering. If life exists there, it would suggest that life is not a rare cosmic accident, but a natural outcome of planetary evolution, emerging wherever conditions allow. Conversely, if Proxima B proves to be sterile despite its apparent potential, it would force us to reconsider the uniqueness of Earth and the improbability of life elsewhere. Proxima B is also an invitation to reimagine the future of humanity. It is not just a scientific target, but a beacon for our interstellar aspirations. Colonizing Proxima B, or even sending human explorers, would require technological leaps in propulsion, life support, and planetary engineering. Yet, the prospect is not as distant as it once seemed. Proxima B challenges us to think beyond our immediate surroundings, to innovate, and to dream of a future where the stars are within our reach. This distant planet is more than just a point of light in the night sky. It is a testament to our capacity for curiosity and discovery. It represents the unknown, the possibilities that lie beyond the horizon, and the unyielding drive to explore that defines humanity. Proxima Centauri B may ultimately reveal a lifeless, hostile environment, or it may open the door to a new chapter in the story of life in the universe. Either way, its study promises to transform the way we see ourselves and our place in the cosmos. Proxima Centauri B is not just a planet. It is a mirror reflecting our greatest scientific and philosophical pursuits. It embodies the confluence of cutting-edge technology, boundless curiosity, and the innate human desire to connect with something beyond ourselves. Every step toward understanding this world brings us closer to answering fundamental questions. What are the limits of life? How do planets evolve under extreme conditions? And could we one day call a world like Proxima B our home? One of the most tantalizing aspects of Proxima B is its potential to challenge the boundaries of what we consider habitable. Earth-like conditions, while ideal, are not the only template for life. On Earth, extremophiles thrive in environments once deemed inhospitable. Places like deep-sea hydrothermal vents, acidic lakes, or beneath kilometers of ice in Antarctica. These life forms have rewritten the rules of habitability, and Proxima B's extreme conditions might similarly foster life forms adapted to its unique environment. The harsh radiation environment of Proxima Centauri could drive the evolution of protective mechanisms in any potential life forms. Organisms might develop robust radiation shielding, such as thick cell walls or specialized pigments that absorb harmful wavelengths. Alternatively, life could evolve underground, where rock and soil provide natural insulation against radiation. Subsurface ecosystems on Earth, sustained by chemical energy rather than sunlight, offer compelling analogs for how life might thrive beneath Proxima B's surface. Even if Proxima B lacks life, it could still serve as a living laboratory for planetary science. Its proximity offers an unparalleled opportunity to study the effects of red dwarf stars on orbiting planets. Red dwarfs are the most common type of star in the galaxy, yet their planets remain among the least understood. By unraveling the mysteries of Proxima B, we gain insights that apply to potentially billions of other planets across the Milky Way. The influence of Proxima Centauri's stellar flares on Proxima B is a critical area of research. These flares are not just random outbursts. They are fundamental to the star's magnetic activity. High-energy particles released during flares interact with planetary atmospheres in complex ways, potentially driving the loss of lighter gases like hydrogen. However, they might also create transient protective layers of ionized particles, temporarily shielding the planet from further radiation. Understanding these processes could reveal how planets around red dwarfs balance destruction and renewal, maintaining conditions suitable for life. The search for biosignatures on Proxima B is another frontier that bridges cutting-edge science and cosmic wonder. Advanced instruments aim to detect the faintest hints of molecules like oxygen, methane, or water vapor. However, scientists must tread carefully when interpreting these signals. Abiotic processes, those unrelated to life, can produce similar chemical signatures. For instance, oxygen can accumulate in an atmosphere through photodissociation, where ultraviolet light breaks water molecules apart. Disentangling these processes requires a deep understanding of planetary chemistry and the development of sophisticated models that account for every possible scenario. Proxima B's role in advancing technology cannot be overstated. The drive to study this distant world has catalyzed innovations in telescope design, computational modeling, and even space propulsion. The next generation of observatories, such as the European Extremely Large Telescope and NASA's LUVOIR, Large UV/Optical/IR Surveyor, will have the sensitivity to directly image Proxima B, potentially resolving surface features or detecting atmospheric haze. These telescopes represent humanity's most ambitious leap yet in the search for other worlds. Meanwhile, the Breakthrough Starshot project is pushing the boundaries of what is technically feasible. Sending a fleet of nanocraft to Proxima Centauri at relativistic speeds would require unprecedented advances in materials science, laser technology, and miniaturization. Yet the promise of receiving close-up images and data from Proxima B within a human lifetime makes this a worthy endeavor. Such a mission would mark humanity's first step toward becoming an interstellar species. Proxima B also serves as a canvas for imagining the future of human exploration. If one day we develop the technology to travel there, how would we adapt to its environment? Colonizing a planet orbiting a red dwarf would require overcoming immense challenges, protecting against radiation, generating sustainable food and water supplies, and constructing habitats capable of withstanding extreme conditions. These challenges, daunting as they are, fuel innovation and push us to expand our understanding of engineering, biology, and the resilience of life. Philosophically, Proxima B reminds us of the preciousness of Earth. In our quest to find other habitable worlds, we are reminded of how rare and fragile our own planet is. Proxima B, with its extreme environment, starkly contrasts the delicate balance that makes Earth so uniquely suited for life. This realization underscores the importance of preserving our home while inspiring us to seek out new horizons. As humanity stands on the cusp of interstellar exploration, Proxima B represents both a challenge and an inspiration. It invites us to push the boundaries of what is possible, to ask questions that transcend the limits of our understanding, and to dream of a future where we are no longer confined to a single planet. Whether Proxima B harbors life, serves as a future outpost, or simply offers a window into the nature of exoplanets, its impact on our collective imagination is profound. The journey to Proxima B has only just begun. Each discovery, each new insight, brings us closer to unlocking the secrets of this distant world. In its orbit around a dim red star, Proxima B shines as a beacon of hope, curiosity, and the unyielding human spirit. Its study is not just a quest for knowledge. It is a testament to our enduring desire to explore the universe and find our place among the stars. Proxima Centauri B may be a small planet orbiting a dim red star, but it holds an outsized place in the story of human exploration. It represents the tantalizing possibility that life, in some form, could exist beyond the confines of Earth. It challenges us to think bigger, to reach further, and to push the boundaries of what is possible. Yet, even if Proxima B turns out to be lifeless, a rocky, barren world bathed in radiation, it will not diminish its significance. Its existence alone proves that planets are abundant, that the cosmos is a vast, dynamic tapestry filled with worlds that are waiting to be explored. This little planet, circling a flickering star just over 4 light-years away, has already changed us. It has sparked new ideas, inspired technological innovation, and reignited our collective sense of wonder. Proxima B is not merely a destination. It is a symbol, a reminder that our journey is just beginning, that there is so much more to discover, to learn, and to experience. In the face of the vast and unyielding cosmos, Proxima B reminds us of our shared humanity. We are explorers, dreamers, and seekers, bound by our curiosity, and united by our quest to understand the universe. Whether Proxima b becomes a second Earth, a stepping stone for interstellar travel, or a silent witness to the history of its system, it will forever mark a turning point in our search for life and meaning among the stars. One day, perhaps far in the future, a message may arrive from a tiny fleet of probes that dared to cross the abyss, carrying with it images of alien landscapes, the chemical fingerprints of an alien world, and perhaps even the faintest whispers of life. In that moment, Proxima b will no longer be a distant, abstract idea. It will be a place, a real and tangible part of our shared existence. And as we gaze upon those images, as we study that data, we will see not only the face of another world, but also the reflection of our enduring spirit, forever reaching for the stars. Haumea, a distant dwarf planet residing in the Kuiper Belt, is a celestial body that challenges and fascinates astronomers with its unique characteristics and enigmatic origins. Located beyond Neptune, Haumea is one of the most intriguing objects in the outer reaches of our solar system, offering valuable insights into planetary formation and the dynamics of the early solar system. Discovered in 2004, Haumea quickly garnered attention due to its unusual properties. Named after the Hawaiian goddess of fertility and childbirth, Haumea symbolizes creation and life cycles, which aligns with the dynamic processes of celestial evolution it represents. Its discovery was surrounded by controversy, as two independent research groups claimed to have identified it first. Nevertheless, Haumea's classification as a dwarf planet by the International Astronomical Union (IAU) in 2008 solidified its place in scientific literature. One of the most remarkable features of Haumea is its rapid rotation. The dwarf planet completes a full rotation on its axis in approximately 3.9 hours, making it one of the fastest rotating large objects in the solar system. This extreme spin has dramatically influenced Haumea's shape, causing it to become elongated into a triaxial ellipsoid rather than a near-spherical form like many other celestial bodies. Measurements estimate its dimensions to be approximately 2322 by 1704 by 1138 kilometers, highlighting its distorted structure. The cause of Haumea's rapid rotation remains a subject of ongoing investigation. The prevailing hypothesis suggests that Haumea may have experienced a colossal impact early in its history. This collision not only accelerated its spin, but also ejected a significant amount of material into space, potentially forming a family of smaller objects that share similar orbital characteristics. These fragments, known as the Haumea family, consist of icy bodies scattered across the Kuiper Belt. Haumea's surface is predominantly covered with crystalline water ice, as revealed by spectral analysis. This icy surface reflects sunlight efficiently, giving Haumea a high albedo of approximately 0.66. The presence of crystalline ice is intriguing, as it typically forms at relatively high temperatures, which contradicts the frigid environment of the Kuiper Belt. Scientists hypothesize that tidal heating or past radioactive decay within Haumea may have provided the necessary energy to maintain its surface in a crystalline state. The dwarf planet also exhibits signs of surface heterogeneity, with darker regions potentially composed of organic compounds or rocky material. These features may indicate a complex history of resurfacing events, impacts, and thermal evolution. Haumea is accompanied by two known moons, Hayaka and Namaka, named after the daughters of the Hawaiian goddess. Hayaka, the larger of the two, orbits Haumea at a distance of approximately 49,880 kilometers and has a diameter of about 310 kilometers. Namaka, the smaller moon, has an irregular shape and orbits closer to Haumea. The study of these moons has provided valuable clues about Haumea's formation and the dynamics of its system. The orbital characteristics of Hayaka and Namaka suggest that they may have formed as a result of the same giant impact that influenced Haumea's rapid rotation. Their compositions are also rich in water ice, further supporting the theory that they originated from Haumea's outer layers. In 2017, astronomers made the surprising discovery of a ring around Haumea. This ring, composed of particles, lies in Haumea's equatorial plane and is situated at a distance of about 2,287 kilometers from its center. The presence of a ring around a dwarf planet was unexpected, as such structures are typically associated with gas giants like Saturn. The discovery of Haumea's ring has sparked new discussions about the mechanisms that can lead to the formation of such features in small celestial bodies. Haumea orbits the Sun at an average distance of 43 astronomical units, AU, placing it well within the Kuiper Belt, a region populated by icy bodies and remnants from the early solar system. Its orbital period is approximately 283 Earth years, and its path is moderately elliptical, with an eccentricity of 0.19. Haumea's inclination of 28 degrees relative to the ecliptic plane further distinguishes its orbit from other Kuiper Belt objects. The Kuiper Belt itself is a treasure trove of scientific discoveries, as it contains objects that have remained relatively unchanged since the formation of the solar system. Haumea's unique properties make it a key subject of study for understanding the physical and chemical processes that shaped this distant region. Haumea's rapid rotation, unusual shape, and icy composition challenge traditional models of planetary formation. The study of Haumea and its system offers critical insights into the processes of accretion, differentiation, and impact events in the early solar system. Moreover, Haumea serves as a natural laboratory for studying the interactions between celestial bodies, including tidal forces, collisional dynamics, and the formation of secondary systems such as rings and moons. Additionally, the discovery of Haumea's ring system has expanded our understanding of ring dynamics and their prevalence among different types of celestial objects. By studying Haumea, scientists can refine their models of ring formation and stability, potentially uncovering new mechanisms that operate in the outer solar system. Despite its significance, Haumea remains a relatively unexplored object. No spacecraft have visited this distant dwarf planet, and much of our knowledge comes from ground-based observations and telescopic studies. Future missions to the Kuiper Belt, such as proposed flybys or orbiters, could provide unprecedented data on Haumea's geology, composition, and evolution. Advances in technology, including powerful space telescopes and adaptive optics, are also expected to enhance our understanding of Haumea. These tools will enable astronomers to resolve finer details of its surface, study its ring system in greater depth, and analyze its moons with higher precision. Haumea, with its striking features and mysterious history, stands as a testament to the complexity and diversity of the solar system. Its study not only deepens our knowledge of distant worlds, but also sheds light on the fundamental processes that govern planetary systems. As exploration of the outer solar system continues, Haumea will undoubtedly remain a focal point of scientific curiosity, inspiring new generations of researchers to uncover the secrets of this remarkable dwarf planet. Haumea's rapid rotation and elongated shape raise profound questions about the dynamics of planetary bodies in the outer solar system. One of the most plausible explanations for its current state involves a massive collision with another large Kuiper Belt object, KBO, early in its history. Such an impact would not only have accelerated Haumea's spin, but also caused significant material to be ejected into its surroundings, giving rise to the family of objects now associated with it. These fragments share similar orbital characteristics and spectral features, suggesting a common origin. By studying these fragments, scientists can reconstruct the conditions and events that shaped Haumea, offering a rare glimpse into the violent early stages of planetary formation. The crystalline water ice observed on Haumea's surface is another enigmatic feature. Crystalline ice forms at temperatures above 110 K, which is significantly warmer than the average temperature in the Kuiper Belt, where conditions are typically frigid, with temperatures hovering around 40 K. This discrepancy suggests that Haumea may have undergone internal heating in its past. The source of this heating could have been tidal interactions, radiogenic decay, or even residual heat from the giant impact that shaped its rotation. This internal activity might have led to resurfacing events, exposing fresher ice layers while burying older, darker material beneath the surface. Such processes would explain the varying albedo and composition observed on Haumea today. The discovery of Haumea's ring added an unexpected dimension to its study. Rings around small bodies like Haumea challenge traditional notions of how such features form and persist. Theories suggest that the ring could be the result of collisional debris that never coalesced into a moon or material ejected from Haumea's surface due to its rapid rotation. The particles in the ring are believed to orbit within the Roche limit of Haumea, where tidal forces prevent them from clumping together into a larger body. Detailed analysis of the ring's composition and dynamics could provide valuable clues about the interactions between Haumea's surface and its surrounding environment, as well as the role of centrifugal forces in maintaining the ring structure. Haumea's moons, Hayaka and Namaka, offer additional opportunities to explore the dynamics of this unique system. Hayaka, the larger of the two, is particularly intriguing due to its relatively high albedo and water ice-rich composition, which mirror the surface features of Haumea itself. This similarity supports the hypothesis that Hayaka formed from material ejected during the same collision that shaped Haumea's rapid spin. Namaka, on the other hand, has an irregular orbit that suggests past interactions with Hayaka or tidal effects from Haumea. The study of these moons can reveal much about the long-term evolution of multi-body systems and the gravitational interactions that govern their stability. The Kuiper Belt, where Haumea resides, is a region filled with ancient relics of the solar system's formation. Unlike the inner planets, which have undergone significant geological and atmospheric evolution, Kuiper Belt objects, KBOs, are thought to have remained relatively pristine. Haumea, however, stands out due to its dynamic history and unique features. Its study provides a counterpoint to other KBOs, highlighting the diversity of processes that have shaped this distant region. By comparing Haumea with other large KBOs like Pluto, Eris, and Makemake, scientists can build a more comprehensive picture of the Kuiper Belt's formation and the role of giant impacts in shaping planetary systems. The presence of organic compounds on Haumea's surface is another area of active research. These compounds, often referred to as tholins, are formed through the photochemical reaction of simple molecules like methane and nitrogen under the influence of ultraviolet light and cosmic rays. The detection of tholins on Haumea suggests that complex chemical processes are at work even in the cold, distant reaches of the solar system. These organics may hold clues to the chemical precursors of life, offering insights into the potential for habitability on icy worlds. Future exploration of Haumea could revolutionize our understanding of the outer solar system. While no spacecraft has yet visited this distant world, its study remains a high priority for missions aiming to explore the Kuiper Belt. A dedicated mission to Haumea could include high-resolution imaging, spectroscopy, and in-situ analysis of its ring and moons. Such a mission would provide detailed data on its surface composition, internal structure, and the dynamics of its unique system. Advances in propulsion technology and miniaturized instruments could make such a mission feasible within the next few decades. Observations from Earth-based telescopes and space observatories like the James Webb Space Telescope, JWST, are already helping to refine our understanding of Haumea. High-precision measurements of its light curve, for example, have provided detailed information about its shape and rotation. Spectroscopic studies have revealed subtle variations in its surface composition, hinting at a more complex history than previously thought. These observations underscore the importance of continued investment in astronomical infrastructure to study distant objects like Haumea. Haumea's story is not just about a single dwarf planet, but about the broader processes that govern the evolution of planetary systems. Its rapid rotation, elongated shape, icy surface, and dynamic environment serve as a microcosm of the interplay between impacts, rotation, and gravitational forces. By studying Haumea, scientists are not only uncovering the secrets of a distant world, but also gaining insights into the forces that have shaped the solar system as a whole. As our understanding deepens, Haumea will undoubtedly continue to inspire new theories, discoveries, and explorations in the field of planetary science. The study of Haumea provides a window into the physical processes that shaped not only the Kuiper Belt but also planetary systems beyond our own. Its elongated shape and rapid spin are unique among known celestial objects of its size, creating a natural laboratory to test theories of rotational dynamics, collisional evolution, and the behavior of matter under extreme conditions. When viewed through this lens, Haumea becomes more than just a distant, icy world. It transforms into a cosmic puzzle piece, revealing how primordial material evolves over billions of years. One of the most compelling aspects of Haumea is its ring, an unexpected feature for a body of its size. This ring system challenges traditional planetary science, as rings have historically been associated with massive gas giants like Saturn, Jupiter, Uranus, and Neptune. The discovery of Haumea's ring suggests that such features may be more common than previously thought, particularly in the Kuiper Belt. The ring's stability and persistence imply that Haumea's rapid rotation plays a central role in maintaining this structure. Centrifugal forces generated by its spin likely prevent the material in the ring from coalescing into a moon or falling back to the planet's surface. Detailed studies of Haumea's ring dynamics could also shed light on the broader phenomenon of ring formation across the solar system. For instance, scientists are interested in whether the particles in Haumea's ring have a consistent size distribution or whether they vary significantly. Understanding these details might help researchers model the processes that lead to the formation of rings and predict where they might be found around other celestial bodies. Spectroscopic observations of Haumea have revealed the presence of minerals and compounds that hint at its internal composition. While the surface is predominantly crystalline water ice, there are also indications of silicates and other rocky material. This dual nature suggests that Haumea underwent a process of differentiation early in its history, with denser materials sinking to form a rocky core while lighter, volatile-rich materials migrated to the surface. Such differentiation processes are critical for understanding how planetary bodies evolve from homogeneous mixtures of material into layered structures with distinct geological and chemical properties. The presence of crystalline water ice on Haumea is particularly intriguing because it implies relatively recent geological activity. In the frigid temperatures of the Kuiper Belt, crystalline ice would ordinarily transition to an amorphous state over time due to cosmic ray bombardment and the natural degradation of its molecular structure. The persistence of crystalline ice on Haumea suggests that the dwarf planet may have undergone resurfacing events in its geologically recent past. These could have been triggered by tidal heating from its moons, internal radioactive decay, or even impacts from other Kuiper Belt objects. Each of these scenarios carries implications for the thermal and mechanical evolution of icy bodies in the outer solar system. Another fascinating area of research is the role of Haumea's moons, Hyakka and Namaka, in shaping its dynamical environment. The larger moon, Hyakka, appears to be rich in water ice, which aligns with the spectral properties of Haumea itself. This suggests that Hyakka may have formed from material ejected during the giant impact that gave Haumea its rapid rotation. Namaka, the smaller and more irregularly shaped moon, exhibits a more chaotic orbit, likely influenced by gravitational interactions with both Haumea and Hyakka. The complex orbital dance between these three bodies provides a natural laboratory for studying tidal forces, orbital resonance, and the long-term stability of multi-body systems. The detection of organic compounds, or tholins, on Haumea's surface also opens the door to exciting possibilities in astrobiology. Tholins are complex organic molecules that form when simpler compounds, such as methane and nitrogen, are exposed to ultraviolet radiation and cosmic rays. These molecules are believed to be precursors to the building blocks of life, such as amino acids and nucleotides. While Haumea's harsh surface environment is unlikely to support life as we know it, the presence of tholins raises questions about the chemical evolution of organic materials in the outer solar system. It also suggests that similar processes could occur on other icy worlds, such as Europa, Enceladus, or Titan, which are considered potential habitats for microbial life. Further exploration of Haumea could yield transformative insights into these scientific questions. A mission to Haumea would likely include a suite of advanced instruments, such as high-resolution cameras, spectrometers, and magnetometers, designed to study its surface, interior, and surrounding environment. Flyby missions, similar to NASA's New Horizons encounter with Pluto, could map Haumea's surface features, analyze its composition, and measure the properties of its ring and moons. A more ambitious mission might involve an orbiter, which could spend months or even years collecting detailed data on Haumea's geology, magnetosphere, and thermal properties. The potential for comparative planetology is another compelling reason to study Haumea. By comparing Haumea with other dwarf planets like Pluto, Eris, and Makemake, scientists can develop a broader understanding of the processes that shape icy worlds in the Kuiper Belt. For example, while Pluto and Eris are characterized by their large atmospheres and complex surface chemistry, Haumea's unique features, its rapid spin, elongated shape, and ring system, offer a complementary perspective on the diversity of planetary evolution in this region. Haumea's study also has implications for exoplanet research. Many exoplanets discovered in distant star systems are thought to be icy or rocky bodies similar in size and composition to the Kuiper Belt's largest objects. By understanding the physical and chemical properties of Haumea, scientists can refine their models of exoplanet formation and behavior, particularly for planets located in the colder, outer regions of their star systems. Haumea thus serves as both a window into our own solar system's past and a guide for exploring planetary systems beyond. In addition to its scientific importance, Haumea captivates the imagination of the public and inspires a sense of wonder about the outer reaches of the solar system. Its elongated shape, shimmering icy surface, and mysterious ring evoke the kind of curiosity that has always driven human exploration. As scientists continue to unravel its secrets, Haumea reminds us of the boundless mysteries that await discovery in the vast expanse of space. Through its study, we deepen not only our understanding of the cosmos but also our appreciation for the complexity and beauty of the universe. Haumea stands as a testament to the intricate interplay of forces that have shaped our solar system over billions of years. Its rapid rotation, dynamic system of moons, and enigmatic surface composition challenge traditional models of planetary science, while opening new avenues for exploration and discovery. In studying Haumea, scientists are not merely piecing together the history of a single dwarf planet. They are uncovering the fundamental principles that govern the evolution of worlds, both within our solar system and beyond. Haumea's extraordinary features draw astronomers deeper into the mysteries of planetary science, serving as a gateway to understanding not just the outer solar system, but the very forces that shaped the universe. Its rapid spin, peculiar shape, and unexpectedly complex system challenge long-held theories and invite tantalizing questions about how such a unique object could have formed and evolved. Theories surrounding Haumea's creation are among the most debated in modern astronomy. One compelling hypothesis suggests that Haumea may have been part of a much larger protoplanet, which collided with another massive object early in the history of the solar system. The violence of this impact likely stripped away a significant portion of Haumea's mass, leaving behind the elongated, rapidly spinning body we see today. The debris from this event is thought to have coalesced into its moons, Haumea and Makemake, and the family of icy fragments scattered throughout the Kuiper belt. This idea not only explains Haumea's rapid rotation, but also aligns with observations of other collisional families within the belt. The high albedo of Haumea, driven by its crystalline water-ice surface, raises intriguing questions about its thermal history. Crystalline ice, as opposed to amorphous ice, requires a heat source to maintain its structure. Yet the Kuiper belt is one of the coldest regions in the solar system, making the persistence of such ice an anomaly. Could Haumea's interior still retain enough heat to periodically resurface its icy crust? If so, this would imply ongoing geological processes in a region once thought to be geologically dead. One possibility is that radioactive isotopes deep within Haumea's rocky core could provide a steady source of internal heat. Even trace amounts of isotopes like potassium-40, uranium-238, or thorium-232 could sustain low-level heating over billions of years, enough to influence the planet's surface over geological timescales. Alternatively, tidal interactions with its moons might generate localized heating, particularly if Haumea and Makemake once orbited much closer to Haumea. These interactions could create frictional forces within Haumea's interior, resulting in periodic episodes of melting and resurfacing. Adding to the intrigue, Haumea's ring presents a scientific enigma that has reshaped how astronomers think about small planetary bodies. Observations suggest the ring is made of icy particles that orbit in a remarkably stable configuration. This stability is surprising given Haumea's rapid rotation and elongated shape, both of which create complex gravitational forces. Models of the ring's dynamics indicate that it likely formed from material ejected from Haumea's surface, possibly during a past collision or through ongoing sublimation processes. The fact that the ring orbits close to Haumea's equatorial plane hints at a strong coupling between the planet's spin and the distribution of material around it. What makes Haumea's ring even more fascinating is its interaction with the planet's gravity field. Haumea's elongated shape creates an uneven gravitational potential, meaning that objects orbiting close to its surface experience varying degrees of pull depending on their position. This creates a dynamic environment where particles in the ring must maintain a delicate balance to avoid being flung outward or drawn inward. Studying this system offers new insights into how similar processes might occur around other small, rapidly rotating objects, both within and beyond our solar system. Moving beyond Haumea itself, the implications of its existence ripple through the field of planetary science. The Kuiper Belt, once thought to be a relatively quiet and uneventful region, is now seen as a hotbed of complex interactions. Haumea, along with other large Kuiper Belt objects like Eris, Makemake, and Quawar, reveals that this region is anything but static. Collisions, migrations, and even the formation of moon systems are ongoing processes, reshaping our understanding of the outer solar system. Haumea's discovery and classification as a dwarf planet also underscore the dynamic and evolving nature of astronomy. When Pluto was reclassified in 2006, it sparked a reevaluation of what constitutes a planet. Haumea's unique characteristics, its irregular shape, rapid rotation, and ring system, have expanded the conversation further, challenging scientists to refine their definitions and consider the incredible diversity of planetary bodies. One of the most tantalizing aspects of Haumea is its potential connection to other planetary systems. Astronomers have discovered thousands of exoplanets orbiting stars beyond our Sun, many of which are icy or rocky bodies similar in size and composition to Haumea. The processes that shaped Haumea, collisions, spin dynamics, and gravitational interactions, are likely at play in these distant systems as well. By studying Haumea, scientists can test models that may apply to planets forming around other stars, bridging the gap between our solar system and the broader galaxy. Advances in observational technology promise to revolutionize our understanding of Haumea in the coming decades. The James Webb Space Telescope, JWST, and next-generation ground-based observatories like the Extremely Large Telescope, ELT, will be capable of resolving finer details of Haumea's surface and ring system. These instruments will provide high-resolution spectra, revealing the precise chemical makeup of Haumea's ice and any organic compounds present. Such data could illuminate the role of complex chemistry in shaping the outer solar system, offering clues to the origins of life's building blocks. The possibility of a dedicated mission to Haumea also looms on the horizon. Such a mission could deploy state-of-the-art instruments to probe Haumea's internal structure, study its moons in detail, and capture close-up images of its surface and ring. In situ sampling of ring particles could provide direct evidence of their origin, while radar imaging could reveal hidden subsurface features. These efforts would not only enhance our understanding of Haumea, but also set the stage for exploring other distant, icy worlds. Perhaps the greatest mystery of Haumea is its ability to continuously surprise and challenge our understanding of the cosmos. Every new discovery, be it its moons, ring system, or peculiar shape, adds another layer of complexity to a body that defies simple categorization. Haumea is a reminder that the universe is full of wonders waiting to be uncovered, and that even the most distant and inaccessible objects can hold the key to profound scientific revelations. Its study is not just a journey to the edges of our solar system, but a quest to understand the forces that shape all planetary systems, including our own. Haumea's mysteries continue to captivate scientists, as each new observation seems to pose more questions than answers. Its existence as a fast-spinning, elongated dwarf planet challenges conventional models of planetary formation, particularly in the context of the Kuiper Belt. Most celestial bodies in this region are thought to have formed through the gradual accretion of smaller objects over millions of years. However, Haumea's unique characteristics suggest that its story is far more dramatic, involving catastrophic collisions, rapid evolutionary processes, and interactions with its surrounding environment that set it apart from its neighbors. One of the most exciting areas of ongoing research is the study of Haumea's internal structure. Based on its shape, density, and rotational speed, scientists believe that Haumea has a differentiated interior, with a dense rocky core surrounded by a thick mantle of water ice. This layered structure implies that Haumea once generated enough heat to allow heavy materials to sink to its center while lighter materials floated to the surface. The source of this heat remains a subject of debate. While radioactive decay within its core could explain some of the energy, it is also possible that the massive impact theorized to have shaped Haumea contributed a significant amount of heat, melting large portions of its interior. This differentiation has significant implications for Haumea's long-term evolution. A rocky core surrounded by an icy mantle would create a natural boundary where heat transfer occurs, driving processes like convection or even cryovolcanism. Cryovolcanism, or cold volcanism, involves the eruption of water, ammonia, or other volatile substances instead of molten rock. On Haumea, cryovolcanism could periodically refresh its surface, bringing fresh crystalline ice to the surface and explaining its high albedo. Such processes have been observed on other icy bodies, like Saturn's moon Enceladus, and their potential existence on Haumea raises fascinating questions about geological activity in the frigid reaches of the Kuiper Belt. Haumea's rapid rotation plays a crucial role in shaping its unique characteristics. Spinning at such an extraordinary speed, completing a full rotation every 3.9 hours, Haumea experiences intense centrifugal forces that distort its shape into a triaxial ellipsoid. This shape, combined with its density of approximately 2.6 g/cm superscript 3, suggests a composition that is denser than pure ice but less dense than a fully rocky body. These centrifugal forces may also affect the distribution of material within Haumea, potentially creating subsurface stresses and fractures. Such stresses could allow volatile substances trapped beneath the surface to escape, further contributing to surface renewal. Haumea's moons, Hayaka and Namaka, are key players in understanding its history and dynamics. Hayaka, the larger and more distant of the two, orbits Haumea in a nearly circular path and has a surface rich in water ice. This moon's composition and orbit suggest that it likely formed from material ejected during the hypothesized giant impact that shaped Haumea. Namaka, the smaller and closer moon, exhibits a more eccentric and irregular orbit, hinting at a complex gravitational interplay with Haumea and Hayaka. Over time, these interactions could have caused tidal heating within Haumea, potentially driving internal processes like the movement of ice and rock or the release of gases from the interior. The discovery of Haumea's ring added yet another layer of intrigue to this already extraordinary dwarf planet. Rings are typically associated with massive gas giants, where strong gravitational fields and complex orbital dynamics create stable environments for ring systems. The existence of a ring around Haumea suggests that even small, rapidly spinning bodies can maintain such structures under the right conditions. Observations indicate that Haumea's ring lies close to the planet's Roche limit, the distance within which tidal forces prevent particles from coalescing into a larger body. The particles in Haumea's ring are thought to be composed of water ice, and their size and distribution provide valuable clues about the processes that sustain the ring. Understanding the origin of Haumea's ring system requires considering its violent past. One possibility is that the ring formed from debris created by a collision with another Kuiper Belt object. Such an impact could have ejected material into Haumea's orbit, where it gradually settled into a stable ring. Another theory posits that the ring is made up of material that was ejected from Haumea's surface due to centrifugal forces caused by its rapid rotation. This would imply a continuous interaction between Haumea's surface and its surrounding environment, with material constantly being added to the ring. Haumea's composition, surface features, and moons are not the only elements that make it scientifically fascinating. Its orbit within the Kuiper Belt offers a glimpse into the dynamics of this distant region of the solar system. The Kuiper Belt is home to a wide variety of objects, ranging from small, icy bodies to larger dwarf planets like Pluto and Eris. These objects are remnants from the early solar system, preserved in a state that reflects the conditions of their formation. Haumea, however, stands out as an active participant in the ongoing evolution of this region. Its rapid rotation, dynamic moon system, and ring highlight the complex interactions that continue to shape the Kuiper Belt. The broader implications of Haumea's study extend to our understanding of planetary systems beyond the solar system. Exoplanets discovered in distant star systems often display characteristics similar to those of Kuiper Belt objects, including icy compositions and orbits in the colder, outer regions of their systems. By studying Haumea, scientists can refine models of planetary formation and evolution that may apply to these distant worlds. Haumea serves as a natural laboratory for testing theories about the behavior of ice, rock, and volatile materials under extreme conditions. As technology advances, the opportunities to explore Haumea in greater detail grow more promising. Space telescopes equipped with advanced imaging and spectroscopy capabilities could resolve finer details of Haumea's surface and ring system, revealing its chemical composition and geological history. A dedicated spacecraft mission could go even further, capturing high-resolution images, mapping its gravity field, and even sampling particles from its ring. Such a mission would provide an unprecedented look at one of the most unique objects in the solar system, offering answers to questions that continue to challenge our understanding of planetary science. Haumea's story is far from complete. Each new discovery adds a layer of complexity to our understanding of this enigmatic world, reminding us that the solar system is full of surprises. Haumea's rapid rotation, elongated shape, icy surface, and dynamic system of moons and rings make it a scientific treasure trove, offering insights into the processes that have shaped not only our corner of the galaxy, but also the broader universe. As scientists continue to study Haumea, they are not just exploring a distant dwarf planet. They are unlocking the secrets of how worlds form, evolve, and interact on a cosmic scale. Haumea is a mystery wrapped in ice, spinning relentlessly in the frozen abyss of the Kuiper Belt. It defies expectations, a celestial enigma that refuses to fit neatly into the categories of planetary science. Every observation deepens the intrigue, leaving astronomers grappling with questions that stretch the boundaries of our understanding. What ancient cosmic drama sculpted this oblong, crystalline world, and what secrets lie hidden beneath its shimmering, icy surface? Imagine a collision so cataclysmic that it didn't just shatter a primordial world but reshaped it entirely, sending fragments spiraling into the void. Haumea is the survivor of such an event, its rapid spin a scar from the unimaginable force of the impact. This is no ordinary collision victim. Haumea carries the hallmarks of an active and dynamic history, a history that may still be unfolding in ways we are only beginning to glimpse. Its crystalline water-ice surface gleams with an unnatural brightness, a mirror to the sun's faint light that shouldn't exist in a place this cold. How is this possible? Crystalline ice should have long since degraded into a dull, amorphous state under the unrelenting bombardment of cosmic radiation. The surface, scientists suspect, may be alive, renewed by mysterious processes deep within the dwarf planet's interior. Could there still be enough warmth in Haumea to stir its icy mantle, bringing fresh material to the surface? If so, Haumea isn't just an icy relic. It's a world in motion, defying the stillness expected of its kind. And then there's the ring. A perfect circle of icy particles orbits Haumea like a frozen halo, a feature astronomers never anticipated around such a small object. Where did it come from? Was it born in the same violent impact that shaped Haumea itself? Or is it a product of its incredible spin, flinging debris into space? The ring seems impossibly stable, as if tethered by invisible forces we have yet to understand. Studying it could unlock secrets about not just Haumea but every planetary ring in the solar system and beyond. Adding to this celestial puzzle are Haumea's moons, Hayaka and Namaka. They aren't merely companions. They're witnesses to the dwarf planet's turbulent history. Hayaka, with its icy surface and steady orbit, seems to whisper of a time when material was torn from Haumea and coalesced into a satellite. Namaka, in contrast, dances erratically, its irregular orbit hinting at ancient gravitational battles. What stories do these moons hold about their enigmatic host? And what of the mysterious organic compounds suspected to coat parts of Haumea's surface? Tholins, complex molecules forged in the harsh interplay of ultraviolet light and cosmic rays, could be present. These are the building blocks of life, scattered across the most hostile environments. Could Haumea, in its distant isolation, hold clues to the chemistry that led to life on Earth? Or even point toward what might be possible in alien star systems? The intrigue deepens when we consider Haumea's role in the broader narrative of the Kuiper Belt. It isn't alone. Scattered around it are fragments, icy, rocky bodies that seem to have been born from Haumea's destruction. They form a family, orbiting the sun in similar paths, a cosmic fingerprint of the cataclysm that reshaped this corner of the solar system. Studying these fragments is like piecing together a shattered vase. Each piece tells part of the story, but the full picture remains elusive. Haumea isn't just a dwarf planet. It's a challenge. It defies the rules of celestial mechanics, pushes the limits of our understanding of icy worlds, and holds tantalizing clues about the forces that shaped not only the solar system but perhaps countless others. Its ring beckons like a frozen whisper from the void, its spin a dizzying testament to the violence of its past, and its surface a shimmering question mark for astronomers. But the most tantalizing question of all may be this: what if Haumea is just the beginning? What if the Kuiper Belt, with its thousands of icy worlds, holds even stranger secrets? Haumea is a gateway to the unknown, a world that demands exploration. And as we uncover its mysteries, we might find answers to questions we haven't even thought to ask yet. The allure of Haumea lies not just in its icy surface or its rapid spin, but in the secrets it seems determined to keep. As telescopes capture faint glimpses of its distant, distorted form, scientists are haunted by questions that seem almost taunting. Why does Haumea spin so quickly, almost to the brink of tearing itself apart? What ancient forces flung it into this perpetual dance? And could its fate be a warning about the fragility of other celestial bodies? Its ring, hauntingly perfect, defies the odds. Unlike Saturn's grand displays or Neptune's faint arcs, Haumea's ring feels personal, almost intimate, a frozen echo of something violent yet beautiful. Could it be the remnants of an ancient moon, shattered and drawn into the dwarf planet's orbit? Or is it debris continually being shed by Haumea itself, a visible trace of the centrifugal forces working against its icy crust? As astronomers map the ring's structure, they confront the possibility that Haumea is actively reshaping its surroundings even now, creating a dynamic system in one of the solar system's coldest, most distant regions. The deeper mystery lies within. Haumea's elongated shape hints at immense pressures and forces locked in its interior. Imagine a rocky core cloaked in a vast, frozen mantle, where the boundary between rock and ice may not be as static as it seems. Could heat from radioactive decay still linger deep within, creating pockets of liquid water or slush? And if so, what strange, alien chemistry might be taking place in those hidden depths? While the odds of life as we know it are slim, the possibility of complex prebiotic chemistry cannot be dismissed. In a universe where life has arisen once, even the faintest hint of chemical complexity carries profound implications. The moons Hayaka and Namaka orbit Haumea like silent sentinels, their trajectories whispering of gravitational battles fought long ago. Hayaka, with its icy sheen, is a nearly perfect reflection of Haumea's surface, suggesting it was born from the same material. Namaka, more erratic in its orbit, could hold the scars of an orbital resonance that no longer exists, a relic of the chaotic early days of Haumea's formation. Studying their motions is like decoding a forgotten language, where every gravitational quirk and orbital anomaly hints at the violent story of Haumea's creation. And then there's the family, dozens of icy fragments scattered throughout the Kuiper belt that share Haumea's spectral signature. These fragments are more than debris. They are clues, pieces of a celestial puzzle that astronomers are racing to solve. Why do these objects orbit in similar paths? And why do they all bear the unmistakable mark of water ice? Could these fragments have once formed a much larger body, now lost to time? Or are they evidence of a cosmic chain reaction, a series of collisions that set the stage for the Kuiper belt as we know it? Haumea also forces us to confront broader, more unsettling questions about the solar system. How many other dwarf planets and small celestial bodies have stories just as dramatic, hidden in the cold darkness beyond Neptune? Are there even stranger worlds waiting to be discovered, with rings, moons, or features we can't yet imagine? Haumea is a reminder that the solar system is far more complex and dynamic than we once thought. A realm of endless surprises that challenges our assumptions about how planets, moons, and rings form and evolve. The potential for exploration looms large. Imagine a spacecraft arriving at Haumea, its cameras capturing the glint of sunlight off its icy surface, and its instruments probing the chemistry of its ring. A close flyby could reveal cracks and fissures in its surface, places where internal processes might have exposed ancient material. Sampling particles from its ring could uncover their origin, fragments of Haumea's crust or relics of an ancient impact. Such a mission would not just answer lingering questions about Haumea, it would redefine our understanding of icy worlds across the galaxy. And yet, Haumea's mysteries feel like they are only deepening. The more we learn, the more questions emerge, as if the dwarf planet itself resists easy categorization. It exists on the edge of the solar system of stability and of what we think is possible for a small icy world. Haumea is not merely a passive remnant of the past, but an active, evolving body that defies expectations at every turn. The ultimate intrigue lies in the unknown. What if Haumea's rapid spin eventually reaches a breaking point? Could it shed more material, creating new moons, or even expanding its ring? What if its interior harbors reservoirs of liquid water, heated by processes we have yet to uncover? And what if its family of fragments is just the beginning, a clue to even larger events that have shaped the outer solar system? Haumea is more than a dwarf planet. It's a story of creation, destruction, and persistence. Its icy surface, shimmering in the distant sunlight, seems almost to beckon, inviting us to uncover its secrets. And as we peer deeper into the Kuiper belt, searching for answers, Haumea reminds us that the universe is vast, mysterious, and infinitely surprising. The enigma of Haumea is a siren call for explorers of the cosmos. It spins, defying the quiet vastness of the Kuiper Belt, its elongated form and glimmering ice a testament to the chaos of its creation. But what if the story of Haumea is not yet finished? What if this distant dwarf planet, seemingly frozen in time, holds the potential for future cosmic drama? Consider its rapid rotation, an extraordinary feature that may eventually push Haumea to its structural limits. While it has endured for billions of years, the centrifugal forces acting on its surface create immense tension. Could there come a day when a piece of Haumea breaks free, flung into space by the sheer velocity of its spin? Such an event would not only add new fragments to the Haumea family, but also alter the dynamics of its ring and moons, reshaping its system in ways we can only theorize. The interaction between Haumea and its ring is another frontier of intrigue. The ring's stability suggests a finely tuned balance, yet its precise origin remains elusive. Are the icy particles a constant reminder of Haumea's violent past, or do they represent an ongoing process, a steady shedding of material as the dwarf planet spins? If the latter is true, Haumea may be in a perpetual state of renewal, its ring evolving over time in response to the gravitational influences of its moons and its own spin. Future observations may reveal whether Haumea's ring is static or dynamic, offering insights into the forces at play in this icy ballet. Haumea's moons, Hayaka and Namaka, are more than mere satellites. They are the keepers of its secrets. Hayaka, with its bright icy surface, seems almost serene, orbiting at a distance that allows it to remain largely untouched by the gravitational tug-of-war closer to Haumea. Namaka, on the other hand, is chaotic, its orbit a reflection of ancient disturbances. Could Namaka's erratic behavior hold the key to understanding the early interactions that shaped Haumea's system? Perhaps its gravitational dance with Hayaka and Haumea is still unfolding, creating subtle shifts that ripple across the entire system. But the greatest mysteries may lie beneath Haumea's icy crust. While its surface dazzles with crystalline ice, its interior could harbor layers of untapped potential. Imagine a hidden ocean, warmed by the residual heat of radioactive decay or the friction of tidal forces. Such an ocean, buried beneath kilometers of ice, would be an isolated world, untouched by sunlight yet teeming with chemical potential. Could it contain the building blocks of life, locked away in the cold depths of this distant dwarf planet? While direct exploration of Haumea's interior remains a distant dream, its study could inspire future missions to icy moons and planets across the solar system. Haumea's orbit through the Kuiper Belt is another piece of the puzzle. Its inclination and eccentricity suggest a tumultuous past, possibly shaped by interactions with Neptune or other massive bodies in the outer solar system. Such gravitational encounters could have influenced not only Haumea's orbit but also its spin and the distribution of its family of fragments. By tracing the orbital histories of Haumea and its kin, scientists hope to reconstruct the events that led to its current state. In doing so, they may uncover new clues about the broader dynamics of the Kuiper Belt and the role of giant planets in shaping its structure. The implications of Haumea's study extend beyond the Kuiper Belt. As astronomers discover more exoplanets, they are finding worlds that mirror the characteristics of Haumea: icy, fast-spinning, and orbiting far from their parent stars. By unraveling the mysteries of Haumea, we gain a template for understanding these distant worlds, many of which may be too far away for direct observation. Haumea, in this sense, is a bridge between our solar system and the wider galaxy, offering a glimpse into the universal processes that shape planetary bodies. The story of Haumea is a reminder that the cosmos is full of surprises. Its existence challenges assumptions, pushing scientists to rethink what is possible in the outer solar system. It is a testament to the resilience of planetary bodies, enduring billions of years of gravitational forces, impacts, and cosmic radiation, all while maintaining its dynamic, enigmatic character. As humanity's reach into space extends further, Haumea beckons as a target for future exploration. A mission to this icy world could answer questions that have eluded us for decades. What is the precise composition of its ring? How do its moons interact with each other and with Haumea? And perhaps most tantalizingly, what lies beneath its surface? A spacecraft could orbit Haumea, mapping its gravitational field, analyzing its surface composition, and even capturing high-resolution images of its moons and ring. Such a mission would not only illuminate Haumea's mysteries, but also pave the way for exploring other icy worlds, from the Kuiper Belt to exoplanetary systems. Until then, Haumea spins on, its secrets intact, daring us to look closer. It is a reminder of the beauty and complexity of the universe, a beacon in the darkness of the Kuiper Belt that challenges us to never stop asking questions. What will we discover next about this enigmatic world? The possibilities are as vast and boundless as space itself. Haumea, suspended in the vast expanse of the Kuiper Belt, is more than just a distant dwarf planet. It's a storyteller. Its every characteristic, from its dizzying rotation to its icy ring, seems to whisper fragments of a narrative that stretches back to the birth of the solar system. But these fragments are incomplete, like pages torn from an ancient book. To piece them together, we must look beyond what we know, daring to imagine the unimaginable. What if Haumea isn't just the product of a single cataclysmic event, but a survivor of multiple cosmic dramas? Each twist of its elongated form, each icy fragment in its ring, may tell of eons of impacts, gravitational disruptions, and tidal forces that molded it into the object we see today. Its rapid spin, an anomaly in itself, raises the question: how much longer can Haumea endure this relentless pace? The centrifugal forces at work threaten to stretch it to its limits, hinting that this story is far from over. Could Haumea still be in the process of transforming, shedding pieces of itself into the void, slowly altering its shape and structure as it dances through space? Then there's the haunting possibility of what lies beneath its icy crust. In the freezing darkness of the Kuiper Belt, where sunlight is a mere whisper, Haumea could harbor secrets beneath its surface. Layers of ice could insulate a hidden world, perhaps a subsurface ocean kept liquid by internal heat. Such oceans have been theorized or discovered on moons like Europa and Enceladus, but on Haumea, the stakes feel even higher. Could such an ocean, locked beneath kilometers of ice, hold the chemical precursors of life? Could it serve as a template for understanding the potential habitability of icy exoplanets orbiting distant stars? Haumea's ring adds another layer of intrigue. Its very existence challenges the understanding of where and how ring systems can form. Unlike the majestic rings of Saturn or the subtle arcs of Neptune, Haumea's ring is a stark, icy reminder of a celestial process we've barely begun to comprehend. Every particle in that ring is a messenger from the past, perhaps a fragment of Haumea itself or a relic of an ancient collision. Studying the ring's composition, motion, and interaction with Haumea's gravity will not only unravel its origins, but could reveal new principles of celestial mechanics that apply to planets and moons across the universe. And what of Haumea's family? These icy siblings scattered across the Kuiper Belt are like echoes of the dwarf planet's violent past. They orbit the Sun in similar paths, carrying with them the spectral signature of Haumea's icy surface. Together, they form a cosmic breadcrumb trail, leading us back to the moments of collision and chaos that birthed them. By studying these fragments, scientists can reconstruct Haumea's history, piece by piece, gaining insights into the broader dynamics of the Kuiper Belt and the violent forces that shaped our solar system. But perhaps the greatest intrigue lies in Haumea's potential to surprise us. The more we study it, the more it defies easy classification. Is it merely a relic of the past, or is it a dynamic, evolving world? Could it, against all odds, be active today, its surface reshaping itself in slow, deliberate ways, its ring and moons bearing witness to ongoing interactions? Haumea's rapid spin, its shimmering ice, its chaotic moons, they all hint at a story still unfolding, a mystery waiting to be unraveled by the next generation of explorers. Haumea invites us to dream. It challenges us to look beyond the obvious, to question what we think we know about planets, moons, and the forces that govern them. It's a world that reminds us of the fragility and resilience of celestial bodies, of the delicate balance between destruction and creation. And as we gaze at this distant, icy world, spinning on the edge of the solar system, we can't help but wonder, what will we discover next? The universe is vast, and Haumea is just one of its many riddles, a beacon that draws us ever closer to the truth hidden in the stars. Haumea, a distant world sculpted by forces beyond comprehension, stands as a silent witness to the violent and creative processes that have shaped the universe. Its story is not one of mere existence, but of resilience, transformation, and the cosmic ballet that links every particle of the solar system. As we peer into the depths of the Kuiper Belt, Haumea's elongated, icy body emerges as a testament to the unrelenting forces that govern celestial mechanics, a masterpiece born from chaos. Haumea's rapid rotation is an enigma wrapped in physical impossibility. It spins so quickly, once every 3.9 hours, that its form stretches into a triaxial ellipsoid, an egg-shaped defiance of gravity's preference for spherical symmetry. This rate of rotation is far beyond what we observe in most celestial bodies of similar size, raising tantalizing questions. How did Haumea reach such a velocity without tearing itself apart? The leading theory suggests a catastrophic impact with another Kuiper Belt object billions of years ago, a collision so violent that it sent debris scattering into space while spinning Haumea like a cosmic top. Yet, this explanation only scratches the surface. Could there have been multiple collisions? What other unknown forces might have contributed to this relentless spin? This rapid rotation doesn't just shape Haumea's form. It governs its entire system. The centrifugal force at work distorts its gravitational field, creating a unique dynamic environment for its ring and moons. Haumea's ring, an impossibly stable structure of icy particles, orbits close to its equatorial plane, held in place by the delicate balance of gravitational and rotational forces. How such a structure remains intact over billions of years is a puzzle in itself. Did the ring form immediately after the catastrophic impact that birthed Haumea's spin? Or is it the result of ongoing processes? Perhaps material being ejected from Haumea's surface due to its rotational velocity? Every particle in that ring holds a clue, and understanding its origins could unlock secrets not just about Haumea, but about the formation of rings around planets and moons throughout the cosmos. The moons, Haumea and Makemake, add further complexity to this dynamic system. Haumea, the larger moon, orbits Haumea at a distance of nearly 50,000 kilometers, its icy surface reflecting sunlight like a distant echo of Haumea itself. Makemake, closer and more chaotic, moves in an irregular orbit, as if haunted by gravitational disturbances from its sibling and Haumea. These moons are not mere companions. They are key players in the story of Haumea's formation and evolution. The interplay of their orbits reveals a history of tidal forces and orbital resonances, a gravitational tug-of-war that may still be unfolding today. Studying their trajectories and compositions is like reading the final chapters of a book, knowing that earlier pages hold the answers to questions yet unresolved. Beneath Haumea's shimmering surface lies another mystery. Spectroscopic analysis reveals that its icy crust is crystalline, a structure that should not exist in the cold vacuum of the Kuiper belt. Over time, cosmic radiation would degrade crystalline ice into a dull, amorphous state. Yet Haumea gleams with brilliance, suggesting a surface that is constantly renewed. What drives this renewal? Internal heating from radioactive decay within Haumea's rocky core could be one explanation. Alternatively, tidal interactions with its moons might generate enough friction to melt subsurface ice, driving eruptions of water or slush to the surface in a process akin to cryovolcanism. Such resurfacing would periodically expose fresh ice, explaining its youthful appearance. If this is true, Haumea is not just a relic of the past. It is an active world, quietly evolving in the cold isolation of the Kuiper belt. The possibility of subsurface oceans beneath Haumea's icy crust elevates its intrigue to another level. These oceans, if they exist, would be insulated from the frigid environment by kilometers of ice, creating a stable environment for complex chemical processes. Could these hidden seas harbor the building blocks of life? On Earth, life thrives in the unlikeliest of places. Deep-sea hydrothermal vents, subglacial lakes, and extreme environments where sunlight never penetrates. If similar conditions exist on Haumea, even the faintest signs of organic chemistry could redefine our understanding of habitability in the universe. Haumea's story is inseparable from the broader narrative of the Kuiper belt, a vast and enigmatic region filled with icy bodies that hold the keys to the early solar system. The discovery of Haumea's family of fragments, icy objects that share its orbital path and spectral properties, suggests a violent origin. These fragments are not random. They are pieces of a cosmic puzzle, scattered remnants of a once larger body that was torn apart by unimaginable forces. Studying these fragments provides a window into the conditions of the Kuiper belt during its formative years, revealing the scale and frequency of collisions that shaped this distant frontier. The Kuiper belt itself is a realm of wonders waiting to be discovered. Beyond Haumea lie countless other worlds, each with its own story. Dwarf planets like Eris, Makemake, and Quawar challenge our definitions of planetary bodies, offering glimpses into the diversity of the solar system's outer reaches. Haumea stands out among them, not just for its unique shape and spin, but for the sheer number of unanswered questions it poses. It is a reminder that even in the cold, dark outskirts of the solar system, there is activity, evolution, and complexity beyond our wildest imaginings. And then there is the ultimate question: what does Haumea mean for our place in the cosmos? As we discover exoplanets in other star systems, many of them icy, fast-spinning worlds, Haumea serves as a template for understanding the forces at play on distant planets. By studying Haumea, we are not just learning about our own solar system, we are building the tools to explore and understand the galaxy. Haumea is not merely an object of scientific study, it is an invitation to wonder. Its secrets are buried beneath layers of ice and veiled in the complexities of its motion, composition, and history. But these secrets will not remain hidden forever. As our technology advances, as we send spacecraft to the outer reaches of the solar system, we edge closer to uncovering the full story of this remarkable world. Until then, Haumea spins on, a glittering enigma on the edge of the solar system, challenging us to look deeper, to dream bigger, and to never stop seeking the unknown. Haumea continues to orbit the Sun as both a tantalizing mystery and a bold reminder of the dynamic, chaotic forces that shaped the early solar system. But this icy world, seemingly isolated in the vastness of the Kuiper Belt, is far from static. It holds within it a potential for discovery that could redefine what we know about the building blocks of planets, moons, and perhaps even life itself. Haumea's dazzling, crystalline surface seems to challenge the natural order of time and entropy. In the cold vacuum of space, where cosmic radiation should erode and darken its icy facade, Haumea instead reflects light with youthful brilliance. Could this defiance of natural decay hint at a subsurface reservoir of activity? Imagine geysers of water vapor or slush erupting from beneath its crust, driven by hidden heat sources deep within the dwarf planet. These cryovolcanic outbursts could not only refresh the surface but also eject material into space, replenishing its mysterious ring. The possibility of internal heating raises profound questions. If radioactive isotopes within Haumea's core are decaying, they could generate enough warmth to maintain a semi-liquid layer beneath the icy exterior. Alternatively, tidal forces exerted by its moons, particularly during periods of orbital resonance, might provide the necessary energy to melt portions of its interior. Such a scenario transforms Haumea from a frozen relic into a living world, where internal dynamics shape its surface and surrounding environment. But what if Haumea's heat is not entirely internal? The interactions between its surface and the vacuum of space could create unique thermodynamic phenomena. Sublimation, where ice transitions directly from a solid to a gas, might be occurring on Haumea's surface. If so, the escaping gas could carry fine particles with it, contributing to the material in its ring. Such a process would suggest that Haumea's ring is not merely a relic of the past but an active feature, evolving in real time. Observing changes in the ring's composition and density over decades could provide a rare glimpse into the ongoing processes shaping this distant world. Haumea's moons add layers of complexity to its system. Hayaka, with its steady orbit and icy surface, appears calm and orderly, a stark contrast to Namaka's erratic path. Yet beneath this seeming tranquility, Hayaka may hold secrets about Haumea's past. If its surface contains traces of materials not found on Haumea, it could indicate that the moon captured debris from other collisions or interactions in the Kuiper Belt. Meanwhile, Namaka's chaotic behavior suggests a history of gravitational disruptions. Its current orbit is a clue, a dynamic puzzle piece that, when understood, could reveal the violent forces that shaped this system billions of years ago. Haumea's enigmatic ring challenges the boundaries of our understanding of celestial mechanics. Unlike the dense, towering rings of Saturn or the faint arcs of Neptune, Haumea's ring exists in a fragile balance, held together by forces we are only beginning to comprehend. How did this ring form, and why has it persisted? Is it the result of a single catastrophic event? A piece of Haumea itself torn free by rotational forces? Or is it a dynamic feature, constantly fed by material ejected from Haumea's surface? If the latter is true, then Haumea could be in the process of reshaping its own environment, creating a system of rings and moons that evolves over time. And then there are the fragments, the scattered pieces of the Haumea family, drifting through the Kuiper belt like whispers of a forgotten past. These icy bodies, with their shared spectral properties and orbital paths, are the remnants of a cosmic explosion. Studying them is like examining shards of ancient pottery, each fragment holding clues to the greater whole. Together, they paint a picture of Haumea's violent birth, revealing the forces that sculpted its unique shape and set it spinning at breakneck speed. But the family's existence raises even deeper questions. Was Haumea once part of an even larger body, perhaps a proto-dwarf planet that shattered in a series of collisions? If so, these fragments are more than debris. They are witnesses to the chaotic dance of formation that defines the Kuiper belt. Haumea's story also forces us to consider the broader implications for planetary science. If such a dynamic, active world can exist in the cold outer reaches of our solar system, what does that say about the potential for similar worlds elsewhere? As we discover exoplanets orbiting other stars, many of them icy bodies in distant orbits, Haumea serves as a model for understanding their behavior. Its rapid spin, ring system, and moons offer a blueprint for interpreting the physical and chemical processes that shape exoplanets in similar environments. The Kuiper belt itself becomes a stage for exploration, its icy worlds offering endless opportunities for discovery. Haumea is just one of many dwarf planets, each with its own unique features and mysteries. Together, these objects form a mosaic of the solar system's early history, preserving the conditions and materials that existed when the planets were young. By studying Haumea and its neighbors, we can piece together a narrative of how the outer solar system evolved, from the chaotic collisions of its infancy to the delicate balances of its present. As we look to the future, Haumea beckons as a target for exploration. A spacecraft mission to this distant world would be a monumental achievement, offering the chance to capture high-resolution images of its surface, ring, and moons. Instruments could probe its interior, searching for signs of liquid water or thermal activity. Sampling particles from its ring could reveal their composition and origin, providing direct evidence of the processes shaping Haumea today. Such a mission would not only answer long-standing questions but also open new avenues of inquiry, inspiring a deeper understanding of the Kuiper belt and the solar system as a whole. Haumea spins on, a frozen sentinel on the edge of the solar system, carrying the secrets of its past while shaping its future. Its story is not just one of survival but of transformation, a tale of creation and destruction, of balance and chaos. As our technology advances and our curiosity deepens, Haumea promises to reveal its secrets, one enigmatic turn at a time. It is not merely a distant world. It is a challenge, an inspiration, and a reminder that the universe is far more complex and beautiful than we ever imagined. Haumea spins relentlessly, a celestial anomaly that resists simplicity. It resides in the cold embrace of the Kuiper belt, yet it burns brightly in the imaginations of astronomers, theorists, and dreamers alike. With every turn, it challenges our understanding of physics, chemistry, and the fragile balance of forces that govern the universe. Its shimmering surface, dynamic moons, and enigmatic ring system make it a beacon of intrigue. A frozen laboratory where the rules of the cosmos are laid bare, waiting to be deciphered. What makes Haumea extraordinary is not just its rapid spin or its elongated shape, but the intricate interplay of forces that hold it together. It's a world seemingly at odds with itself. The centrifugal forces acting upon it, driven by its breakneck rotation, work tirelessly to fling material outward, while its own gravity pulls inward, trying to maintain cohesion. This delicate balance creates a state of tension that has persisted for billions of years. But could this balance one day fail? If Haumea's rotation accelerates even slightly, or if external forces disturb its equilibrium, the dwarf planet could undergo a catastrophic event, shedding material into space and reshaping itself entirely. Such an event could provide a real-time glimpse into the processes that shaped not only Haumea but also countless other objects in the early solar system. It might offer answers to the origin of Haumea's existing ring, an icy halo that seems impossibly stable yet teems with questions. The particles in this ring are not random. They follow specific paths, locked into orbits that suggest a history of gravitational interactions and subtle dynamics. Could they hold the molecular fingerprints of Haumea's crust? Or perhaps even older material from the Kuiper belt, predating Haumea itself? Each particle is a messenger from another time, a piece of cosmic history suspended in perpetual motion. The surface of Haumea, glimmering with crystalline water ice, seems almost alive in its defiance of entropy. Such ice should not exist in a region as cold and irradiated as the Kuiper belt. Cosmic rays and ultraviolet radiation from distant stars should have rendered it amorphous long ago. And yet Haumea gleams. This raises profound questions about its internal activity. Could heat from its rocky core, perhaps generated by the slow decay of radioactive isotopes, be driving convection beneath its icy mantle? Such movement could bring fresh ice to the surface, constantly renewing its crystalline sheen. If this is the case, the implications are staggering. Haumea might not be the inert, frozen world it appears to be, but a dynamic body with ongoing geological processes. These processes might include cryovolcanism, where subsurface water or slush erupts through cracks in the crust, only to freeze instantly in the vacuum of space. Such eruptions could explain not only the crystalline nature of the surface but also the presence of the ring, as ejected material might accumulate in stable orbits around the dwarf planet. The moons of Haumea add another layer of complexity to this dynamic system. Hayaka, the larger of the two, is a fascinating world in its own right. Its surface, rich in water ice, mirrors that of Haumea, suggesting a shared origin. But Hayaka's near-circular orbit and apparent stability contrast sharply with Namaka, its smaller, more erratic sibling. Namaka's irregular path hints at past gravitational interactions, perhaps even orbital resonances with Hayaka or disturbances caused by Haumea's rapid spin. These interactions may have generated tidal forces within Haumea, heating its interior and driving the processes that renew its surface. The history of Haumea's system is written in these moons, its ring, and the family of fragments scattered across the Kuiper belt. This family, a collection of icy bodies with spectral properties nearly identical to Haumea, represents the shattered remnants of a larger whole. They are not random objects but a coherent group, orbiting the sun in harmony as if paying homage to the collision that created them. Each fragment is a clue, a piece of the puzzle that scientists are painstakingly assembling. Together, they tell a story of violence, survival, and transformation. But what if Haumea's story is not unique? What if other worlds in the Kuiper belt or beyond share similar histories? As telescopes peer deeper into space, they are uncovering icy planets and moons in distant star systems, many of which bear striking resemblances to Haumea. These discoveries suggest that the processes that shaped Haumea are not isolated to our solar system but are part of a universal pattern. Haumea becomes a Rosetta Stone for understanding the behavior of icy bodies throughout the cosmos, a touchstone for studying the forces of collision, rotation, and gravitational interaction on a galactic scale. The potential for exploration of Haumea is boundless. A dedicated mission to this distant world could transform our understanding of icy bodies. Imagine a spacecraft equipped with advanced imaging systems, spectrometers, and even cryogenic sampling instruments, arriving in Haumea's orbit. It could map the dwarf planet's surface in exquisite detail, capturing the cracks, fissures, and potential cryovolcanic vents that hint at its internal processes. Probes could analyze the composition of its ring, unraveling its origins and evolution. And landers might even touch down on Haumea or one of its moons, drilling into the ice to search for signs of past or present activity. The implications of such a mission would extend far beyond Haumea itself. The data collected could redefine our models of planetary formation and evolution, offering insights that apply to icy moons like Europa and Enceladus, to distant exoplanets, and even to the earliest epochs of the solar system. Haumea, in its shimmering isolation, holds the potential to illuminate not just its own mysteries, but the mysteries of countless other worlds. For now, Haumea spins on, an icy enigma on the edge of our solar system, daring us to look closer. Its beauty is not just in its shimmering surface or its haunting ring, but in its complexity. A complexity that reminds us that the universe is full of surprises, waiting to be discovered. Haumea is more than a dwarf planet. It is a challenge, a wonder, and a beacon of curiosity, inviting us to unravel its secrets one discovery at a time. Haumea's enigmatic presence in the Kuiper Belt is a testament to the resilience and complexity of celestial objects that dwell in the outermost reaches of our solar system. It is a cosmic storyteller, spinning tirelessly, whispering tales of ancient collisions, hidden internal processes, and an ever-evolving relationship with its surroundings. Each rotation, each icy glint off its surface, is a fragment of a larger narrative that invites us to explore deeper, ask more questions, and push the boundaries of what we know. The dwarf planet's unique shape is a direct consequence of its incredible rotation speed. A speed so fast it has distorted its body into an ellipsoid, far from the spherical equilibrium typically seen in celestial objects of its size. This deformation is a window into the physics of rotational dynamics under extreme conditions. Haumea's rapid spin stretches its mass outward, generating centrifugal forces that test the limits of its structural integrity. Scientists theorize that if Haumea were to spin even slightly faster, these forces might overcome its gravity, causing chunks of its surface to break away, forming additional debris or reshaping its ring system. Is Haumea already nearing this breaking point, or could it stabilize indefinitely in this precarious balance? The existence of Haumea's ring further complicates our understanding of how such features form and persist. Unlike the massive gas giants whose rings are sustained by vast gravitational wells and shepherd moons, Haumea's much smaller mass and rapid spin create a dynamic and delicate environment for its ring. Simulations of Haumea's ring dynamics suggest that the particles orbiting the dwarf planet are locked in a resonance with its rotation, stabilized by the very forces that seem poised to disrupt them. But the precise origin of these particles remains unclear. Were they ejected from Haumea's surface, torn free by its incredible spin? Or are they remnants of an ancient collision, preserved in this icy halo by some yet unknown mechanism? Haumea's moons, Hayaka and Namaka, act as gravitational counterpoints in this complex system. Hayaka, orbiting farther from Haumea, is relatively stable, but Namaka's erratic path suggests a history of significant gravitational interactions. This imbalance between the moons may have influenced the development of Haumea's ring, either by stabilizing its particles through subtle resonances or by contributing to the chaotic forces that prevent material from coalescing into additional moons. Together, these moons form a dynamic trio with Haumea, their motions a silent record of billions of years of orbital evolution. As scientists delve deeper into Haumea's mysteries, the crystalline water ice on its surface remains one of the most compelling puzzles. This ice, which glitters under the faint light of the sun, should not exist in the Kuiper Belt, where cosmic rays and ultraviolet radiation degrade crystalline structures over time. The persistence of this ice suggests ongoing resurfacing processes, likely driven by internal activity. But what mechanisms could keep Haumea geologically active in such a cold and distant region of the solar system? Radioactive decay within Haumea's rocky core is one possibility. Even small amounts of radioactive isotopes could produce enough heat to maintain a subsurface ocean or slushy layer beneath the ice. This internal warmth could drive convection currents, slowly cycling material to the surface and creating the cracks and fissures that might act as vents for cryovolcanism. Alternatively, tidal forces from its moons could generate enough friction within Haumea to keep parts of its interior warm. These processes, while speculative, paint a picture of a world that is far from static. A world where ice flows, cracks form, and energy moves in ways that defy the expectations of a frozen, isolated dwarf planet. The potential for a hidden ocean beneath Haumea's icy crust is particularly tantalizing. Subsurface oceans have been confirmed on moons like Europa and Enceladus, where they are thought to interact with rocky cores to create complex chemical environments. Could a similar ocean exist on Haumea, shielded from the cold vacuum of space by its icy shell? If so, it might contain the building blocks of life, formed in conditions entirely unlike those on Earth. Haumea's extreme distance from the Sun makes it an unlikely candidate for habitability in the traditional sense, but its internal chemistry could provide clues about the potential for life in other icy worlds, both in our solar system and beyond. Haumea's family of fragments scattered across the Kuiper Belt adds yet another layer to its story. These objects, sharing similar orbits and spectral properties, are the remnants of a massive collision that likely shaped Haumea's current form. By studying these fragments, astronomers hope to reconstruct the events of this ancient impact, its energy, its aftermath, and the processes that allowed Haumea to emerge as one of the fastest rotating objects of its kind. Each fragment is a time capsule, preserving information about the composition and conditions of the early solar system. Together, they form a mosaic that, when pieced together, reveals the violent, dynamic history of the Kuiper Belt. The implications of Haumea's study extend far beyond the Kuiper Belt. As telescopes detect more exoplanets, many of which are icy bodies in distant orbits around their stars, Haumea serves as a model for understanding these worlds. Its rapid spin, unusual shape, and complex system of moons and rings offer a template for interpreting the physical and chemical processes that might shape similar objects across the galaxy. Haumea's story is not just a local one. It is part of a universal narrative about the formation and evolution of planets and moons in icy environments. As humanity's technological reach grows, the prospect of exploring Haumea directly becomes increasingly feasible. A spacecraft mission to Haumea could revolutionize our understanding of icy worlds. Equipped with advanced imaging systems, spectrometers, and probes, such a mission could map Haumea's surface in unparalleled detail, analyze the composition of its ring and moons, and search for signs of subsurface activity. It could even deploy landers or robotic explorers to sample Haumea's surface ice, testing for organic compounds or other chemical signatures that might hint at its internal processes. Such a mission would not only answer existing questions about Haumea but also raise new ones, pushing the boundaries of planetary science. For now, Haumea remains a glittering mystery on the edge of the solar system, spinning ceaselessly, inviting us to uncover its secrets. Its rapid rotation, shimmering ice, and dynamic system of moons and rings are more than scientific curiosities. They are a reminder of the complexity and beauty of the universe. Haumea stands as a beacon of curiosity, a challenge to our understanding, and a testament to the unyielding forces that shape the cosmos. Its story is far from over, and as we continue to explore, it promises to reveal new chapters that will inspire wonder and discovery for generations to come. Haumea's story, spinning on the edges of the solar system, is a tale that transcends its icy surface and fragmented history. It is a symbol of how much there is left to discover in the vast expanse of space, where even the smallest celestial bodies can challenge the limits of human understanding. Its enigmatic features, a dazzling crystalline crust, a tenuous yet intricate ring, and moons that seem to dance to the rhythm of its rotation, represent questions that stretch the imagination. Yet these are not questions meant to linger unanswered. They are a call to action, urging us to reach farther and think deeper. As we look at Haumea, shimmering against the darkness of the Kuiper Belt, we see not just a world but a gateway. It is a bridge between the past and the future, between the solar system's earliest moments and the technologies we have yet to invent. Each rotation carries the echoes of a violent birth, the scars of ancient impacts, and the whispers of processes still unfolding. It's not just a frozen body but a living archive, holding secrets that span billions of years. To unravel those secrets is to understand not just Haumea but the forces that have shaped every world, including our own. Imagine the day a spacecraft finally reaches Haumea, slipping into orbit to become the first emissary from Earth to this icy realm. Cameras would capture its elongated shape in breathtaking detail, revealing the fractures and ridges of its surface, the glittering complexities of its ring, and the textures of its moons. Instruments would analyze the ice for signs of molecular diversity, searching for the fingerprints of the processes that renew its surface. A lander might touch down, drilling into the frozen crust to uncover ancient materials preserved from the dawn of the solar system. Each piece of data sent back to Earth would deepen our understanding, not just of Haumea, but of the outer solar system and the origins of planetary systems everywhere. And what if Haumea's secrets lead to discoveries that redefine what we know about life? Subsurface oceans hidden beneath kilometers of ice could harbor chemical processes akin to those that gave rise to life on Earth. The ring particles, studied closely, might reveal unexpected organic compounds, raising questions about the prevalence of prebiotic chemistry in the outer solar system. Haumea, seemingly distant and cold, could be the key to understanding how the conditions for life emerge in the most unlikely places. But even beyond the science, Haumea inspires something more profound: wonder. It reminds us that the universe is far from static or simple. Even in the most remote corners, there is activity, change, and evolution. Haumea is a story of resilience, a world forged in the chaos of collisions, yet still spinning with purpose. It is a testament to the idea that every object in the cosmos, no matter how small or far away, plays a role in the greater narrative of existence. Haumea's ending is not final. It is open, spinning endlessly like its rapid rotation. It is an invitation to keep exploring, to send missions, build telescopes, and push the boundaries of what humanity can achieve. It is a reminder that the edge of the solar system is not the edge of knowledge, but the beginning of new frontiers. Haumea spins, its secrets locked in ice and orbit, waiting for the day we finally uncover them. Its story will not end with mystery. It will end with discovery, with answers that inspire even more profound questions, and with a deeper understanding of the universe and our place within it. Gliese 581g, a planet shrouded in intrigue and scientific fascination, orbits its dim, red dwarf star, Gliese 581, situated approximately 20 light-years away in the Libra constellation. Discovered in 2010, this exoplanet quickly captured the imagination of scientists and the public alike due to its potential for habitability. Its location within the so-called habitable zone of its parent star sparked widespread discussion about the possibility of extraterrestrial life and the conditions necessary to sustain it. The habitable zone, often referred to as the Goldilocks zone, is a region around a star where conditions might allow liquid water to exist, a critical ingredient for life as we know it. Unlike Earth, which orbits a yellow G-type star, Gliese 581g circles an M-class red dwarf. These stars are cooler, smaller, and longer-lived than our Sun, making them intriguing targets for the search for habitable worlds. Red dwarfs comprise the majority of stars in the Milky Way galaxy, suggesting that habitable zone planets like Gliese 581g could be more common than initially thought. What makes Gliese 581g particularly captivating is its size and mass, which suggests that it could be a rocky planet like Earth. Its minimum mass is estimated to be about 3 to 4 times that of Earth, placing it within the range of super-Earths. Super-Earths are planets larger than Earth but smaller than gas giants, a category that has no direct analog in our solar system. The radius of Gliese 581g, while not directly measured, is inferred to be about 1.5 times that of Earth, based on its mass and density assumptions. This size raises questions about the planet's geological activity, magnetic field, and ability to retain an atmosphere, all crucial factors for habitability. The parent star, Gliese 581, is relatively dim, emitting only about 1.3% of the Sun's luminosity. As a result, the habitable zone lies much closer to the star. Gliese 581g completes one orbit in just 36.6 Earth days, indicating a much shorter year compared to our planet. Being so close to its star, Gliese 581g is likely tidally locked, meaning one side perpetually faces the star while the other remains in darkness. This configuration creates stark contrasts in temperature between the day and night sides, with a narrow twilight zone, a terminator line, where conditions might be more temperate. The potential for life hinges on the planet's atmosphere, if one exists. An atmosphere could moderate temperature extremes, facilitating heat redistribution between the star-facing and dark sides. Without an atmosphere, the planet's surface would likely be inhospitable, with one hemisphere baking under constant starlight while the other freezes in perpetual night. The discovery of Gliese 581g emerged from meticulous analysis of radial velocity data. This method detects wobbles in a star caused by the gravitational pull of orbiting planets. The wobble in Gliese 581's motion suggested the presence of multiple planets, including Gliese 581g. However, the initial excitement surrounding its discovery was tempered by subsequent debates. Some studies questioned the planet's existence, attributing the detected signals to stellar activity rather than a planetary companion. Yet, subsequent reanalyses of the data have reignited interest, with some researchers asserting that the planet's existence cannot be ruled out. The tantalizing possibility of Gliese 581g has inspired numerous theoretical studies. Simulations suggest that if the planet has an atmosphere with greenhouse gases like carbon dioxide, It could maintain surface temperatures conducive to liquid water, particularly in the terminator zone. The planet's gravity, estimated to be about 1.1 to 1, 7 times that of Earth's, would allow it to hold onto an atmosphere, further enhancing its potential for habitability. Observing Gliese 581g directly remains a formidable challenge due to its distance and the limitations of current technology. However, future telescopes like the James Webb Space Telescope and next-generation ground-based observatories could provide crucial insights. Spectroscopic analysis might reveal the presence of atmospheric components such as water vapor, oxygen, or methane, potential biosignatures. The search for habitable worlds like Gliese 581g underscores humanity's enduring quest to understand our place in the cosmos. As we develop more advanced technologies and refine our techniques, the possibility of confirming the existence of life beyond Earth inches closer to reality. Gliese 581g remains a symbol of scientific curiosity, a beacon guiding us toward the stars, and a reminder of the vast, unexplored frontier that awaits humanity. The allure of Gliese 581g extends beyond its scientific significance. It challenges our understanding of habitability, planetary formation, and the dynamics of star systems. In the years since its discovery, this enigmatic world has sparked intense debates within the scientific community. While some researchers remain skeptical of its existence, others argue that the data strongly supports the presence of a planet within Gliese 581's habitable zone. This divide highlights the complexity of exoplanet detection and the necessity for continuous improvement in observational techniques. If Gliese 581g is indeed a real, rocky planet, its surface environment could be shaped by numerous factors, including its geological activity, atmospheric composition, and interaction with stellar radiation. The tidally locked nature of the planet presents unique challenges for habitability, yet it also opens fascinating possibilities. The constant daylight on one side and perpetual night on the other create extreme environmental contrasts, potentially driving dynamic atmospheric and oceanic currents. If liquid water exists, the terminator zone, where the two hemispheres meet, is particularly intriguing as a potential haven for life. This narrow region might offer moderate temperatures, where the interplay of light and dark could sustain a diverse range of climates and ecosystems. Astrobiologists speculate that any life on Gliese 581g, if present, would have adapted to these extreme conditions. On the star-facing side, organisms might evolve to withstand high levels of radiation and heat, perhaps developing reflective surfaces or protective biofilms. In the dark hemisphere, life could depend on geothermal heat or chemical energy sources, much like extremophiles on Earth that thrive in hydrothermal vents. The terminator zone, with its relatively stable and temperate conditions, might host the richest diversity of life, with ecosystems that bridge the light and dark worlds. The potential for life on Gliese 581g also raises profound philosophical and existential questions. What would the discovery of extraterrestrial life mean for humanity? How would it reshape our understanding of biology, evolution, and the universe itself? These questions drive not only scientific inquiry but also inspire art, literature, and culture, reflecting humanity's deep yearning to connect with the cosmos. From a technological perspective, the search for Gliese 581g and similar planets has fueled advancements in observational astronomy. Techniques such as transit photometry, direct imaging, and radial velocity measurements have become increasingly sophisticated, enabling the detection of smaller and more distant exoplanets. Instruments like the Transiting Exoplanet Survey Satellite, TESS, and the European Space Agency's Cheops mission are paving the way for more detailed studies of planetary systems. Meanwhile, ground-based observatories equipped with adaptive optics are pushing the boundaries of resolution, allowing astronomers to probe the atmospheres of distant worlds. Future missions, such as the planned LUVOIR and HABEX telescopes, aim to directly image Earth-like exoplanets and analyze their atmospheres for biosignatures. These cutting-edge instruments could potentially confirm the existence of Gliese 581G and provide crucial data about its surface and atmospheric conditions. Such observations would represent a monumental leap forward in our quest to identify habitable worlds and answer the age-old question: are we alone in the universe? The study of Gliese 581G also has implications for planetary science and the theory of planetary system formation. The Gliese 581 system, with its multiple planets spanning a range of orbits, offers a valuable case study for understanding how planets evolve in the vicinity of red dwarf stars. Red dwarfs are known for their intense stellar activity, particularly during their early stages, when frequent flares can bombard nearby planets with high-energy radiation. These conditions could strip atmospheres or significantly alter planetary surfaces. Yet planets like Gliese 581G might survive such tumultuous phases, raising questions about the resilience of potentially habitable worlds. Moreover, the discovery of Gliese 581G underscores the importance of interdisciplinary research in exoplanetary science. Astrophysics, geology, atmospheric chemistry, and biology converge to paint a more complete picture of what life on such a planet might look like and how we might detect it. Collaborative efforts between scientists across these fields are essential to unravel the mysteries of Gliese 581G and its counterparts. Public engagement with the discovery of Gliese 581G has been equally significant. The idea of a potentially habitable planet so close to Earth has captured the imagination of millions, fostering a renewed interest in space exploration and astronomy. It has also highlighted the need for continued investment in space science and education, ensuring that future generations are equipped to tackle the challenges and opportunities of exploring the universe. As humanity stands on the brink of a new era in space exploration, Gliese 581G serves as a reminder of the vast, uncharted territories that lie beyond our solar system. Whether or not this planet ultimately proves to be habitable or even real, it has already played a pivotal role in advancing our understanding of the cosmos and inspiring a sense of wonder about the possibilities that await us among the stars. The journey to uncover the truth about Gliese 581G is a testament to human curiosity, resilience, and our enduring desire to explore the unknown. It is a journey that will continue to shape our understanding of the universe and our place within it for generations to come. Gliese 581G represents one of the most captivating enigmas in the field of exoplanet research, offering an opportunity to delve into questions that bridge astronomy, biology, and planetary science. The planet's potential habitability has made it a focal point for studies that explore the conditions necessary for life beyond Earth, driving innovation and collaboration across scientific disciplines. Orbiting its red dwarf parent star at a distance that places it within the habitable zone, Gliese 581G has the unique distinction of being one of the earliest exoplanets identified as a candidate for hosting liquid water on its surface. The mere suggestion of such a possibility set off a flurry of scientific papers, debates, and theoretical models aimed at understanding the characteristics of this world and its potential to harbor life. The characteristics of red dwarf stars like Gliese 581 are critical to this discussion. As the most common type of star in our galaxy, red dwarfs offer a promising avenue for finding habitable planets due to their long lifespans and prevalence. However, these stars also pose challenges, particularly in their propensity for stellar flares and high levels of radiation during their early evolutionary stages. For Gliese 581g, this raises questions about the stability and survivability of its atmosphere over geological timescales. If the planet's atmosphere has endured these conditions, it could act as a protective layer, shielding the surface from harmful radiation and maintaining temperatures conducive to liquid water. Researchers have hypothesized that the composition of such an atmosphere would play a pivotal role in its ability to sustain life. A thick atmosphere rich in greenhouse gases like carbon dioxide could help moderate temperatures across the planet's surface, especially given its likely tidally locked rotation. In a tidally locked state, one side of Gliese 581g would face perpetual daylight while the other remains in constant darkness. This configuration creates extreme temperature gradients, but an atmosphere with robust circulation patterns could distribute heat more evenly, making the twilight zone between day and night a potential hotspot for habitability. The geological features of Gliese 581g, though entirely speculative at this stage, add another layer of intrigue to the planet's story. A rocky composition with active tectonics could support the recycling of carbon and other life-sustaining elements, a process that is vital for maintaining a stable climate over long periods. Volcanic activity could also release gases into the atmosphere, contributing to its density and composition while providing energy sources for potential microbial life forms. The question of water, arguably the most crucial ingredient for life, remains central to discussions about Gliese 581g. If liquid water exists on the planet, it could take various forms, from vast oceans covering the terminator zone to subsurface reservoirs protected from the harsh conditions of the surface. The presence of water would not only enhance the planet's habitability but also provide a medium for chemical interactions that could lead to the emergence of life. The discovery of Gliese 581g and the subsequent debates about its existence highlight the challenges inherent in exoplanet detection. The radial velocity method used to identify the planet relies on detecting the minute wobbles in a star's motion caused by the gravitational pull of orbiting planets. While this technique has proven highly effective, it is not without its limitations, particularly when it comes to disentangling planetary signals from stellar activity. In the case of Gliese 581g, this has led to conflicting interpretations of the data, with some studies affirming the planet's presence and others attributing the observed signals to noise or activity within the star itself. Despite these uncertainties, the prospect of Gliese 581g has galvanized efforts to improve detection methods and refine our understanding of planetary systems. Advances in spectroscopy, adaptive optics, and space-based observatories have opened new frontiers in the study of exoplanets, enabling scientists to probe the atmospheres, compositions, and climates of distant worlds with increasing precision. For Gliese 581g, future missions capable of directly imaging exoplanets or analyzing their atmospheric spectra could provide definitive answers about its characteristics and potential for habitability. Beyond its scientific implications, Gliese 581g holds a special place in the broader narrative of humanity's search for life beyond Earth. The idea of a potentially habitable planet within our cosmic neighborhood has captured the imagination of people around the world, serving as a source of inspiration and wonder. It underscores the importance of exploring the universe, not only to satisfy our curiosity, but also to gain perspective on our own planet and the fragile ecosystems it supports. The search for Gliese 581g is part of a larger journey to understand the conditions that give rise to life and the factors that enable it to thrive. It challenges us to consider the diversity of planetary environments that might exist in the universe and the ways in which life could adapt to conditions vastly different from those on Earth. Whether Gliese 581g ultimately proves to be habitable or even real Its story exemplifies the spirit of discovery that drives scientific exploration and the unyielding human desire to seek answers to the fundamental questions of existence. In the coming decades, as new technologies and missions take us closer to uncovering the secrets of distant star systems, Gliese 581G will remain a symbol of the possibilities that await us in the uncharted realms of the cosmos. It is a reminder that the universe is vast, mysterious, and full of potential, beckoning us to look beyond our own world and envision the countless others that lie waiting to be discovered. The mystery of Gliese 581G deepens with every question we ask, pulling us into an intellectual adventure that stretches the boundaries of science and imagination. What if this distant world, orbiting a star so unlike our sun, harbors secrets that could redefine our understanding of life itself? Imagine standing on its twilight line, the narrow strip where day perpetually meets night, under a crimson sky painted by the faint glow of its red dwarf star. This region, balanced between scorching heat and frigid cold, could be a crucible of possibilities, a place where chemistry dances on the edge of biology, where alien ecosystems might thrive in conditions we can barely fathom. But the intrigue doesn't end there. The planet's tidally locked nature could create bizarre and extreme weather patterns. On the sunlit side, relentless winds might scour barren landscapes, their fury shaped by the intense gravitational pull of Gliese 581. On the dark side, perpetual night might shroud frozen plains in eternal silence, broken only by the faint whispers of atmospheric currents. Yet in the Terminator zone, where the extremes meet, we might find an otherworldly equilibrium, a place where liquid water flows in alien rivers, carving paths through landscapes no human eye has yet seen. Consider the possibilities for life under such conditions. Life on Gliese 581G, if it exists, would likely be unrecognizable to us. On the sunlit side, photosynthetic organisms might harness the weak, reddish light of their star, evolving pigments unlike anything on Earth. Their slow, deliberate metabolic processes could mirror the measured rhythm of a star that lives for trillions of years. Meanwhile, in the eternal night, bioluminescent creatures could navigate the darkness, their faint glows illuminating the icy void. Life in the Terminator zone might bridge these extremes, adapting to the cycles of warmth and cold, light and dark, in ways we can only begin to theorize. Even the planet's potential atmosphere fuels the imagination. Could it be a dense, greenhouse-rich envelope that traps heat and nurtures liquid water on the surface? Or perhaps it's a thin, fragile veil, constantly replenished by geological activity. Volcanoes, spewing gases into the sky, might create fleeting auroras visible from space, spectacles that tell a silent story of a world alive with unseen processes. Gliese 581G also represents a profound challenge for our technology and ingenuity. How do we study a planet so distant, so veiled in mystery? Current telescopes and instruments can only infer its existence through indirect measurements, tantalizing us with clues but offering no direct glimpse. Yet, the dream of seeing this world in detail, its mountains, valleys, and oceans, if they exist, is not out of reach. The next generation of space telescopes, equipped with advanced imaging capabilities, could one day reveal its secrets. Imagine the moment when humanity captures the first image of this alien world, a pale, distant orb shimmering in the vastness of space. And what if, buried in its spectral data, we find the signatures of life? Methane, oxygen, or even more exotic chemicals could signal biological activity, raising questions that transcend science. How did life begin there? What forms has it taken? And what does its existence mean for us, for our place in the universe, and for the story of life itself? As we peer deeper into the cosmos, Gliese 581G serves as a beacon, a reminder of the limitless potential of discovery. It challenges us to dream bigger, to push the boundaries of what we know, and to explore the vast, uncharted frontier of interstellar space. For every answer we uncover, 1,000 new questions arise, each more tantalizing than the last. The universe is calling, and Gliese 581G is one of the voices whispering back, daring us to uncover its secrets and confront the extraordinary possibilities that lie beyond the veil of the familiar. The story of Gliese 581G continues to unfold as both a scientific mystery and a symbol of humanity's enduring fascination with the unknown. This planet, locked in a gravitational dance with its faint red dwarf star, tantalizes us with the possibility that it might be more than a barren rock adrift in the cosmos. It might be a world alive, dynamic, and teeming with answers to questions we've only just begun to ask. The implications of its potential habitability resonate far beyond the confines of academic research. They reach into the realms of philosophy, art, and our deepest existential curiosities. Picture the landscape of Gliese 581G as you might imagine it. On the day side, bathed in the dim, red light of its star, rocky terrain might stretch endlessly, pockmarked by craters and perhaps softened by the erosion of ancient winds. Dust particles, caught in the weak yet persistent pull of gravity, could linger in the thin air, diffusing the starlight into surreal, otherworldly hues. Temperatures on this hemisphere might soar, baking the surface into a parched expanse that challenges even the hardiest of hypothetical life forms. And yet, the potential for adaptation here remains a source of endless speculation. Microbes capable of tolerating heat, shielded beneath layers of rock or protected by biofilms, could thrive where we see desolation. The night side, by contrast, plunges into eternal darkness, a frigid and silent abyss where temperatures might plummet to extremes unimaginable on Earth. Here, ice could dominate, covering the ground in thick, immovable sheets that glisten faintly under the weak glow of distant stars. Beneath this frozen crust, however, life might persist in liquid water reservoirs, heated by the planet's geothermal energy. Organisms might rely on chemosynthesis, drawing energy from the planet's inner heat and mineral-rich waters. These ecosystems, if they exist, could mirror those found around Earth's hydrothermal vents, cradles of life that flourish in the absence of sunlight. But it is the terminator zone, the narrow band where day meets night, that captivates the imagination most profoundly. Here, conditions might be just right for liquid water to exist on the surface, a key ingredient for life as we know it. The interplay of light and shadow could create a dynamic environment, with winds transporting heat from the day side to the night side, moderating temperatures and fostering climatic stability. The twilight region could host alien lakes or even shallow seas, reflecting the red glow of the star in shimmering waves. If vegetation or microbial mats exist, they might cover the ground in vibrant, otherworldly colors, evolving pigments to absorb the limited light efficiently. From a scientific perspective, the potential habitability of Gliese 581G raises critical questions about the resilience and adaptability of life. On Earth, extremophiles thrive in conditions once thought inhospitable, within acidic hot springs, beneath kilometers of ice, and even in radioactive environments. These organisms challenge our assumptions about where life can exist and push us to expand our search criteria for extraterrestrial life. Could Gliese 581G, with its extremes of light and dark, heat and cold, be a crucible for similar extremophiles? If so, what might their biochemistry look like? Would it rely on carbon and water as Earth's life does? Or could it be based on entirely different elements and compounds, rewriting the rules of biology? To answer these questions, scientists are turning to cutting-edge technology and innovative methods. The hunt for biosignatures on Gliese 581G hinges on spectroscopy, a technique that analyzes the light passing through a planet's atmosphere to detect chemical fingerprints. By studying the light from its host star as it interacts with the planet's atmosphere, we might detect gases like oxygen, methane, or ozone molecules that, on Earth, are closely associated with life. The detection of these compounds in specific ratios could signal biological activity, providing indirect yet compelling evidence of life on this distant world. However, observing Gliese 581G directly presents formidable challenges. At a distance of 20 light-years, it is too faint to be resolved by most current telescopes. But the next generation of observatories, such as the Extremely Large Telescope, ELT, and the James Webb Space Telescope, JWST, promises to revolutionize our ability to study exoplanets. Equipped with advanced imaging systems and spectrographs, these instruments could reveal not only the composition of Gliese 581G's atmosphere, but also its surface temperature, albedo, and even signs of seasonal changes, indicators of an active, dynamic environment. Beyond the scientific intrigue, the discovery of a potentially habitable world so close to Earth has profound implications for humanity's future. It forces us to confront the possibility that we are not alone in the universe, a realization that could fundamentally alter our worldview. It challenges us to think about life not just as a phenomenon unique to our planet, but as a cosmic inevitability, arising wherever conditions allow. And it inspires us to dream of the day when we might send probes, or even humans, to explore such worlds firsthand. The journey to Gliese 581G is one of imagination as much as science. It beckons us to look up at the night sky and wonder, what would it feel like to stand on this alien world, to breathe its air, hear its sounds, and experience the strange beauty of its landscapes? What stories would its rocks tell, and what secrets might its waters hold? These questions, unanswered and open-ended, are a testament to the boundless curiosity that drives us to explore, to push beyond the limits of what we know, and to seek out the unknown. In this pursuit, Gliese 581G is more than just a planet. It is a symbol of possibility, a reminder that the universe is vast and full of wonders waiting to be discovered. It represents the next chapter in our journey of exploration, a journey that has taken us from the shores of Earth to the farthest reaches of our solar system and now to the stars beyond. The story of Gliese 581G is, in many ways, our own story, one of resilience, curiosity, and an unyielding drive to understand the cosmos and our place within it. And as we continue to search for answers, this enigmatic world remains a beacon of hope and inspiration, calling us ever onward into the great unknown. The enigma of Gliese 581G deepens with every theoretical exploration, each new layer of possibility stirring the imagination and pushing the boundaries of human understanding. What if this distant world is not only habitable but inhabited? What forms of life might have evolved under the unique conditions imposed by its red dwarf star? Could its ecosystems, shaped by an interplay of perpetual day, eternal night, and the temperate twilight in between, reveal evolutionary trajectories that defy anything seen on Earth? The sheer adaptability of life as we know it suggests that even the most extreme environments on Gliese 581G might harbor organisms. On Earth, tardigrades survive in the vacuum of space, extremophiles thrive in boiling acidic springs, and microbes flourish beneath miles of Antarctic ice. Life on Gliese 581g, if it exists, could have adapted to its own extremes with equal ingenuity. On the sunlit side, organisms might have evolved biochemical shields against the intense radiation emitted by its star, perhaps using pigments that not only protect but also harness the weak red light for energy. These creatures could be analogous to Earth's cyanobacteria, the pioneers of oxygenic photosynthesis that once transformed our planet's atmosphere. In the icy darkness of the night side, life might depend on geothermal energy rather than starlight. Beneath layers of ice, vast subsurface oceans, kept liquid by the heat from the planet's interior, could support ecosystems much like those found near Earth's hydrothermal vents. Here, chemosynthetic bacteria might form the base of a food chain that includes complex multicellular organisms, all thriving in complete darkness. Imagine the sight of bioluminescent creatures illuminating these underworld oceans, their ghostly light creating a living galaxy beneath the ice. The Terminator Zone, that fascinating strip where light and dark meet, presents a unique frontier for habitability. Here, the balance of temperature and light could create an environment not only suitable for life but one rich in biodiversity. This region might host alien forests, sprawling across a landscape where the dim red light nurtures strange, slow-growing plants or fungal analogs. These organisms could form the basis of a complex ecosystem, one where herbivores, scavengers, and predators have evolved in ways dictated by the planet's peculiar rhythms. And then there is the question of intelligence. Could life on Gliese 581g have evolved beyond the microbial stage? Could sentient beings, shaped by the challenges of their environment, have developed civilizations on this distant world? If so, what would their cultures look like and how might they perceive the universe? Would they gaze at the stars, as we do, and wonder if they are alone? These speculative musings drive the profound sense of wonder that Gliese 581g inspires. But the scientific challenges of studying such a planet are as vast as its potential. The faint light from Gliese 581g carries whispers of its composition, its atmospheric chemistry, and perhaps even its weather patterns. By analyzing this light with advanced spectrographs, we might one day detect molecules like water vapor, carbon dioxide, or methane, compounds that could hint at the presence of life. Even more tantalizing would be the discovery of biosignatures such as oxygen or ozone, which, in certain contexts, could be indicative of biological processes. Future telescopes, such as LUVOIR or HABEX, promise to revolutionize our ability to study planets like Gliese 581g. Equipped with instruments capable of imaging Earth-sized planets and analyzing their atmospheres, these observatories could transform our theoretical models into empirical knowledge. The dream of seeing Gliese 581g's surface, its landscapes, its oceans, and perhaps even its clouds, is not beyond reach. Such an achievement would mark a turning point in human history, providing not just answers but new questions about our place in the cosmos. As we look toward the future, the journey to understand Gliese 581g reflects humanity's broader quest for meaning and connection. This distant world, so far beyond our grasp yet so tantalizingly close in astronomical terms, represents a bridge between the known and the unknown. It reminds us that the universe is vast, filled with mysteries that challenge our intellect and inspire our creativity. The pursuit of Gliese 581g is a testament to the unyielding human spirit, our relentless curiosity, and our capacity to dream beyond the confines of our present reality. Every step we take in unraveling the secrets of Gliese 581G brings us closer to answering some of the most profound questions we can ask. Are we alone in the universe? Is life a rare accident, confined to the pale blue dot we call home, or a common thread woven throughout the cosmic tapestry? Gliese 581G stands as a beacon in this search, a symbol of what lies beyond, waiting for us to discover it. Its story is not just a scientific narrative. It is a human one, a story of wonder, exploration, and the timeless desire to reach for the stars. The story of Gliese 581G unfolds like an endless narrative, one that pulls us deeper into the mystery of our universe with every new thought, every unanswered question. As we dream of this world, distant yet tantalizingly close in cosmic terms, we are reminded of the unyielding drive to explore the unknown, to uncover truths about ourselves through the distant echoes of alien landscapes. What if Gliese 581G is more than just habitable? What if it is alive, its ecosystems thriving in conditions completely foreign to human experience? Its red dwarf star, Gliese 581, may shine dimmer and cooler than our sun, but its stability over billions of years offers a fertile ground for life to evolve. Unlike massive stars that burn out quickly, red dwarfs endure for trillions of years, their longevity providing a long and steady backdrop for biological complexity to arise. Could this cosmic stability have fostered life forms with an ancient evolutionary lineage, far surpassing the mere 4.5 billion years of life's history on Earth? Imagine beings shaped by the peculiarities of their environment. If intelligent life exists on Gliese 581G, how would it have adapted to a tidally locked world? On the perpetual day side, would civilizations have evolved to harness the constant low-energy red light of their star, building cities that stretch into the blazing horizon? On the dark side, might they have carved their homes into the icy crust, using geothermal heat as a lifeline in the unending cold? In the Terminator zone, where the two extremes meet, could there be societies that thrive in balance, their lives shaped by the interplay of light and darkness, warmth and cold? The possibility of intelligent life raises profound questions about communication. If beings on Gliese 581G possessed technology, would they have tried to signal their presence to the cosmos? Could their messages, traveling at the speed of light, already be on their way to us, waiting to be intercepted by our instruments? Or, conversely, could we send messages to them, carefully encoded radio waves or laser pulses designed to announce our presence and invite dialogue? The prospect of such contact ignites the imagination, bridging the vast interstellar gulf with a spark of shared curiosity. But the road to uncovering these possibilities is fraught with challenges. Observing Gliese 581G directly requires pushing the boundaries of modern astronomy. At a distance of 20 light-years, the planet appears as little more than a faint point of light against the vastness of space. Yet that faint light holds the keys to its secrets. By splitting the light into its spectral components, astronomers can infer the planet's atmospheric composition, surface conditions, and even signs of seasonal change. Each discovery would add a new layer to the story, transforming speculation into knowledge. Even with our most advanced technologies, reaching Gliese 581G remains a distant dream. At our current pace of space travel, a journey to this exoplanet would take tens of thousands of years. Yet visions of interstellar exploration persist, fueled by concepts like solar sails, fusion propulsion, and wormholes. Each new technological breakthrough brings us a step closer to turning science fiction into science fact, to transforming Gliese 581G from a point of light in the sky into a destination for exploration. As we await these advances, the scientific community continues to debate the very existence of Gliese 581g. The signals that hint at its presence are subtle, buried in the noise of stellar activity and the complexities of its star's motion. Some argue that the planet is a ghost, an artifact of flawed data analysis. Others remain convinced that it is real, pointing to patterns that align too precisely with the characteristics of a planetary body to be mere coincidence. This ongoing debate underscores the challenges of exoplanet detection, reminding us that science is a process, one that thrives on questioning, refinement, and discovery. Yet, even if Gliese 581g were to prove elusive, the questions it raises endure. What would it mean for life to exist so far from Earth? How would such a discovery reshape our understanding of biology, of evolution, and of ourselves? Would we see ourselves as unique, a rare anomaly in an otherwise barren universe? Or would we come to understand that life is not an exception but a rule, a natural consequence of the cosmos' inherent creativity? The search for answers propels us forward, inspiring new missions, new technologies, and new ways of thinking. In pursuing Gliese 581g, we are not merely exploring a distant world, we are exploring the very essence of what it means to be human. Our curiosity, our ingenuity, and our desire to understand the universe are as much a part of this story as the planet itself. As the narrative of Gliese 581g continues to evolve, it invites us to dream boldly and think deeply. It challenges us to look beyond the immediate and familiar, to imagine what lies beyond the edge of our knowledge. And it reminds us that the universe is vast, filled with wonders that await our discovery. Gliese 581g, whether real or hypothetical, stands as a symbol of this limitless potential, a reminder that the journey to understanding is as infinite as the cosmos itself. In the pursuit of this enigmatic world, we find not only the promise of answers, but also the enduring thrill of the unknown. The intrigue surrounding Gliese 581g only grows as we consider the implications of its potential for life, its role in the broader search for habitable worlds, and what it tells us about the universe's boundless possibilities. It exists in a delicate balance of mystery and promise, a world that could be a thriving hub of alien ecosystems or a silent, barren outpost, waiting for the touch of human exploration to give it meaning. One of the most fascinating aspects of Gliese 581g is how it forces us to rethink habitability itself. For decades, scientists believed that life could only flourish in conditions similar to those on Earth: temperate climates, abundant liquid water, and a stable atmosphere. Yet, as we discover more exoplanets and study extremophiles here on Earth, our understanding of life's resilience has expanded dramatically. Could Gliese 581g, with its stark contrasts of light and dark, host forms of life that have evolved to exploit its unique environment? Imagine standing on the planet's terminator line, where the eternal sunrise or sunset would paint the sky in otherworldly hues. The landscape could be a fusion of molten rock and icy plains, with rivers of liquid water meandering through the temperate middle. Winds might sweep across this boundary, carrying warmth from the sunlit side into the frozen darkness, creating a dynamic weather system. If Gliese 581g has an atmosphere, its composition could be entirely alien to us, a mix of exotic gases that sustain life forms unrecognizable by earthly standards. Perhaps the skies are filled with drifting organisms, floating like jellyfish on currents of heated air, their translucent bodies glowing faintly in the crimson light. On the perpetual night side, the darkness might be pierced only by flashes of bioluminescence or the faint flicker of volcanic eruptions. Here, life could be deeply subterranean, thriving in caverns warmed by geothermal energy. The idea of ecosystems thriving in complete isolation from their sun, powered solely by the heat of the planet's core, is not entirely foreign to us. On Earth, similar communities exist around hydrothermal vents at the bottom of our oceans, where sunlight never penetrates. The day side, exposed to constant starlight, could be a harsh and unforgiving desert. Yet even here, life might find a way. Organisms could evolve to withstand the radiation of the red dwarf, using biochemical shields or developing pigments that convert the intense energy into a usable form. Life on this side might resemble hardy desert flora or subterranean microbes, hiding beneath the surface to escape the relentless heat. And then there is the question of time. If Gliese 581g is real, it has existed for billions of years, orbiting a star that will outlive our own by trillions more. What if life there has had eons longer than life on Earth to evolve and diversify? Could it have reached levels of complexity and intelligence far beyond our comprehension? The potential age of this system presents a tantalizing possibility. That Gliese 581g could host ancient civilizations or the ruins of ones that rose and fell long before humanity began its ascent. The search for intelligent life brings with it profound questions about communication and understanding. How would beings from a tidally locked world perceive time, space, and existence? Would they even recognize us as intelligent? Or would our perspectives and forms be as alien to them as theirs would be to us? Efforts like the search for extraterrestrial intelligence, SETI, aim to answer these questions, scanning the skies for signals that might reveal the presence of advanced civilizations. Gliese 581g, with its potential habitability, is a prime candidate for such investigations. A single signal, even a faint, undecipherable one, would change everything we know about our place in the universe. Yet Gliese 581g is not just a beacon of scientific interest. It is a symbol of hope, curiosity, and the boundless human drive to explore. Its existence, debated as it may be, has already reshaped the way we think about exoplanets and the search for life. It has inspired advancements in technology, from more sensitive spectrographs to ambitious missions designed to image distant worlds directly. The dream of not just studying Gliese 581g from afar but one day sending probes, or even humans, to its surface feels closer with every technological leap. Such an endeavor would mark a turning point in human history. Imagine the moment when a probe enters orbit around Gliese 581g, capturing detailed images of its surface for the first time. Each pixel of data would carry the weight of generations of effort, curiosity, and wonder. What would we see? Rugged mountains carved by alien winds? Vast, ice-covered oceans glinting faintly in the starlight? Cities illuminated by the glow of an intelligent species? The possibilities are endless, each one more thrilling than the last. As we continue to refine our tools and deepen our understanding of exoplanets, the narrative of Gliese 581g remains a story in progress. Whether it proves to be a world brimming with life, a silent rock in the void, or even a phantom of data misinterpreted, its legacy is assured. It has pushed us to look farther, think deeper, and dream bigger. It reminds us that the universe is vast, that the unknown is always worth exploring, and that the pursuit of knowledge is a journey without end. The story of Gliese 581g is ultimately a human story. It reflects our insatiable curiosity, our unyielding determination, and our capacity for wonder. It is a story that will continue to inspire as we push the boundaries of what is possible, daring to imagine worlds beyond our own and our place among them. In the endless expanse of the cosmos, Gliese 581G shines as a beacon of possibility, a reminder that no matter how much we discover, there will always be more to explore. Gliese 581G is more than a planet. It's a puzzle that captures the imagination and invites us to step beyond the boundaries of what we know. It's a silent whisper from the cosmos, beckoning us to unravel its mysteries and confront the tantalizing question: could this distant world be home to life? Every theory, every model, and every speculative idea we craft about this enigmatic exoplanet pulls us deeper into the possibilities of its reality. If it exists, Gliese 581G could be the closest clue we have to understanding our place in a universe brimming with untold wonders. Imagine standing on its surface. The sky above is not blue but a dim reddish hue, illuminated by the weak but steady light of its red dwarf star. The star is larger in the sky than our sun, casting an eerie crimson glow over the landscape. The air, if it exists, might feel thick and alien, carrying unfamiliar scents of chemical reactions unseen on Earth. On the Terminator line, where day meets night, strange and delicate ecosystems might flourish, adapting to the planet's unique dance of extremes. Each step you take could echo with the unknown, the feeling of treading on ground where no human has ever been, a frontier that challenges every assumption we have about life and habitability. The planet's locked orientation to its star means that its day side could be a searing, alien desert, while its night side is a frozen abyss. But here, in this narrow band between scorching light and eternal darkness, the balance of temperatures might create an environment hospitable to life. Imagine vast oceans that stretch across the twilight zone, warmed by heat transfer from the planet's molten core and stabilized by its atmosphere. If the planet's atmosphere is dense enough, it could buffer these extremes, creating a temperate haven where water, wind, and rock converge to form the conditions for life. But what kind of life? This is where Gliese 581G takes our imagination to its farthest reaches. On the day side, organisms might have evolved to thrive under the constant red light of the star, their biology optimized for photosynthesis in this unique spectrum. Unlike Earth's green vegetation, plants here might be dark, even black, absorbing every scrap of light to fuel their growth. Meanwhile, on the night side, life could be vastly different. Without sunlight, ecosystems might be powered by geothermal energy, with organisms relying on chemosynthesis to survive. These creatures could be alien in every sense of the word, with biologies shaped by the absence of light and the harsh grip of cold. And then there's the possibility of intelligent life. Could civilizations have arisen in this dynamic environment, adapting to the challenges of a tidally locked world? If so, how might they have evolved to communicate, to build, to dream? Would their societies be divided along the lines of light and dark, or unified by their shared existence in the narrow habitable zone? Would they look to the stars as we do and wonder about others out there, or have they already found ways to explore beyond their world, sending signals into the cosmos that we have yet to detect? The search for answers brings us to the cutting edge of technology and science. The faint signals of Gliese 581G challenge our best instruments, requiring unprecedented precision to separate the planet's whispers from the noise of its star. As we refine our tools, spectrographs capable of analyzing atmospheric gases, telescopes designed to image distant worlds directly, the prospect of uncovering the truth grows ever closer. Imagine the thrill of detecting oxygen, methane, or water vapor in the planet's atmosphere, clear indicators of active processes, perhaps even life. But the journey to Gliese 581G doesn't stop with telescopes. Humanity dreams of reaching for the stars, of building the ships that will one day take us to other worlds. Concepts like solar sails, propelled by the light of the sun, or nuclear fusion drives, capable of accelerating to unimaginable speeds, bring the dream of interstellar travel within the realm of possibility. Imagine a fleet of robotic explorers designed to withstand the harshness of deep space, setting out on a journey across the void to reach Gliese 581G. Decades or centuries later, their data could return to Earth, bringing with it the first images of an alien world. And what if we discover more than landscapes and atmospheres? What if those images reveal cities, alien architecture standing silent under the crimson sky? Or even the faint, unmistakable signatures of technology, signals that suggest intelligence capable of shaping its environment and contemplating the stars? The discovery of life, let alone intelligent life, on Gliese 581G would be the most profound moment in human history, rewriting our understanding of existence itself. It would force us to confront questions about our place in the cosmos, about what it means to be alive, and about the nature of intelligence across the universe. Gliese 581G stands as a symbol of everything we have yet to discover. It reminds us of the vastness of the universe and the infinite possibilities contained within it. Whether it turns out to be a living world or a barren rock, its story will continue to inspire us to look outward, to dream of other worlds, and to imagine what lies beyond the veil of the stars. In the pursuit of Gliese 581G, we are reminded that the greatest discoveries are not just about the answers we find, but about the journey itself, the relentless human drive to explore, to question, and to seek the extraordinary. The universe is calling, and Gliese 581G is one of its most compelling voices, urging us to step into the unknown and embrace the boundless potential of what lies beyond. The allure of Gliese 581G persists, an enigmatic siren in the vast cosmic ocean, pulling us deeper into its mysteries. What secrets does this distant world hold, and how far will humanity go to uncover them? Every unanswered question about Gliese 581G is a challenge to our ingenuity, a test of our willingness to dream beyond the constraints of our current understanding. It dares us to ask, if we were to make contact with another world, what would we learn? Not only about it, but also about ourselves. The very idea of Gliese 581G sparks profound wonder because it represents a threshold, one where science meets imagination, where the boundaries of the known dissolve into infinite possibilities. Imagine stepping into the shadowed twilight of this planet, where the air might shimmer with suspended particles, scattering the faint red light into surreal patterns. In this perpetual dawn or dusk, the landscapes could be sculpted by winds that have never ceased, carving out cliffs, dunes, and plains of alien beauty. If life exists here, how might it have adapted to this ever-balanced dance between extremes? On Earth, even the harshest environments host life forms that astonish us with their resilience. From bacteria thriving in the scalding waters of volcanic vents to microbes surviving in radioactive waste, life finds a way. Could Gliese 581G harbor similar extremophiles, their biochemistries tailored to the planet's unique conditions? Imagine complex organisms evolved to straddle the light and dark zones, moving seamlessly between the hot, barren lands of the dayside and the icy wastelands of the night. These beings could embody dualities unknown to Earth, a fusion of adaptations for fire and ice. The atmospheric mysteries of Gliese 581G are no less captivating. If the planet possesses a thick atmosphere, it might act as a thermal regulator, redistributing heat from the dayside to the night. The result? Violent storms, endlessly circling the Terminator line, churning clouds of exotic gases and rains of liquid compounds alien to anything on Earth. Lightning storms could ignite the skies with blinding flashes, illuminating the stark contrasts of a planet caught between perpetual light and unending darkness. What if the atmosphere itself teems with life? Floating organisms, perhaps resembling Earth's plankton but vastly larger, could drift on the winds, absorbing nutrients from the air. These aerial ecosystems might form the backbone of an alien food chain, their delicate structures shimmering under the faint light of the star. Imagine vast swarms of bioluminescent creatures lighting up the planet's skies, signaling to one another in patterns of color and brightness. A living aurora dancing against the eternal twilight. The concept of intelligent life on Gliese 581G propels us into the realm of the extraordinary. Could beings on this planet have evolved in harmony with its extremes, their civilizations reflecting the balance of their world? Imagine cities built along the Terminator line, designed to withstand the relentless forces of nature. These structures might incorporate materials unknown to us, derived from the unique geology of Gliese 581G. Their technology could be based on principles we have yet to comprehend, shaped by their adaptation to an environment so unlike our own. If these beings are there, would they have turned their gaze to the stars? Would they have wondered about other worlds, just as we do? What if they have already detected Earth, their instruments picking up the faint signals of our civilization? The possibility that they might be listening, or even attempting to communicate, transforms Gliese 581G from a distant curiosity into a cosmic mirror, reflecting our own hopes and fears about the unknown. The challenges of reaching Gliese 581G are monumental, yet the dream persists. Advanced propulsion concepts such as antimatter engines or warp drives could one day make interstellar travel feasible, shrinking the vast distances between stars. Imagine a future where humanity sends an armada of robotic probes to Gliese 581G, each equipped with advanced AI to analyze its environment and search for signs of life. These machines could land, explore, and even return samples to Earth, delivering answers to questions we can barely articulate today. But what if we could go further? What if Gliese 581G became humanity's first interstellar colony? Its potential habitability, combined with its relative proximity, makes it a tantalizing candidate for settlement. Colonists might build self-sustaining habitats in the temperate zones, adapting their technology to the planet's unique conditions. They would carry the legacy of Earth to a new world, forging a future among the stars while uncovering the secrets of their alien home. The pursuit of Gliese 581G isn't just a scientific endeavor. It's a philosophical journey. It forces us to confront the nature of life itself, to redefine what it means to exist in a universe so vast that even the closest stars seem impossibly distant. It challenges us to think beyond Earth, to consider the infinite diversity of worlds that might lie waiting to be discovered. And it reminds us that every step we take into the cosmos is also a step inward, toward a deeper understanding of who we are and what we aspire to become. Gliese 581G, whether it proves to be a cradle of life or a silent, barren rock, is a symbol of humanity's greatest strengths. Our curiosity, our creativity, and our unrelenting drive to explore. It is a reminder that the universe is not a collection of distant stars and empty space, but a living tapestry, filled with possibilities that stretch beyond the limits of imagination. As we gaze at the faint light of Gliese 581G's star, we are not just looking outward, we are looking forward, into a future shaped by discovery, wonder, and the endless pursuit of the extraordinary. The mystery of Gliese 581G lingers in the imagination like a tantalizing melody, unresolved but unforgettable. It is a silent enigma suspended 20 light-years away, orbiting a red dwarf star that flickers dimly in the vast black canvas of space. Every whisper of data, every theoretical model, pulls us closer to the brink of revelation. What lies on this distant world? A barren, rocky expanse? Or a thriving haven, rich with life unlike anything we've ever conceived? Picture yourself approaching Gliese 581G for the first time, aboard a futuristic spacecraft built to traverse the interstellar gulf. The planet looms into view, a shadowy sphere half-lit by its crimson star, its surface shrouded in swirling clouds that glint faintly in the twilight. The closer you get, the more its secrets begin to reveal themselves. You see vast mountain ranges on the Terminator line, where temperatures might be just mild enough for liquid water to carve paths down jagged slopes. You catch glimpses of oceans reflecting the dim starlight, stretching across the twilight zone like shimmering ribbons of liquid possibility. But what if Gliese 581G holds more than landscapes and water? What if, as you descend into its atmosphere, you find a world alive with the unfamiliar? Imagine creatures perfectly adapted to the planet's extreme conditions, their forms dictated by a blend of necessity and evolutionary creativity. On the sunlit side, strange, towering organisms might soak in the weak red light, their surfaces dark and glossy to absorb every photon. These alien plants, if they exist, could reach toward the star in intricate shapes, their growth guided by the low, steady energy that has sustained their world for billions of years. On the night side, life might take a different form entirely. In the frigid darkness, glowing rivers of molten rock from geothermal activity could snake across the surface, creating pockets of warmth. In these rare havens, bioluminescent organisms might thrive, their ethereal lights pulsing like living stars in an eternal black sky. Some might cling to the icy ground, while others drift in the thin, alien winds, their glowing bodies a beacon of life in an otherwise frozen void. And in the twilight zone, where light and dark meet, could there be even more? Perhaps an ecosystem balanced delicately between the extremes. Here, liquid water could flow freely, warmed by the atmosphere and the planet's inner heat. Life could take on forms that straddle both sides of existence. Plants with roots in the shadows and leaves stretching toward the light. Creatures that bask in the sun by day and burrow into the ground at night. This band of perpetual dawn and dusk might teem with diversity, a living laboratory of survival and adaptation. The possibilities extend beyond biology. Gliese 581G's potential to host intelligent life remains one of the most captivating questions of all. If civilizations have arisen there, how might they have adapted to a tidally locked planet? Would they have built their cities along the Terminator line, where energy and resources are most abundant? Would their technology harness the winds that constantly sweep between the hemispheres, or tap into the geothermal heat that pulses beneath the surface? And if these beings have evolved alongside their unique environment, how might their perspectives on existence differ from ours? Would they look to the stars as we do, longing for connection, or would their focus remain on their own world, content within its dualities? The idea of contact with such a civilization electrifies the imagination. What if they've already sent signals into the void, messages that we've yet to recognize or decode? Or what if, even now, they're listening for whispers from other worlds, scanning the skies and wondering if they, too, are alone? The thought that two species separated by light years could one day meet, if only through faint signals or shared knowledge, feels like the ultimate expression of humanity's longing for connection, a bridge across the cosmic divide. Yet Gliese 581g is more than just a scientific curiosity or a setting for speculative wonder. It represents the pinnacle of human aspiration, the dream of discovery that drives us to push beyond the boundaries of what we know. Every effort to understand it, every telescope pointed at its star, every simulation run to model its environment, brings us closer not only to it but to ourselves. What we discover about Gliese 581g, whether it's a thriving world or a silent rock, will redefine what we believe is possible. It will challenge our assumptions about life, resilience, and the vast array of ways a planet can be alive. The universe is vast, its secrets infinite. Gliese 581g, perched on the edge of the known and the unknown, serves as a reminder of this vastness and of the incredible privilege we have to explore it. Whether we find alien life or learn only more about the intricate dance of planets and stars, the pursuit itself is a testament to human ingenuity and curiosity. And so, Gliese 581g remains a beacon in the cosmos, a question waiting to be answered. It invites us to keep looking, to keep dreaming, to imagine what lies beyond the horizon of what we know. It reminds us that the universe is not a place of isolation but of infinite connections waiting to be made. It is a call to wonder, a reminder that in the quiet moments under our own starry sky, we are all part of something far greater than we can comprehend. The intrigue of Gliese 581g lies not only in its potential as a habitable world, but also in the tantalizing possibilities it opens for humanity's future. A future where exploration knows no bounds, and the stars become stepping stones rather than unreachable lights in the sky. Every detail we imagine about this distant planet draws us closer to a cosmic perspective, one that forces us to reconsider the nature of life, the limits of survival, and the destiny of civilizations. What if Gliese 581g is more than a world waiting to be discovered? What if it is a mirror, a reflection of what our own planet could become under different circumstances? The tidally locked nature of the planet creates a stark duality, a line between light and dark, hot and cold. On one side, the relentless rays of its red dwarf star bake the surface, while on the other, eternal night plunges the terrain into icy stillness. This duality challenges us to think about balance, about how life, if it exists there, might adapt not to one environment but to two extremes. Imagine how such an existence would shape life. Could there be creatures capable of crossing the line between the scorching day side and the frozen night side, their bodies evolving to endure both? Perhaps their physiology is a marvel of adaptability, with skin that reflects heat in the day and conserves warmth in the night, or with metabolisms that shift dramatically depending on their location. These beings might move in cycles, migrating with the winds that sweep between the hemispheres, their lives a rhythm in harmony with the planet's extremes. And what if these creatures are intelligent? A species evolved to survive such a world might possess an extraordinary understanding of balance, resourcefulness, and resilience. Their civilizations could be masterpieces of adaptation, their architecture designed to thrive in the Terminator zone where day and night meet. Imagine cities that stretch along this twilight band, their towers reaching into the thin, reddish atmosphere, capturing light and warmth while shielding their inhabitants from the harsher elements. These cities might glow faintly in the perpetual twilight, powered by geothermal energy or winds that never cease. If they look to the stars as we do, would they recognize Earth as a living planet? Would they interpret our broadcasts, the stray signals we've sent into the cosmos, as the first whispers of another intelligent species? What would they think of us? Would they see us as kindred explorers, reaching out into the void, or as enigmatic and unknowable as they would be to us. The thought of two civilizations, separated by light years, exchanging knowledge and understanding is both thrilling and humbling. But Gliese 581G might not wait for us to send a probe or detect a signal. It could be the first place where humanity sets foot on another world beyond our solar system. The idea of reaching it may seem like a distant dream, but history is full of impossible ambitions that were eventually realized. Concepts like interstellar travel, once relegated to science fiction, are slowly edging into the realm of possibility. The development of technologies like light sails, powered by lasers, or fusion propulsion systems could make the journey to Gliese 581G achievable within the lifetimes of future generations. Imagine humanity's first mission to Gliese 581G, a voyage spanning decades, with explorers entering a suspended state for the journey. Upon arrival, they awaken to the sight of an alien world, glowing faintly under the red light of its sun. As they descend through its atmosphere, the first glimpses of the surface appear. Landscapes shaped by forces both familiar and alien, rivers winding through rocky valleys, and perhaps even clouds hinting at the presence of water. What would we learn by stepping onto its surface? If life exists, every discovery would be a revelation, a window into the diversity of biology in the universe. Even if the planet is barren, it would still hold valuable insights into planetary formation, geology, and climate systems under the unique conditions of a red dwarf star. The data we gather would not only deepen our understanding of the cosmos, but also enhance our ability to protect and sustain life on Earth. But Gliese 581G isn't just about science. It's about inspiration. The pursuit of this distant world has already expanded our sense of what's possible, driving innovation and fostering collaboration across nations and disciplines. It reminds us that the universe is not a place of isolation, but a network of connections waiting to be uncovered. Every question we ask about Gliese 581G, about its environment, its potential for life, its role in the cosmic order, connects us to something larger, a shared curiosity that transcends borders and unites us in the quest to understand our place in the universe. As we dream of Gliese 581G, we are reminded that the stars are not beyond our reach. They are a challenge, a call to push beyond the limits of what we know and to embrace the boundless potential of exploration. Whether Gliese 581G proves to be a cradle of alien life, a silent rock, or something altogether unexpected, its story will continue to inspire us to look outward, to imagine, and to strive for the extraordinary. It stands as a symbol of humanity's greatest strength, our ability to wonder and our courage to seek answers in the vastness of the unknown. The fascination with Gliese 581G grows with every thought, every speculation, every scientific leap that brings us closer to unraveling its secrets. It stands as a silent guardian of the unknown, a celestial enigma that challenges humanity to push beyond its boundaries. Its distant orbit around a red dwarf star, so unlike our own sun, hints at the diversity of the universe, a reminder that the cosmos holds far more than we can see or even imagine. What if Gliese 581G is not just a singular curiosity but a gateway to understanding the vast potential of red dwarf systems? These stars, which make up about 70% of the stars in the Milky Way, are dim and long-lived, their lifespans stretching into trillions of years. They could be cosmic cradles, hosting countless habitable worlds that evolve slowly under their faint, steady glow. If life has emerged on Gliese 581G, it may have had far more time to evolve than life on Earth, potentially leading to forms and systems that challenge our understanding of biology, technology, and intelligence. The idea of such an ancient world teeming with life is as thrilling as it is humbling. Imagine ecosystems that have adapted to millions, even billions of years of stability. Evolution on Gliese 581G could produce creatures that embody efficiency, resilience, and cooperation in ways Earth's life never had to. These beings might possess an innate harmony with their environment, their survival tied intricately to the rhythms of their tidally locked planet. Such creatures might not simply live on their world. They might be its custodians, shaping and preserving it in ways we have only begun to understand on Earth. But what if Gliese 581G tells a different story? What if it is a world that once thrived but is now silent, a relic of a time long past? The possibility that it could harbor ruins, ancient cities buried beneath layers of dust or ice, adds a profound dimension to our search. If we were to find remnants of an advanced civilization, it would be the ultimate lesson in the fragility of existence and the fleeting nature of even the most resilient societies. Such a discovery would echo across time and space, a warning and a challenge for humanity to learn from the successes and failures of a species that came before. Even without life or civilization, Gliese 581G could be a treasure trove of knowledge. Its geologic record might reveal the history of its formation, the impact of its star's radiation, and the chemical processes that shaped its surface and atmosphere. Its conditions could provide insights into the variety of environments where life might arise, helping us refine our search for habitable planets in other star systems. By studying Gliese 581G, we would not only learn about a single world but also gain a deeper understanding of the universe's vast potential. The pursuit of Gliese 581G is not just about data, it is about vision. It represents humanity's greatest ambition, to reach for the stars and to understand the cosmos not as a distant, unreachable expanse but as a vast, interconnected web of possibilities. It challenges us to think big, to innovate, and to dream of futures that transcend the limitations of our present. Imagine what it would mean for humanity to send a spacecraft to this distant world, a vessel carrying the hopes and dreams of billions, reaching across the void to touch a new frontier. Such a mission would not only be a triumph of engineering and science but also a testament to our collective spirit. The first images sent back from Gliese 581G would capture the imagination of every person on Earth, uniting us in a shared sense of wonder and curiosity. What would we see in those images? Jagged cliffs bathed in red light? Endless plains of ice stretching into the shadows? Or perhaps something unexpected? A sign that we are not alone, that the universe is far richer and more complex than we ever dared to dream? The potential for discovery on Gliese 581G is as vast as the space that separates us from it. Every step we take toward understanding this world brings us closer to answering the most profound questions of existence. Are we alone? What is the nature of life? What is our place in the cosmos? The journey to Gliese 581G, whether it leads to life or silence, is a journey inward as much as it is outward, a journey to understand the universe and our role within it. And so, Gliese 581G remains a beacon, a challenge, and a promise. It invites us to look beyond the familiar, to embrace the unknown, and to explore not just with our instruments but with our minds and hearts. It is a reminder that the greatest discoveries often lie at the edge of the possible, waiting for those bold enough to seek them. The story of Gliese 581G is not yet written, but its pages are already filled with hope, ambition, and the unyielding human desire to explore the extraordinary. The story of Gliese 581G continues to unfold in our minds, a narrative fueled by the infinite possibilities it represents. Every thought about this distant world pushes us to question our assumptions about life, habitability, and the nature of the cosmos itself. Gliese 581g is not merely a scientific target. It's a symbol of what humanity can achieve when curiosity and determination collide. Imagine the first exploratory craft reaching Gliese 581g, equipped with advanced AI, sensors, and cameras to study its surface, atmosphere, and potential biosphere. As it descends into the planet's orbit, the spacecraft might pass through layers of clouds that have never felt the touch of light from Earth. Its instruments would detect subtle shifts in chemical signatures, atmospheric dynamics, and thermal energy, unraveling the mysteries of this tidally locked world. On the sunlit side, the probe might capture breathtaking images of endless deserts glowing under the red dwarf's steady light. The ground, scorched by millennia of exposure, could reveal unique mineral compositions or even hints of ancient geological processes. Winds might sweep fine dust into intricate patterns, creating landscapes both alien and beautiful. If liquid water exists here, it could be in deep underground reservoirs, shielded from the star's harsh radiation. A reminder that even the most extreme environments can harbor surprises. Crossing into the eternal night, the scene would shift dramatically. Frozen plains could stretch into the darkness, their icy surfaces fractured by the slow movements of geothermal heat escaping from beneath the crust. The probe's sensors might detect faint warmth near volcanic vents, evidence of internal activity that keeps the planet alive in its own way. And there, in the shadows, the possibility of subsurface oceans could emerge, a hidden sanctuary for life. But it is the Terminator Zone, the band where light and dark meet, that holds the most promise. This narrow region, where temperatures might balance to create Earth-like conditions, could be a cradle of habitability. Here, the probe might detect rivers of liquid water winding through rocky terrain or even vast seas reflecting the dim, crimson light of the star. The atmosphere might swirl with dynamic patterns, driven by the stark temperature contrasts between the hemispheres. If life exists, this is where we might first find it, clinging to the margins, thriving in the balance between extremes. The potential for life on Gliese 581g extends far beyond our understanding of biology. If life evolved under the planet's unique conditions, it might have taken paths we cannot yet imagine. Could microbial life forms float in the upper atmosphere, feeding on chemical compounds carried by the winds? Could surface organisms have evolved to absorb the weak red light, their structures optimized for photosynthesis in a way entirely alien to Earth? The discovery of even the simplest life form on Gliese 581g would revolutionize our understanding of the universe, proving that life is not an Earth-exclusive phenomenon but a natural consequence of the right conditions. And then there's the question of intelligence. If Gliese 581g harbors advanced life, what form might it take? A civilization evolved under the constraints of a tidally locked world would face challenges unlike any we've known. Their architecture might incorporate elements designed to protect against radiation on the day side or insulate against the cold on the night side. Their technology might harness geothermal energy or rely on atmospheric dynamics, using the planet's unique environment to their advantage. If these beings exist, would they have discovered us? The faint signals of human civilization, radio waves, television broadcasts, and radar pulses, have been radiating into space for decades. By now, they would have reached Gliese 581g, faint echoes of a distant world. If intelligent life exists there, they might be listening, trying to decode the signals from a planet orbiting a faraway yellow star. And if they've sent signals of their own, could we detect them? What would they say? A simple greeting? Or something far more profound? The search for such signals, part of humanity's ongoing efforts in the search for extraterrestrial intelligence, SETI, remains one of the most exciting and speculative areas of science. Every scan of the skies, every analysis of interstellar noise, carries the hope that we might one day hear a voice from another world. Gliese 581g, with its potential for habitability, is one of the prime targets for such a discovery. The thought that we could one day establish contact with another civilization is as thrilling as it is humbling, a reminder of the vastness of the cosmos and the connections that might lie waiting to be uncovered. Even if we never find life on Gliese 581g, its existence or the search for it would still shape our understanding of the universe. The study of its environment, geology, and atmosphere could provide insights into planetary systems, the role of red dwarfs in supporting life, and the delicate balance required for habitability. It would deepen our understanding of Earth's uniqueness and fragility, reminding us of the cosmic factors that make life possible. Gliese 581g remains a symbol of humanity's drive to explore and to dream. It challenges us to think beyond our immediate surroundings, to imagine worlds far different from our own, and to embrace the unknown with open minds and relentless curiosity. Whether it is a cradle of life, a barren rock, or a relic of something ancient, its story is one we are writing with every observation, every question, and every step into the cosmic frontier. In the end, Gliese 581g is not just about what we might find, it's about the journey. It's about daring to look beyond the confines of Earth, to imagine what lies out there, and to recognize that we are part of a universe filled with infinite possibilities. As we continue our search, Gliese 581g stands as a beacon of hope and wonder, a reminder that the greatest discoveries often lie just beyond the horizon, waiting for those bold enough to seek them. The allure of Gliese 581g refuses to dim, drawing us ever deeper into its mystery with the promise of answers that could transform not just science, but humanity's very sense of identity in the cosmos. Every imagined detail about this distant world sharpens the edges of our curiosity, painting a picture of a place both alien and oddly familiar. It challenges us to stretch our minds, to envision what it would mean to stand on such a planet, to breathe its air, and to witness its landscapes under a red, eternal sky. Imagine that first human step onto Gliese 581g's surface, a moment that would echo through history as profoundly as the Apollo moon landings. The astronauts would step into a world where nothing is ordinary, where every rock, every breeze, every trace of moisture tells a story billions of years in the making. Would they find a surface carved by ancient rivers, their dry beds a relic of a time when the planet was warmer? Or would they see ice formations, frozen sculptures created by winds that howl endlessly between the hemispheres? Even the soil underfoot could hold secrets, its composition hinting at the planet's geological history and the processes that shaped its evolution. As explorers moved toward the Terminator Zone, the planet's dynamic nature would become more evident. Here, the balance between light and dark might create a microclimate rich with complexity. Winds sweeping from the scorching day side could mix with the freezing air of the night side, creating powerful storms that rage perpetually in this twilight band. The explorers would face not just physical challenges, but profound existential questions. Every sample collected, every image captured, would demand a deeper understanding of how this world came to be, and what it means for Earth and our place in the cosmos. The possibility of life on Gliese 581g is the ultimate enigma, the tantalizing thread that keeps scientists and dreamers alike captivated. If life has emerged on this distant world, it may look nothing like life on Earth. The conditions on Gliese 581g would drive evolution down paths we cannot yet imagine. Organisms might be silicon-based instead of carbon-based, Their metabolisms adapted to the weaker red light of the star. Plants, if they exist, could be dark-hued or even black, absorbing every possible photon to fuel their growth. Microbes might flourish underground, protected from the radiation of the dayside and the deep cold of the night. But what if life on Gliese 581G is more than microbial? What if this world has fostered the rise of intelligence? The idea of an alien civilization evolving under the dim light of a red dwarf is almost impossible to resist. Such a society would have developed in conditions utterly unlike those on Earth. Their culture, technology, and way of life would have been shaped by the extremes of their environment. Perhaps they built cities along the Terminator line, harnessing geothermal energy or wind power to sustain themselves. Or perhaps their civilization developed underground, where conditions are more stable, emerging only occasionally to explore the surface. The thought of communicating with such beings is as exhilarating as it is daunting. How would they perceive us? Would they understand our signals, our attempts to reach across the void? Would they even recognize us as intelligent beings? Or would their own form of intelligence be so different that mutual understanding becomes a puzzle of cosmic proportions? And if they were to send a message, what would it say? A greeting? A warning? Or something far more cryptic? An insight into a way of thinking shaped by a world so unlike our own? Even if Gliese 581G turns out to be lifeless, it still holds immense value. Its study would give us a deeper understanding of the conditions that lead to habitability, helping us refine our search for life on other exoplanets. It would offer insights into the effects of tidal locking, atmospheric dynamics, and the impact of red dwarf stars on their planets. Every piece of data would add a new chapter to our understanding of planetary science. Each discovery a step closer to answering the biggest questions about the universe. As we dream of exploring Gliese 581G, we are reminded of the incredible journey humanity has already undertaken. From gazing at the stars with naked eyes to building telescopes capable of peering across the galaxy, our curiosity has driven us to reach for the unknown. Gliese 581G is the next frontier, a symbol of what lies ahead if we continue to push the boundaries of what is possible. The pursuit of Gliese 581G represents the best of what humanity can achieve. It is a story of exploration, innovation, and hope, a story that belongs not just to scientists and engineers, but to everyone who dares to look up at the night sky and wonder. Whether it is a cradle of life, a silent rock, or something entirely unexpected, Gliese 581G will remain a beacon of inspiration, a reminder that the universe is vast, mysterious, and full of possibilities waiting to be discovered. The journey to this distant world is more than a scientific endeavor. It is a testament to the human spirit, to our unyielding desire to explore and to dream of what lies beyond. The mystery of Gliese 581G is not just a scientific curiosity. It is an unending story about humanity's place in the cosmos. It calls to us with the weight of potential, urging us to look beyond our planet, beyond our limitations, and beyond our present understanding of life. This distant world, shrouded in both scientific debate and dreams of discovery, represents the ultimate frontier, a destination not just for exploration, but for transformation. The journey to Gliese 581G is, at its core, a journey inward. As we imagine the landscapes of this alien world, its extreme environments, and its potential for life, we are forced to confront questions about our own existence. Why do we seek to know what lies beyond? What drives us to search for others in the vastness of the universe? The answers lie in the very essence of what it means to be human. The desire to understand, to connect, and to find meaning in the infinite. If Gliese 581g holds life, even in its simplest forms, it would shatter the notion of Earth's uniqueness. A single microbial organism would be a cosmic revelation, proving that life is not confined to our blue planet but a phenomenon woven into the fabric of the universe. Such a discovery would redefine biology, forcing us to rethink the conditions under which life can arise and thrive. It would inspire generations of scientists, philosophers, and dreamers to explore the implications of a universe teeming with possibility. If, however, Gliese 581g is barren, it would still speak volumes. Its silence would not be a failure of exploration but a reminder of the delicate balance that makes Earth so special. It would be a testament to the extraordinary conditions that have allowed life to flourish here. A fragile gift that we must protect at all costs. A lifeless Gliese 581g would challenge us to cherish our own planet even more deeply, to ensure that the spark of life continues to burn brightly in a universe that may be, in many places, cold and quiet. The dream of reaching Gliese 581g stretches the limits of our imagination and our technology. Today, it is a distant point of light in our telescopes, its existence inferred through subtle wobbles in its star. Tomorrow, it could be the target of robotic probes, equipped with the tools to map its surface and search for signs of life. One day, it could even be humanity's first interstellar destination, a world where our descendants might walk under a red sky, their every step a testament to the indomitable spirit that carried them across the stars. But the journey to Gliese 581g is not only about reaching another world. It is about what we become in the process. To explore such a distant planet, we must innovate, collaborate, and think on a scale that transcends borders and generations. The technologies developed for this endeavor, advanced propulsion systems, sustainable life support systems, and artificial intelligence, will not only bring us closer to the stars but also transform life on Earth. The pursuit of Gliese 581g is a call to unite, to work together in the name of discovery, and to dream beyond the confines of what seems possible. This distant world, locked in a delicate balance of light and dark, represents the balance we seek in our own lives. The balance between fear of the unknown and the courage to face it, between our attachment to Earth and our longing to explore. Gliese 581g is a reflection of our greatest strengths as a species, our resilience, our curiosity, and our unyielding hope for a future filled with wonder. As we continue to search for answers, Gliese 581g reminds us that the universe is not a void but a stage, vast and filled with potential. Whether it is a living world, a silent witness to time, or something entirely unexpected, it stands as a symbol of what lies ahead for humanity. It is a challenge, a promise, and a dream that drives us ever forward. In the grand narrative of the cosmos, Gliese 581g is but one chapter, but it is a chapter that invites us to write the story of exploration, discovery, and connection. It urges us to ask questions we've never dared to ask and to seek answers we've never imagined possible. It is a reminder that the greatest journeys are those that push us beyond what we know, into the infinite unknown. And as we stand at the threshold of this journey, we are reminded that the true destination is not just a distant planet but the future itself. A future shaped by our courage to dream, to explore, and to reach for the stars.
Makemake, one of the fascinating trans-Neptunian objects in our solar system, stands as a key member of the distant Kuiper Belt, a region of icy bodies located beyond the orbit of Neptune. This dwarf planet, formally recognized by the International Astronomical Union (IAU) in 2008, has intrigued astronomers since its discovery due to its unique combination of physical, chemical, and orbital characteristics. Discovered on March 31, 2005, by a team led by Michael E. Brown, Chad Trujillo, and David Rabinowitz, this enigmatic world has become a focal point of study for understanding the outer reaches of the solar system. Makemake's name is derived from the mythology of the Rapa Nui people, the indigenous inhabitants of Easter Island. In their culture, Makemake is a creator deity, an appropriate name for a celestial body that opens new chapters in humanity's understanding of the cosmos. This remote world, often described as a Plutoid because of its similarities to Pluto, provides critical insights into the formation and evolution of the solar system's outer regions. With a diameter of approximately 1,430 kilometers, Makemake ranks as the third largest known dwarf planet in the solar system, following Pluto and Eris. Its size, though modest compared to planets, is substantial enough to allow its gravity to shape it into a roughly spherical form. This classification criterion, along with its orbit around the Sun and its inability to clear its orbital path of debris, secures its status as a dwarf planet under the IAU's definition. Observations of Makemake have revealed an intriguing surface composition dominated by methane, ethane, and other hydrocarbons, which are thought to give the dwarf planet its reddish hue. Spectroscopic studies conducted using ground-based telescopes, such as the Very Large Telescope, VLT, in Chile, have been instrumental in identifying these compounds. The presence of methane ice, in particular, draws parallels with both Pluto and Neptune's moon Triton, suggesting commonalities in the processes that shape these distant objects. The surface of this distant world is believed to be extremely cold, with temperatures averaging around -243 degrees Celsius. At such frigid temperatures, volatiles like nitrogen and methane freeze solid, forming an icy crust that reflects sunlight with a moderate degree of brightness. Makemake's albedo, or reflectivity, is higher than that of most other Kuiper Belt objects, KBOs, which has aided in its detection and characterization. Makemake orbits the Sun at an average distance of about 45.7 astronomical units, AU, equivalent to roughly 6.8 billion kilometers. Its elliptical orbit takes it around the Sun once every 305 Earth years, with a slight inclination of 29 degrees relative to the plane of the solar system. This inclined trajectory places Makemake among the dynamically hot KBOs, which have orbits more tilted and eccentric than the cold classical KBOs like Quaoar. One of the most intriguing aspects of this Kuiper Belt object is its lack of a significant atmosphere. Unlike Pluto, which experiences seasonal atmospheric changes due to the sublimation of nitrogen and methane ices, Makemake's tenuous atmosphere, if present at all, is likely composed of trace amounts of methane and nitrogen. Observations during stellar occultations, when the dwarf planet passes in front of a distant star, have provided valuable constraints on its atmospheric properties. These events reveal a sharp drop in brightness, indicative of a lack of a substantial gaseous envelope. In 2016, the Hubble Space Telescope made a groundbreaking discovery by identifying a small moon orbiting Makemake. This satellite, unofficially nicknamed 2 Malawian Kwachas, is estimated to have a diameter of about 175 kilometers. It's the trans-Neptunian body, known as Makemake, stands as a remarkable example of the icy worlds populating the outer reaches of our solar system. This celestial object, part of the Kuiper Belt, occupies a region teeming with primordial remnants from the early formation of the Sun and its planetary system. Since its discovery in 2005 by a team of astronomers led by Michael E. Brown, the frozen sphere has captivated scientists eager to unravel the mysteries of these distant and enigmatic objects. This dwarf planet, the third largest among its peers, boasts a diameter of approximately 1,430 kilometers, situating it in the same category as Pluto and Eris. Unlike the inner rocky planets or the gas giants, the icy surface of this world is composed primarily of frozen methane, ethane, and other hydrocarbons, which give it a reddish hue. Spectroscopic analyses, carried out with advanced telescopes like the Very Large Telescope, VLT, in Chile, have been pivotal in uncovering the chemical composition of the Kuiper Belt object. Orbiting at an average distance of 45.7 astronomical units, AU, from the Sun, this remote sphere takes approximately 305 Earth years to complete a single orbit. Its elliptical path, inclined by 29 degrees relative to the ecliptic plane, distinguishes it from many other solar system objects. These orbital characteristics classify the icy body as part of the dynamically hot population of the Kuiper Belt, where orbits tend to be more eccentric and inclined than the cold population. Interestingly, this far-off world exhibits a surface that is highly reflective, with an albedo higher than that of most other trans-Neptunian objects. This bright reflectivity, coupled with its size, made it a relatively easier target for telescopes to detect compared to smaller, darker Kuiper Belt objects. Its icy crust, composed of solidified methane and nitrogen, reflects sunlight with a unique reddish tint, linking this distant body to other notable objects like Pluto and Triton, Neptune's large moon. Unlike Pluto, however, this celestial body lacks a significant atmosphere. Stellar occultations, events where the icy sphere passes in front of a background star, have revealed that it does not possess the thick layers of nitrogen and methane gas seen on its sibling dwarf planet. At its average surface temperature of -243 degrees Celsius, any gases would freeze rapidly, leaving only a tenuous, almost imperceptible envelope of methane molecules. Adding to the intrigue, in 2016, astronomers using the Hubble Space Telescope uncovered a faint satellite orbiting this frozen world. The Moon, provisionally labeled 2 Malawian Kwaches, is estimated to be about 175 kilometers in diameter. The discovery of this satellite has opened new doors for research, allowing scientists to measure the mass and density of the dwarf planet with greater precision. By observing the orbital dynamics of 2 Malawian Kwaches, researchers aim to gain deeper insights into the internal structure of this trans-Neptunian object and its formation history. The discovery of this moon also hints at the possibility that this distant body underwent a significant collision event in the past, similar to the impacts theorized for other dwarf planets and their moons. Such events are thought to have played a critical role in shaping the Kuiper Belt as we observe it today, providing clues to the early chaotic phase of the solar system's evolution. This icy world's methane-rich surface composition links it chemically to Pluto and Triton, suggesting a shared evolutionary pathway for these distant objects. Methane, one of the simplest hydrocarbons, plays a vital role in determining the color and reflectivity of this frigid world. The reddish hue observed on its surface is likely the result of complex organic molecules, known as tholins, formed through the interaction of methane with ultraviolet radiation from the Sun. These tholins are common on outer solar system bodies and are responsible for the strikingly varied colors of trans-Neptunian objects. Scientists hypothesized that the distant sphere's lack of significant nitrogen ice might be due to its smaller size and weaker gravity, which would make it more difficult for the object to retain lighter gases over billions of years. This hypothesis contrasts sharply with Pluto, which has managed to sustain a thin but dynamic nitrogen-rich atmosphere. The comparative study of these worlds offers a glimpse into the diversity of conditions and evolutionary pathways among objects in the outer solar system. Further investigations into this Kuiper belt member have been bolstered by advanced telescopic technologies and computational modeling. Observations using infrared spectroscopy have provided evidence for seasonal changes on the surface of this frozen sphere. These changes, though far less dynamic than those on Earth or Mars, hint at subtle shifts in the distribution of ices as the dwarf planet travels through its elongated orbit around the Sun. The exploration of this enigmatic object has also fueled discussions about potential spacecraft missions to the Kuiper belt. While current missions, such as NASA's New Horizons probe, have provided invaluable data on similar bodies, a dedicated mission to this dwarf planet and its moon could revolutionize our understanding of the outer solar system. By studying this world up close, scientists could analyze its geology, surface chemistry, and potential subsurface layers, answering long-standing questions about the building blocks of planets and the processes that govern their evolution. This frozen world, residing in the cold and distant reaches of the solar system, represents a time capsule of early solar system materials. Its study not only sheds light on the dynamics of the Kuiper belt but also provides broader insights into the mechanisms that drive planetary formation and migration. Through ongoing research and future exploration, the mysteries of this icy body continue to inspire curiosity and expand the boundaries of human knowledge. The frozen orb stands as a crucial key to understanding the broader landscape of the Kuiper belt, a region that serves as a repository for ancient materials from the dawn of the solar system. Unlike the rocky planets of the inner solar system or the gas giants further out, this remote celestial body represents a category of icy worlds that formed in the outermost reaches, where the sun's warmth is but a faint glow. Its composition, structure, and orbit together create a unique portrait of conditions far removed from those familiar to earthbound observers. One of the remarkable features of this Kuiper belt resident is its stability over time. Despite its vast distance from the Sun and its relatively small size, the dwarf planet has maintained a consistent orbital path for billions of years. This stability has allowed astronomers to study the interactions between it and other trans-Neptunian objects, offering critical insights into the gravitational dynamics of the outer solar system. The inclined orbit of this icy body, with its significant tilt compared to the plane of the solar system, suggests a turbulent past. It is likely that gravitational interactions with Neptune, or perhaps with other large Kuiper belt objects, played a role in shaping its current trajectory. The absence of significant atmospherics on this distant sphere has not deterred scientists from probing its surface for clues about its evolutionary history. High-resolution imaging and spectroscopy have revealed a patchwork of icy materials, including solid methane and ethane, alongside traces of more complex organic molecules. These compounds, while frozen solid under the extreme cold, bear evidence of photochemical reactions driven by the faint sunlight and cosmic rays that permeate the outer solar system. The reddish tint that characterizes its surface is a hallmark of such processes, with tholins, organic residues formed from methane, providing the distinctive coloration. Further exploration of this icy sphere's surface has revealed intriguing hints about its geological processes. While its small size and low gravity likely prevent tectonic activity or large-scale volcanism, there is evidence to suggest that sublimation and deposition cycles may occur on a seasonal basis. As the frozen world moves closer to the Sun in its elliptical orbit, some of its methane and nitrogen ices could transition directly from solid to gas, creating transient atmospheric effects or causing slight changes in the surface texture. These processes, though subtle, are of immense interest to planetary scientists, as they mirror phenomena observed on other Kuiper Belt objects like Pluto. The discovery of a small satellite orbiting this celestial object has added a new layer of complexity to its study. 2 Malawian Quachas, as the Moon is informally known, is much darker than its parent body, reflecting only a fraction of the sunlight. This stark contrast in albedo suggests that the Moon and its host may have originated under different circumstances. One prevailing theory is that the satellite was formed as a result of a massive collision, similar to the events that are thought to have created Pluto's moon system. Such a collision would have ejected material from the surface of the icy world, which later coalesced to form the smaller companion. The existence of 2 Malawian Quachas also provides astronomers with a unique tool for studying the mass and density of the frozen orb. By carefully tracking the motion of the Moon around its primary, scientists can calculate the mass of the entire system, shedding light on its internal composition. Early estimates suggest that the density of this Kuiper Belt resident is lower than that of Pluto but higher than some smaller trans-Neptunian objects, implying a mixture of rock and ice in its interior. These findings hint at a layered structure, with denser materials concentrated in the core and lighter ices forming the outer shell. In addition to its intrinsic scientific value, the study of this remote celestial body holds broader implications for understanding the history of our solar system. The Kuiper Belt, of which this dwarf planet is a part, is believed to be a remnant of the primordial disk of gas and dust that gave rise to the Sun and its planets. By analyzing the composition and distribution of these icy objects, researchers can reconstruct the conditions that prevailed during the early stages of planetary formation. This frozen sphere, with its pristine ices and unaltered surface features, serves as a time capsule preserving the chemical and physical processes that shaped the solar system's infancy. The implications of studying this distant world extend beyond the confines of our solar system. Similar icy bodies are thought to populate the outer regions of other planetary systems, where they may serve as building blocks for planets or as reservoirs of water and organic materials. Understanding the processes that govern the evolution of this frozen orb can therefore provide valuable insights into the potential habitability of exoplanetary systems and the origins of life elsewhere in the universe. Despite its remoteness, this trans-Neptunian body remains within reach of modern astronomy. Ground-based telescopes equipped with adaptive optics, as well as space-based observatories like the James Webb Space Telescope, continue to provide detailed observations of its surface and surroundings. These instruments have opened new windows into the chemistry and physics of the frozen world, revealing intricate details that were once beyond the reach of human knowledge. Future missions to this icy sphere, though technically challenging, are already being considered. A spacecraft equipped with advanced imaging systems and spectrometers could map its surface in unprecedented detail, revealing the distribution of ices, organics, and other materials. Such a mission could also investigate the properties of 2 Malawian Quachas, providing a more complete picture of the system as a whole. By venturing into the Kuiper Belt, humanity could achieve a deeper understanding of the forces that govern the outer solar system and the processes that drive its ongoing evolution. The remote icy body serves as a critical focal point for the study of planetary systems in their infancy. As one of the larger members of the Kuiper Belt, it represents a class of objects that have remained largely unchanged since the solar system's formation approximately 4.6 billion years ago. These distant worlds, often referred to as fossils of the early solar nebula, offer a glimpse into the conditions that existed before the major planets coalesced from the primordial disk of gas and dust. The frozen celestial sphere's surface is a testament to the extreme environment in which it resides. Temperatures hover near absolute zero, at around -243 degrees Celsius. At such frigid levels, volatile compounds like nitrogen and methane freeze solid, forming a crust of ices that preserves the chemical history of the early solar system. This pristine environment is not only scientifically valuable but also serves as a natural laboratory for studying the behavior of materials under conditions far removed from those on Earth. One of the most intriguing aspects of this outer solar system world is its potential internal structure. While direct observations are impossible without a dedicated spacecraft mission, models based on its size, density, and surface composition suggest a differentiated interior. Beneath the icy crust, the trans-Neptunian body may harbor a layer of water ice mixed with rocky material. At greater depths, under the pressure of overlying layers, this water ice could transition to an exotic form known as high-pressure ice. Such internal layering is consistent with what has been inferred for similar-sized dwarf planets like Pluto and Eris. The density of the frozen celestial object, estimated from the orbital motion of its moon 2 Malawian-Quachas, indicates that it is likely composed of a mixture of rock and ice, with rock constituting a significant portion of its mass. This combination aligns with the idea that objects in the Kuiper belt formed in a region where water and other volatile compounds were abundant, but temperatures were too low for significant accretion of gaseous materials. These conditions contrast sharply with those of the inner solar system, where rocky planets formed in a hotter, more volatile depleted environment. The Kuiper belt residence moon, 2 Malawian-Quachas, continues to be a topic of intense scientific interest. With its dark surface and small size, this satellite poses unique challenges for observation, even with the most advanced telescopes. Nevertheless, the discovery of this moon has provided an invaluable tool for determining the mass and gravitational field of the parent body. By analyzing the orbital dynamics of 2 Malawian-Quachas, researchers can refine their models of the dwarf planet's internal structure and gain insights into the processes that led to the formation of this binary system. The relationship between this icy world and its satellite raises questions about the broader processes that govern the formation of moons in the Kuiper belt. In the case of the distant sphere, the leading theory is that 2 Malawian-Quachas was created through a giant impact, in which a collision with another Kuiper belt object ejected material into orbit. Over time, this debris coalesced into the moon we observe today. Such impact events were likely common in the early solar system, as countless small bodies collided and merged to form the larger objects we see today. In addition to its role in understanding the solar system's past, the study of this remote world holds implications for the search for life beyond Earth. While the frozen orb itself is unlikely to support life due to its extreme cold and lack of liquid water on the surface, it represents a class of objects that may exist in other planetary systems. The presence of water ice and organic compounds on its surface suggests that similar materials could be common in exoplanetary systems, where they might serve as the building blocks for life. Moreover, the exploration of this frozen celestial body and its neighbors could help scientists understand the distribution of water and organics throughout the solar system. These materials are thought to have been delivered to the inner planets, including Earth, by comets and other icy bodies during the late heavy bombardment period. By studying the chemical composition of Kuiper belt objects, researchers can trace the pathways by which life-essential elements were transported across vast distances. Future missions to this distant celestial sphere are likely to revolutionize our understanding of the Kuiper Belt. A spacecraft equipped with high-resolution cameras, spectrometers, and radar instruments could map the surface in unprecedented detail, revealing the distribution of ices, organics, and other materials. Such a mission could also investigate the Moon 2 Malawian Quachas, providing a more complete picture of the system as a whole. The data collected would not only deepen our knowledge of this specific object but also shed light on the broader processes that govern the formation and evolution of the outer solar system. The technical challenges of reaching the frozen sphere are significant, but not insurmountable. The vast distance, combined with the need for advanced propulsion systems and power sources capable of operating in the frigid, low-light conditions of the Kuiper Belt, requires innovative engineering solutions. NASA's New Horizons mission to Pluto and the Kuiper Belt has demonstrated the feasibility of exploring these distant regions, paving the way for more ambitious missions in the future. This icy body and its companions in the Kuiper Belt are more than just distant curiosities, they are windows into the origins of our solar system and the processes that continue to shape it. By studying this frozen world and its environment, scientists can address some of the most profound questions in planetary science. How did the solar system form and evolve? What role did icy bodies play in delivering water and organic materials to Earth? And what can these distant objects teach us about the potential for life elsewhere in the universe? The scientific journey to understand this frozen sphere is far from over. As technology advances and new discoveries are made, the mysteries of this remote world will continue to inspire curiosity and exploration, driving humanity ever further into the depths of the cosmos. The frozen sphere, a silent wanderer of the Kuiper Belt, represents an ancient fragment of the solar system's earliest epochs. Its story is woven into the dynamic and chaotic processes that govern the formation of planets, moons, and smaller celestial bodies. As one of the largest known Kuiper Belt objects, this trans-Neptunian body occupies a unique position, bridging the gap between the icy remnants of the solar nebula and the more familiar planetary systems closer to the Sun. The orbital mechanics of this distant orb reveal fascinating insights into the gravitational influences shaping the outer solar system. Its elongated, inclined orbit, which takes it as far as 53 astronomical units, AU, from the Sun at its aphelion, reflects the complex interplay of forces at work in the Kuiper Belt. The perturbations caused by Neptune's gravity, along with interactions with other large Kuiper Belt objects, have likely sculpted the path of this icy wanderer over billions of years. This orbital behavior is not merely a curiosity, it provides clues to the early migration of the giant planets, particularly Neptune and Uranus, which are thought to have shifted positions during the solar system's formative years. Comparing this celestial body to its counterparts, such as Pluto, Eris, and Haumea, reveals a diverse population of icy worlds, each with its own unique characteristics. While Pluto is known for its dynamic surface and tenuous atmosphere, the frozen celestial sphere lacks such activity, likely due to its smaller size and weaker gravitational field. Eris, the most massive known dwarf planet, shares some similarities in surface composition, with both objects displaying evidence of methane ice. Haumea, on the other hand, stands out with its elongated shape and rapid rotation, characteristics not observed in the more spherical and slower rotating body in question. One intriguing aspect of this trans-Neptunian object is the potential for subsurface processes despite its frigid environment. Models suggest that, under its icy crust, the distant sphere may harbor a layer of liquid water or slush, kept warm by the decay of radioactive isotopes in its rocky core. While speculative, this possibility raises fascinating questions about the potential habitability of such environments. Subsurface oceans have been proposed for other icy worlds, including Europa, Enceladus, and even Pluto, suggesting that liquid water reservoirs might be more common in the solar system than previously thought. The frozen orb's lack of a substantial atmosphere distinguishes it from Pluto, whose nitrogen-rich atmosphere undergoes seasonal variations as it approaches and recedes from the Sun. Observations during stellar occultations have confirmed that any gaseous envelope surrounding this distant body is vanishingly thin, composed primarily of trace amounts of methane and possibly nitrogen. This scarcity of atmospheric volatiles likely reflects the object's smaller size and weaker gravity, which make it less capable of retaining light gases over geological timescales. The surface chemistry of the frozen sphere offers a window into the chemical processes operating in the outer solar system. The detection of methane, ethane, and other hydrocarbons on its surface suggests ongoing